So here the same concept but differences. Here we're going to use oxidation only, but here we're going to use hot concentrated KMnO4. So what does this depend? Here the KMnO4 in the earlier one and this one also, the oxidation state is 7. Done. Here what happens, this reaction, it depends on, most important thing which is remember, it depends on arrangement of groups around carbon-carbon double bond. Okay, this is what is depends. What am I trying to explain? I'll just tell you taking certain examples. Now let us take stage 1. Let me divide this one into stage 1 and stage 2. In stage 1, suppose I have an alkene like this. Okay, C double bond C. Here there are alkyl groups R1. This is R2. There is one more alkyl group R3. This is R4. Now I said KMnO4 is going to release out nascent oxygen, correct? So here I am going to take nascent oxygen O. So how many? 2. So what type of product we'll get? There is a cleavage of this bond. We get 2 different products. One is C, R1 is here, R2 is here, double bond O. One more C, one more adds here to this carbon, R3 and R4. This is the condition. This is first stage. Now let us take certain examples for this and understand what does this mean. Suppose if I take an example for this, right? Let me take first example. Right. The concept is the same, but it differs. We are getting the carbonyl compounds. We will see. Suppose if I take here carbon, now 1, 2, 3, 4 different alkyl groups, isn't it? Here I am going to take CH3, here I am going to take CH3, here I am going to take CH3, here also I am going to take CH3. Now how many did I add? I have added 2 nascent oxygens which I got it from KMnO4 in the earlier video. Done. So how does it do? What product? There is a cleavage of the bond here. There is a cleavage here, it breaks here. And what do I get? I am going to get one product here. This is CH3. C double bond O CH3, okay, plus, okay, once again O C CH3 and CH3, okay, done, isn't it? I have got ketones, both the ketones.
Unacademy, the biggest online platform, learning platform in India. Let's crack it. I'm Vani Potepalli, the verified educator for grade 12 students, CBSE, ICSE as well as state board students are with me. These are the Unacademy Plus subscription features where you have daily practice sessions, mock tests which are going on, live quizzes which will be going on, subjective test series coming soon. Join us. Unacademy iconic subscription features include personal mentors. You have live doubt clearing sessions. Weekly reports will be sent to the parents. Parent connect where the report will be sent to the parent and the educators are in contact with the parents too. A study planner is perfectly planned and all benefits of Plus also will come under iconic. Vani10 and Vani Life is my referral code. These are the subscription rates for 11 and 12 Plus iconic subscription. Rates are given. Please check the rates, students. Vani10 and Vani Life is my referral code again to mention. These are grade 12 subscription for the Plus and grade 12 subscription for the iconic. You can choose for 1 month, 3 months also because you still have 100 days for the board examination of students. Join me there. So you have free sessions, students, which are planned for both grade 11 and 12. So join me in the special classes. Students, for grade 12 students, the topic, the date and the timings are mentioned here. It's going to start on 17th February and it's going to be for almost 10 days. Note the timing, students, note the topics. All sessions are free for you all. As your board practicals are coming, I'll be giving you tips and tricks also to perform board practicals 2021. Timings are 8 p.m. to 9 p.m. This is for the grade 11 students. Same students, I'll be meeting you from 16th February. This is going to go for almost 10 days. Topics, date and time are mentioned. I'll be giving you all one-shot revisions. Please join me in the session. It's for free. Download the Unacademy app for this, students. Right. So there is an Unacademy Ascent All India Championship for classes 6 to 12. Date is on 13th February 2021. Timings would be 11 a.m. to 12 p.m. students. Almost the prizes of 5 lakh rupees, students. You can win a scholarship. So this is the procedure to attend. If you're a new user, download the Unacademy app. Follow the instructions given here. and join in the competition. The step 1, 2 and 3 and 4 are mentioned here. You can just join easy. 3 steps to become a champion. Step 1, preparation. Step 2, to participate in the All India Championship on February 13. Step 3, to get analysis from the top educators after the test. Date is 13 February, 11 am to 12 pm, and scholarship amount is 5 lakh students. Enroll now. Link is given in the description. Please check.
This is example 1. Suppose if I take, now I'm going to change this combination, just see. Suppose if I go with example 2. So in earlier one, what did I get? I've got ketones in both the ways. Now I'm going to change the ketone, taking 2 example. Here what will I take? I'll take again alkene. But now, instead of 4 alkyl groups, here I'll be taking 1 alkyl group here. I'll be taking 1 more alkyl. This is H. See here, I have changed this group now. Earlier it was CH3. Now I have changed the group to H. Now again I'm going to take 2 nascent oxygens because I need to break on either side. There is a cleavage of the bond here. And what do I get? I'm going to get CH3, C, a hydrogen, double bond O. That is 1 more, and these 2 will be here. O, C, CH3 and CH3. Done, isn't it? Fine. Now I've got an aldehyde and a ketone because I've changed the group. Now, suppose if I take one more example and one more thing. What will happen to this aldehyde? This aldehyde further, it undergoes oxidation, right? And it becomes an acid. CH3 here, oxidation, oxygen adds here. So C is here, H, and this becomes CO. That means it looks like this. Let us write in this way. Let me erase this out. This one, CH3, C, double bond O and OH. This is an acid. So aldehydes and oxidation gives acids. Remember this. Okay, aldehydes and oxidation gives acids. This is the concept. So let's understand. So I have given you what combination. Let's see this. I have this combination. Then I have the second, first general one, first example, second example. Now let me take the third set of example. So here when I take the third example, what am I going to do? Now I am going to change the groups. Earlier first it was 4 alkyl groups. Then I have taken out 1 alkyl group and added hydrogen. Now in the third example, I am going to take hydrogen, 2 methyl groups only. Then again, now I am going to add 3 nascent oxygens. Right? So just see how does it go about. When I add this, again there is a cleavage of the bond here. So what will happen? Just see here, H, C. Now I'm adding 3, isn't it? So H, first one, C, O, OH, plus here this bond is broken. This becomes C double bond O, CH3, CH3. Done. So what is the name of this? This is a ketone. Which ketone? This is propanone. Let us write. This is propanone. Now what is the name of this compound? This is HCOOH. It is methanoic acid. 1 carbon, isn't it? So it is methanoic acid. So this methanoic acid further, when I have to oxidize this, I'm going to further oxidize this. What should I do? I have to use KMnO4. When I further oxidize this, I get products like carbon dioxide and water. That's it. So this is how is a combination. This is how it goes about in terms of hot concentrated KMnO4. Now let us summarize one important thing about this reaction. When we have to write the summary of this particular thing, remember when you have 2 alkyl groups, okay, 2 alkyl groups at one end, 2 alkyl groups at one end, what will it convert into? That part will get converted, one part will get converted into ketones, right? Suppose if you have 1 alkyl group and 1 H, R stands for alkyl group, then they get converted into acids. Suppose if you have 2 hydrogens and 2 alkyl groups on either side, then finally it gets converted to carbon dioxide and water. So this is your reaction. So this is how we are going to study the hot concentrated conditions, students. So thank you for watching. I'll meet you again with the next type of reaction, that is substitution reactions of alkenes. Right. So welcome students to one more reactions of alkenes, that is polymerization reactions. So till now we have seen the addition reactions of alkenes, based on which rule we have studied, based on Markovnikov as well as anti-Markovnikov addition rule. Right, so I have also taught the mechanism in the previous videos. Now we will almost completing the alkene chapter. Like we just left with polymerization as well as oxidation reactions. So we'll finish that and go back to alkynes. Done. So when I have to speak about polymerization reaction, what actually is the definition? Let's see. So polymerization, polymer means poly means many, mer means unit. Polymerization means it's a process. So let us write the definition now. It is a polymerization is a process in which large number of a simple molecules combine under suitable one. Let us write the definition, then come back to the explanation. Suitable conditions to form a large molecule. Okay, we have written a lot of words in this. We will say large molecule. That is nothing but that large molecule is called macromolecule. Okay, so macromolecule, or this macromolecule is also called as polymer. Fine. So what have we this? We said process, polymerization is a process. Okay, this is a method where large number of simple molecules, small molecules, that is your monomers, that simple molecules are called monomers. So monomers, they combine together. So we need certain suitable conditions like temperature, pressure, catalyst, like that. So when these are provided, the small monomers, whatever are there, okay, so what do we require? We require conditions like temperature, we require conditions like catalyst, we require conditions like pressure. Then what will happen? These small monomers, they will combine together to form polymer. So this is called polymerization. This process is called polymerization. Okay, done. Now let's start seeing the examples of this. So when I speak about the polymerization reaction examples, the first most simple thing. Now let me take a list of this. Now I'm going to take the first example, the basic alkene. This is called what? Ethylene or ethene. Right? Let us write ethylene. Now what happens? Now to this ethylene, suppose if I'm introducing high temperature and I'm introducing pressure also. Okay. Then what happens? This double bond, whatever is there, this breaks up. And what will happen? This continues. One alkene combines with one more alkene combines with one more. Like that, monomers combine together and finally form a polymer. See here, this CH2 I'm writing here. This chain continues in this way. CH2, again this chain continues in this. So this is called polyethylene or polyethene. Done. So this is the first important type of polymer. So this is a monomer, this is a polymer. So ethylene or ethene is a monomer, polyethene or polyethylene is a polymer. Done. Let us take one more example. Suppose if I take this CH2 double bond CH, now CH3. Now how many carbons are there? 1, 2, 3. What is the name of this compound? Propene or propylene. Right. Now N, this is a monomer. Fine. Now you're creating the same, like in different high temperatures and pressure. Then what will happen? This double bond breaks here and this propagates. So CH2 is here. It becomes single bond because it is already broken to form a chain on either side. Then this is your CH. Now this is your CH3. Okay. Then what happens? Chain continues. We are writing N. N means it goes on continuously forms a chain. It forms a big macromolecule till it combines. It goes on forming. One monomer combines with the other. One monomer combines with the other, like that till they form a bigger or larger macromolecule. It's going to form a big chain. So this is what it is. Poly means many. Prop, it has come from prop, so it is called polypropylene. Done. Now third example, suppose if I take an example like CH2 double bond CH and CN. What is the name of this compound? N, monomer. For monomer you write N here. When it continues with the chain, you are going to write N here. So what is the name of this compound? This is called acrylonitrile. acrylonitrile. Done. Right, again some conditions. So as I said, when you supply high temperature and pressure, the bond breaks and it starts forming a polymer. So CH2 is here, it becomes single bond, CH, then CN is here. As I said, this continues and you need to write here N. Now what is the name of this compound? This is called Orlon. Orlon. Right. Now let us write one more example. Suppose if I take the fourth example as CH2 double bond CH and Cl. Okay, N. What is the name of this compound? This is vinyl group. Okay, vinyl. So vinyl chloride. Okay, this is vinyl chloride. Now same thing, I'm going to write, or I'm going to supply high temperature. I said no, under temperature, high temperature and pressure conditions and catalyst only, it's going to show the monomer, means monomer combined together to form polymer, isn't it? Right. So this bond breaks and how does it look? It looks CH2, this becomes single bond CH, and this is Cl here and N. What is the name of this compound? This is vinyl chloride. Now this is polyvinyl chloride. Polyvinyl chloride. So this is where your PVC pipes are made. This is called PVC. PVC pipes are made. I know you've already seen where we use it for this PVC pipes, or this particular material is used for making pipes. It is made for use of furniture, gaskets, your gaskets and everything. So we will see the uses also in just 2 to 3 minutes. Done. After that, suppose if I take one more example, now I'm going to take this compound CH2. Now this is one compound. Okay, right. So what is, again I have to use high temperature and pressure in the presence of a catalyst. Then automatically, okay, first we'll write the name of this compound. This is called styrene. This compound is called styrene. So there's a cleavage of the bond. In the presence of high temperature and pressure, there is a cleavage of this pi bond and the chain continues. You need to put 2 brackets like this. Your CH, C6H5 is still there, then single bond, because bond has broken to continue further propagation. So this becomes your CH2 and N. What is the name of this compound? This is styrene. This will become the polymer, that is polystyrene. Right, this is a compound. In this way, the monomers are getting converted to polymers. So this is called polymerization. Let's see one more example. Suppose if I take the 6th one. Now CF2 double bond CF2. What is the name of this? I need to write N. This is called tetrafluoro. Okay, 4 fluorines. It is tetrafluoroethene. So again I'm going to use high temperature pressure, then this is the catalyst. This bond breaks up and you need to put 2 brackets, right? So first is CF2, single bond CF2, and N is here. What is this? This is called Teflon, or it's also called PTFE, polytetrafluoroethene. Okay, Teflon. Where are we using this Teflon? We are using Teflon in your non-stick cookwares, isn't it? Where they form a coating on the surface of the non-stick thing, right? So these are the different processes. This is the different methods how to convert monomers into polymers. Now let us see the applications. Let us see certain uses. So we have done polythene. First of all, when I take polythene, so polythene, where is it used? It's used, basically you've seen it in day-to-day life. Everywhere it is polythene only. It is used to make plastic bags. Where are we using? We are using to make saline bottles, isn't it? What else do we have? We can use it for plastic gloves also. Like that, you can learn different examples. I'm just writing few only. Right. After that, if I take polypropylene, or we have written, isn't it? In the first example, when I take polypropylene, which we have used already prepared, I can use polypropylene for making food containers. We get this plastic containers, isn't it? They say that you can use it for long standing. You can store your cereals, rice, grains, pulses and everything there. Polypropylene is also used to make furniture, right? Then after that, polypropylene is used to make cosmetics, the outer covering of your lipsticks, Vaseline bottles and all these. Okay, it is also used in medical industry, medicinal industry, or medical industries, right? Just to make bottles, syringes and all these. After that, suppose if I take Orlon. Okay, Orlon, what is example? Orlon is used as in fibers, in your cloth fibers, where it is used. Fibers means where we use the fibers for making sweaters. It is used to make gloves. It is used to make mats. Okay, all this Orlon is used as a fiber, right? And the next, Suppose if I have to take PVC pipe, we have made PVC polyvinyl chloride, right? It is used, where did I say? It is used to make your car bumpers. Okay, you all know what a bumpers, car bumpers, isn't it? Right, it is used to make gaskets. It is used to make furniture trimming. See, whenever you have the furniture where you have to seal the furniture so that it is not hurting somebody, the furniture trimming also is done by PVC. Then after that, if I have to take styrene basically is used in food packing. I'm just picking up 3 of food packing. Then it is used to make toys. Okay, it is very, very flexible to make toys. Flexible toys. You give it to flexible toys. Small children, when they try to use the toother or something, very flexible thing, which it is easy to handle. So flexible toys, such things, styrene is used. Suppose if I have to take PTFE, polytetrafluoroethene, which we have prepared. Okay, we have prepared from tetrafluoroethene. So this PTFE, polytetrafluoroethene, it is used for making cooking pans. Okay, and it is used in making cables. Then it is also used to transfer high, like if I have to transfer high, it is used to transfer highly sensitive fluids. So these things all I can use it. I can use PTFE for doing that. So these are the different applications. These are the different examples of polymerization reaction, students. So I've covered the examples. I have shown you what are the monomers. I have shown you what are the polymers and their applications. So thank you for watching. I'll meet you again in the next video. That is your oxidation reactions of alkenes. Very, very important reactions. Let's meet again. Thank you for watching. So welcome, students, to one more session of your hydrocarbons chapter. Now, we have already completed different types of reactions of alkenes. We have studied the addition reactions. We have studied the allylic substitution reactions. Then we have studied combustion reactions, oxidation reactions. Now, we'll be studying the ozonolysis reactions of alkenes. So the same thing will be the basic idea of ozonolysis. We'll be studying alkynes also, right? So what actually is ozonolysis? Ozonolysis is nothing but, just let us write the definition first. So it is nothing but an oxidatively cleaving alkenes, okay, or as I said, alkynes also. So it is oxidatively cleaving alkynes. With what am I cleaving alkynes? I'm going to use O3. Okay, ozone molecule is O3, isn't it? What is O3? It is a reactive allotrope of oxygen. Okay, so what am I going to do? I'm going to explain you step by step. I said we are going to, ozonolysis is a process of reactive cleaving of alkenes. Okay, the oxidatively cleaving of alkenes or alkynes using ozone, that is allotrope of oxygen. You know what allotropes is, isn't it? The same so existing in 2 or more forms. Carbon, for carbon, Dryman is an allotrope, graphite is an allotrope, Buckminster fullerene is an allotrope, right? So ozone also, like naturally also we'll discuss about that topic also. So ozonolysis occurs naturally. That is what is important. Okay, I'll be teaching that process also very soon, right? So how does this occur? Suppose if I have to take, let me take an example and explain you. So now this is an alkene. Okay, C double bond C is an alkene. Now I'm going to add ozone to this O3 molecule, right? How does it go and add? Just see, there is a cleavage of this bond here, right? This bond, this pi bond, and see here, see carbon, carbon. These 2 bonds are here, this also is here. These 2 bonds are here, this also is here. Now this oxygen molecule, it attaches to this around the double bond. 1 oxygen here, 1 more oxygen here, 1. Then this is 1 more oxygen, this. So 1, 2, 3, 3 oxygens over. Now fill in the electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now for this 1, 2, 3, 4, 5, 6, 7, 8. For this 1, 2, 3, 4. So 5, 6, 7, 8. Now this particular thing further it forms 2 different products. So the first product is C double bond O. There is a cleavage of the bond here in this way, and this here also, and it forms C double bond O. See here, C double bond O, right? So 1, 2, 3, 4, 1 product, and 1 more O. 1, 2, 3, 4. This is the product. Two products are formed. What are these products? These are called carbonyl compounds. Okay, carbonyl compounds or carbonyl products. Okay, let us see in detail what are there here for both. Let us see the reaction. Now, let me explain you the mechanism of ozonolysis. Then you'll clearly understand what actually it is. So, let me take a fresh page. Right. So, now we will learn the mechanism. As I said, we will see where is it adding, how is it adding around the double bond. So let us write mechanism of ozonolysis reaction. So understand carefully, students. Let me underline this start. First of all, this is called electrophilic addition of ozone. So this is called EAR, electrophilic addition reactions of O3. Now in the first step, let me take carbon double bond carbon. Now this is your alkene. Now ozone molecule should add to this. So ozone structure is O, single bond O, double bond O, because this is resonating and this keeps resonating in this direction, here and here. Correct? Right. So now fill in 1, 2, 3, 4, 5, 6, 7, 8. Now for this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Over. Right. So the first important thing is, there is, when ozone adds to this molecule, there is a cleavage of this bond, isn't it? Right. So this pair of this particular electron is shifted to this when this bond is broken, and this one is shifted to this. First important thing before that, what will happen? This bond, whatever is there, is going to shift towards this oxygen. That should happen first, not this. This should happen second. First, there is shift of pi bond here. So 1, 2, 3, 4, 5, 6, 7, 8. When the shift of pi bond, plus sign, when this becomes minus, right? Once this shifts. So once again, step 1, there is shift of pi bond, this becomes plus and this becomes minus. So this electron is shared with this carbon. How does this look? This looks like this. Carbon, 2 bonds are here, it is bonded to this. 1 more carbon, 2 bonds are here, it is bonded to this. 1 more oxygen, isn't it? Right. Now let's fill oxygens. 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen. Now for this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. For this oxygen, 1, 2, 3, 4, 6, 7, 8. This is done. Fine. So now this compound is called mole ozonide or mole ozonide. Okay. Done. So just see, observe carefully. This bond from here shifts. From here, this bond shifts. So this is shifting here, this is shifting here. Then we are going to get 2 products, right? 2 products. What are the first product, right? So here, when this is shifting in this direction, carbon double bond O plus, this whole thing has shifted here. So this becomes, this whole thing is here only. This is attached like this only, isn't it? So you have carbon present with the bonds, bond oxygen, single bond oxygen. Now fill in 1, 2, 3, 4, 5, 6, 7, 8. So positive sign for this. 1, 2, 3, 4, 5, 6, 7, 8. Negative sign. Right. So this is called carbonyl oxide. Carbonyl oxide. In the next step, what happens? Right. So this is I think why should I should not write plus here. This part is broken in this way. This whole part is broken in this way. Done. Okay. I'm sorry. This should not be plus. This is carbonyl oxide. Now in the second step, what happens? Right. So now let us write step 2. You have this C double bond O in the earlier step, and this one carbonyl oxide plus and minus. This bond from here is going to shift to this carbon. This oxygen from here is going to shift to this carbon. Both are in equilibrium, and finally you get a mole ozonide. This is your ozonide. Okay, this is your, from mole ozonide you're going to get ozonoid. This is your basic thing. This is how it forms. This is the formation of ozonoid in the reaction. Okay. This is the mechanism of ozonolysis. Now let me take the same mechanism and apply it in different examples. Suppose if I take this example, like different examples are stated, like you have in your textbook also, like different thing. You will try all the possible combinations and just write. So first example is, if I take this alkene in the exam, suppose this alkene is given to you in this way. Now you have to add ozone. I told you, isn't it? So ozone. So we call this as reductive workup. Reductive workup. So as I told you, it forms mol ozonide. After mol ozonide, it's going to form ozonide. So during this process, there is a cleavage of the bond, right? And you get two products. Same, the procedure is the same. I'm directly writing the products. That's it. Go back to the mechanism, understand the mechanism, and then come back and write the product. CH and double bond. See here. This part is here. This part is here. Okay, done, isn't it? So this is how you have to write. Suppose if I take, let me take number is as first example. Now I'll take one more example. Carbon here. Okay, C double bond C, CH3, CH3, oxygen. Again, a reductive workup, same thing. Now see, this is broken and this you will get two products. Oxygen plus bond O. Done. Now one more example we'll try. Third example, suppose if I have an alkene like this, one methyl group here, the C3H7 here, the chain is increasing basically, C3H7 here. Now I'm going to add ozone to this. Again same reductive workup. So again this will break in this direction, this will also break. What do I get? CH3, CH, double bond O, and C3H7 carbon, C3H7 double bond O. Hope you're understanding, students. Both see here, this one and both I'm writing in this direction, both the things I'm just breaking and writing two different products. Let us take one more example and see. Suppose if I have this compound, okay, this is given to you, you need to do the ozonolysis. Again same thing, reductive workup. What will happen? Let's see the products which we are going to get. Just see, I'm opening up the chain now. I get CH3 here. This one is here. So next one, it's going to add 1, 2, 3, 4, 5. Oh, CH3. See here, now count 1, 2, 3, 4, 5, 6, 7, and this is the one. Okay, now 6, 7, 8. Right, over, isn't it? So this is the product. Now let's do one more. Suppose, let us take the fifth example. Suppose this compound is given to me. I need to do ozonolysis process. So this in the presence of O3, and next we are also going to use one more, that is zinc in the presence of water. What is the use of this? This zinc helps in the process of reduction. First it will form ozonide, then it undergo further reduction. That's why this is called reductive ozonolysis, because we are using a reducing agent here. So again, I'll break the bond here. I get two products. One product is CH3CH2 aldehyde, and one more product I get is this. So please remember, I am just showing directly now. I've shown the mechanism earlier. Watch the mechanism, practice the mechanism, see how mol ozonide is formed and then ozonoid is formed, and then try to apply that in this example. And yes, so now one more example. Suppose this alkene is given to you. What is this alkene? This alkene, that is named this 1, 2, 3, 4, 5 pent, isn't it? So which pent it is? Pent-2-ene, right? So when I take this pent-2-ene, again I have first condition ozonolysis, second condition reductive ozonolysis in the presence of zinc and water. Again I get two products. Okay, let me write that down. Okay, I think this is confusing. Let me draw a line for this. We will get two products. I am holding this here, this particular bond, both the sides oxygen adds. So what do you get? CH3, CH2, CHO. Okay, that is double bond O plus O. This isn't it? This here. O. This is CH, CH3. So this is propanol. This is ethanol. Isn't it? Two carbons. Right. Let us do one more example and see. Suppose if I am taking the 7th example. So CH3. Now CH. This is alkene. Now here, yeah. Now I have a substituent here. The same process. Your teacher has asked you to do ozonolysis. You have in the presence of zinc, that is reductive ozonolysis. So what product? Again, you should hold your this one here, break it in the center. This will be one oxygen and this will be the other oxygen. So CH3, CHO plus CH3, again CH3, both are linked to carbon and C double bond O. Now here we have got acetaldehyde, and what is this? This is 3 carbon propanone ketone, one aldehyde and one ketone. So these are the different examples of ozonolysis, students. So I have done how many examples? Let me cross check again. First I have done 1, 2, right, 3, 4, 5, 6 and 7 examples I have done for ozonolysis, right. Last but not the least, let us write the uses of ozonolysis. So basically it will help us to locate uses of ozonolysis reaction. Ozonolysis. Ozone means addition of ozone by lysing it, by breaking it. So ozonolysis reaction, it helps us in locating position of double bond. Position of double bond in alkene. And what else can be used? It can be used in explaining the structure of alkene. Elucidation means that it like help in explaining the structure of alkene. In elucidation of structure of alkene. So these are the different things. So once again, let us revise what we did for ozonolysis. Let me take back my papers. So whenever ozonolysis reaction is given to you, just see students, I'll just come back again. Whenever ozonolysis is given, you have to write the definition of that. After writing the definition of that, you need to tell your teacher, like the examiner, whoever is there. So you have to see what actually happens in ozonolysis. After that, you will be explaining the mechanism of that. So here, mechanism, I think, okay, examples first I have taught you. Examples also I have taught you, one after the other. And before that, I have taught you something called mechanism. This is very important. So you will show the mechanism first from the attack of ozone molecule forming ozonide. From ozonide, it's going to form carbonyl oxide, and then finally that carbonyl oxide combines with the given group and then finally forms ozonide. Then I have taken how many examples? I have taken 1, 2 here. I have taken 3, 4, then 5, 6 and 7 examples. After that, finally I have explained you the uses of ozonolysis. So this is how we are going to explain a reaction, students. Thank you for watching. Let me meet you again with the next type of reaction. Right. So welcome students to one more session of your alkene reaction. Right. So now we are going to study the important reaction of alkene, that is alkene plus NBS reaction. Okay, what is NBS? NBS stands for N. Okay, bromo succinimide. Okay, N-bromosuccinimide is NBS. So basically, what is NBS? Where are we using? NBS is a chemical reagent. Okay, where am I going to use in chemistry? Let us see first. This chemical reagent, basically, I'm going to use wherever there is radical substitution reactions. The free radical substitution reaction, wherever it is there, I'm going to use NBS. I can use NBS in electrophilic addition reactions. I can use NBS in electrophilic substitution reactions. So what is the basic idea is, NBS is a convenient source. It is a convenient source of bromine free, supplying bromine free radical. So wherever we require or the formation of bromine free radical, I'll be using NBS for giving us that bromine free radical. So what is the formula of NBS? So basically just see, NBS looks like this. CH2 linked to one more CH2, then CO, again here CO, NBr. This is NBS, N-bromosuccinimide. This is your complex. So here let me take one example and understand how does it go and add. So now you know NBS is used for what. So if I have to start with certain example, here I am going to take unsymmetrical alkene, right? CH, single bond, CH2. CH, this is your CH3, done. Right. So now I'm going to add NBS. So NBS, we've already learned the formula. CH2, CO is here, CO, N and Br. Now this whole reaction occurs in the presence of H nu. I said free radical. Let us see how it forms a free radical in the mechanism also. So here this H nu, in the presence of light only this occurs. So what product do we get? Here first important thing, it will go and add this bromine. I said NBS is a source of bromine free radical. This bromine goes and adds or attacks this allylic hydrogen, means allylic carbon containing hydrogen, allylic hydrogen. This. So what product do I get? I get CH2, double bond CH, single bond CH2 Br. Now what will happen to this? Right? There is one hydrogen, isn't it? This hydrogen comes and adds to this nitrogen. So this hydrogen, let us put in this way, this hydrogen comes and adds to this. This becomes CH2 joined to this CO, CO and NH. So what is this name of this compound? This is nothing but succinimide. Succinimide. This is N-bromosuccinimide and this is succinimide. Now let us take one more example and let's take again, suppose if I have this compound. Well, let me take one more example too. I have a compound. Okay, this is, let me join. Now what is this compound? This is a cyclo group. Cyclo, how many are there? 1, 2, 3, 4, 5, 6. Okay, right. So this is cyclohexene. Now I'm going to use NBS, and whenever you have NBS, H nu is compulsory. Okay, H nu or heat also not a problem. So what did I say? I said it is a source of bromine supply, isn't it? Just see here. The bromine is going to attach to the position where means this is a double bond, leave this bond and then it will join here. Remember that. Once again, double bond, leave this bond and it's going, the bromine is going to join in which position? Here it is going to join. You should not write adjacent to that. We will see the mechanism, then you will understand why it is like that. So here this is a double bond, this is where. So what product do I get? I am going to get in this way, double bond, this is where your bromine adds and HBr is out. Along with that succinimide, I said it has to come out, NH, that H goes and adds to this. So NH is here, CO, this is also CO, and means that particular thing this way. So this is your succinimide. Succinimide is out. Now let us take one more example. Suppose if I take example 3. Now I have in my exam, my teacher has given me this. Okay, right, like this. Now there is one substituent here. Now NBS, H nu or heat. What product do I get? I said again, this is your double bond. This is where it attaches here. One bond you should leave. See here, this is double bond, you have left one bond, then added. Here also, this is the double bond, you leave one bond and then add. What product do I get? I get a product like this. HBr is out because that hydrogen comes out with this, and as usual, plus this whole compound, that is succinimide is out. Succinimide, okay, I've written the spelling wrong. Succinimide is out. This is the product. Right, students? Now, so remember, you need to leave one bond and join. Now let us see the mechanism of addition of N-bromosuccinimide. So when I have to speak about, okay, let us write the heading, mechanism for addition of NBS, N-bromosuccinimide. Now let us underline this mechanism word. Done. One carbon away from the double bond. Remember that always. Let us write, where will the bromine? Okay, bromine adds at one carbon away from double bond. This is what is a concept, correct? Remember, right? Let us see the mechanism first. So here NBS, whenever I said it is a source of, or it supplies bromine free radical, I said, isn't it? That free radical formation you have to show. So here first step, NBS combines with HBr. Okay, what does it do? This particular thing, bromine is out. Okay, when it combines, that NBS when it combines with HBr, bromine is out. So after that bromine is out, this bromine now starts, see here, this bromine is linked like this, and let us write 1 2 3 4 5 6. Here also 1 2 3 4 5 6. Now what happens here? Yes, this, I hope you understand this arrow, students. There's a break, it cleaves there in the presence of H nu and to form two bromine free radicals. Okay, 1 2, now 3 4. This is your free radical. Done. Yes, very important. See here, there is a cleavage of the bond, homolytic cleavage of the bond, because both are similar. Now there is a formation of, this is what, bromine. There are two bromine, so two bromine free radical is formed. This is where it is the supply, that supply of that. Now suppose if I take one example, right, I am going to take this example, then what happens here? This is your cyclohexene. Now there is one hydrogen here, so this is, there is one bond here, also there is one electron, this is one electron. Now this bromine free radical attacks this 1 2 3 4 5 6. This is your bromine free radical. This bromine free radical attacks this, because you should leave this double bond one carbon away. After this double bond, there's one bond here. This is where it attacks, isn't it? When this attacks, what, how does it look? First, your free radical, this becomes a free radical, HBr is out, correct? Because this comes out with this Br, one more, and HBr. Now this exists in resonance with one more structure, that is this and free radical. These two are resonating structures. Fine. So now what will happen in the final stage? Okay, let me take the same page. In the final stage, what will happen? Your cyclohexene free radical combines. There is one more bromine free radical here, isn't it? See here, one I have taken here. I am going to take the second bromine free radical here. So 1 2 3 4 5 6. You need to mention this careful. Right, so this free radical combines, this one combines with this. What do you get? This is a second bromine free radical. Second bromine free radical. So where does it form a bond now? Right, one, this left, and this is where it attacks. This is how it attacks. That's why I said one bond left, then only bromine reaction. Bromine goes and adds. So this is your NBS reaction with alkene, students. Hope the concept is clear, mechanism is clear. Any doubts, please let me know in the comment section. Thank you for watching, students. I'll meet you again with the next type of reaction of alkenes. Very important reaction, that is ozonolysis reaction. Welcome back, students, to one more session of your allylic substitution reactions of alkenes. So till now we have studied the oxidation reactions of alkenes, we have studied polymerization reactions, we have studied addition reactions. Now we'll be studying the substitution reactions. So what actually is allylic means? Let us see. Suppose there is in one particular unsymmetrical alkene, if the halogen concentration is very low, then it undergoes allylic substitution reactions. So why does it undergo? So first of all, you should know what is allyl group, isn't it? Okay, let us write. So let us take one example. So CH3, this is CH2, 1 2 3. Okay, now this is your allylic group. This immediately both are attached to the double bond. Now when does this allylic substitution occur? Allylic substitution basically occurs, once again I'm telling, when the halogen concentration is low. So this is your halogen. If the concentration is low, then what will happen? The alkenes, whatever which we have, this alkenes containing allylic hydrogens, this is your allylic hydrogens, they are going to undergo substitution reactions at the allylic position. They are going to undergo simple this allylic alkene. So once again, whenever the concentration of the halogens is less, the alkenes at the allylic position, or the allylic hydrogen, they are going to undergo this allylic hydrogen. This is your allylic hydrogen. This is the double bond adjacent, and this is your allylic hydrogen. This undergoes substitution reactions rather than addition reactions of the double bond. So hope it is concept is clear, students. So whenever the concentration is less, immediately the allylic hydrogen, instead of addition reaction, this addition reaction, it prefers substitution reactions. So that is called allylic substitution. Let's start. What product? I'm going to heat the reaction, then I'm going to get a substitute product. Here this hydrogen is replaced, I get X. Okay, this is one more hydrogen, this is C, double bond C. This whole thing will be like that only. So halogen can be chlorine or bromine, right? So this is called allylic substitution reactions. Now let's start taking an example for this. In allylic substitution reactions, hope now you've understood why does this undergo substitution. Suppose if I take the first example, now I'm going to take C double bond C. Okay, now this is CH3, this is H, this is CH2. What is the name of this compound? This is propene or propylene. Done. Now I'm going to add chlorine to this. I'm going to use 600 degrees centigrade to this. Now I said what will happen? Here the concentration of halogen is less. So where will it go and replace? It will go and replace at this hydrogen. This is your allylic hydrogen here. So you get a product Cl, CH2, CH, double bond, CH2. So this is called allyl chloride. Allyl chloride. Okay, count 2 plus 2, 4. 1, 2, 3, 4. 2, 3, 4. This. Now this is your allyl chloride and substituted, isn't it? One hydrogen got substituted. Done. Suppose if I take one more example. Here I am going to take here, just see here, CH3. Now what happened? The double bond has shifted here, and this is a allylic hydrogen. So I'm going to add bromine. At what temperature? I'm going to add 800 Kelvin. Okay, did I write centigrade? Okay, that also please change it to Kelvin. Now this bromine concentration is less, concentration is low. Then what will happen? It will go and substitute this hydrogen. HBr is out. That is understood. What product do I get? CH2 double bond CH. CH2Br. This is your this. What is this compound? The name is IUPAC is 3-bromo. 1, 2, 3. 1, 2, 3. 3-bromo. Prop-1-ene. Isn't it? Yes. So this is called allyl bromide. Allyl bromide. Right. So allyl bromide as a concept. So this is how we are going to learn the allylic substitution reactions of alkenes. Now in my previous in my next video, like what I was trying, I in the previous video I've explained oxidation, then I've explained now substitution reactions. Now in my next video I'll be teaching you what happens when alkene is added to NBS. That is, NBS is nothing but N-bromosuccinamide. Very, very important reaction of alkenes. N-bromosuccinamide. Here, bromine directly we have given. But we are going to see what is the reaction mechanism when N-bromosuccinamide is added to alkene also. We will see what is the reaction mechanism, what happens in that. So let me come back and meet you with NBS reaction plus alkene in my next video. Thank you for watching. Right, so welcome back students. The next to the next method of preparation of alkynes. So in the previous video we have watched the industrial method. In that we have seen industrial method as well as lab method, right? I've picked up old method and new method, so please practice those reactions, students. I think you're following me every day. Unless until you study on the daily basis organic chemistry, it looks easy when you understand, but you need to study on daily basis, then only it will become, you will just get grip on the subject, right? So today the topic which I'm going to teach you is alkyl substitution in alkynes. That means what am I going to do? I'm going to prepare higher alkynes, right? So higher alkynes I'll be preparing from lower alkynes. So this is the concept. Basic concept is preparation of higher alkynes from lower alkynes. Done. Now what are we going to do? Basically, suppose, let us see one mechanism, then go back to the reactions. Now I have an alkyne, right? Now this alkyne, now I'm going to treat it with either NaNH2 or sodium. This is sodium amide or this is Na, metal. Then what happens? This is the terminal hydrogen. isn't it? Right. So this is replaced by sodium. So what do we get? R, C, triple bond C, and this is minus, and this is Na plus. Now apart from that, we have NH3 or half hydrogen, which is evolved out. That. Now this particular thing, this is there, isn't it? Now I'm going to take this. I'm just showing you the mechanism so that we can further take you to the examples. Now here to this particular thing, we are going to add a primary alkyl halide. Okay, primary alkyl halide. So I'm going to take primary, right? So alkyl group, this is primary, this is CH2X, isn't it? Right. Now the C minus attacks this bond. Then what happens when this attacks? There's a cleavage of the bond here, isn't it? This becomes R, C, and your triple bond C, CH2, R. And X minus is out. So which type of mechanism is that? You have both there are two reactant molecules participating. So this is nothing but SN2, it is following SN2 mechanism, isn't it? Right. So now let us start with the concept. So please understand, first this is the formation of what is this? What is the name of this compound? It is called, now because there are two carbons, isn't it? Now I name this compound as sodium ethanide. Okay, sodium ethanide. Let us write that. It is sodium. Here I've taken R. Generally, if I don't have R, if there's only one hydrogen, then I can call it a sodium ethanide. So now there is no hydrogen specifically, so I'm going to write sodium alkanide. Okay, sodium alkanide. Done. Right. Now with this mechanism, let us take certain examples and see. First, let me take this fresh page. Suppose if I take acetylene, right? So I am taking acetylene. Now I'm going to, let me write this as example 1. What am I going to do? I'm going to introduce NaNH2, sodium amide, in the presence of liquid ammonia. Okay, so this at minus 33 degree centigrade. Then what happens? This hydrogen is replaced by this sodium. I'm going to get sodium, and this is Na. Right. Then now what we say, we just said this particular thing, after sodium attacks this, what do we get? We get, name of this is sodium ethanide. Now what else is left out? This is attacked, and this hydrogen is, yes, accepted by this, and we get ammonia. Now, so now suppose if I take the same sodium acetylide or ethanide. So this is highly basic, isn't it? Isn't it? So this competes elimination, highly basic part. So it competes elimination, and that elimination part is more than this. So the products of such elimination reactions are, we very well know, are an alkene from the alkyl halide and an alkyne. That is what is the concept. Now what happens? This to this acetylide, I'm going to introduce C4H9Br. Right? Fine. So what is the C4? It is nothing but butyl bromide. Now what happens? Just see here, observe carefully. The product form is CH3, CH2 taken thrice, C triple bond CH. So the answer is 1-hexyne 3 4 5 6 carbons. So triple bond in the first position, 1-hexyne. Fine. So here how many do we have? We have 1 2 plus 4 6. So this is how higher alkynes are prepared from lower alkynes, that is acetylene. Right? Fine. Suppose if I have, let me see one more. If I have to take the next example, the same thing, let me introduce one more alkyl halide. Now again I am taking, let me take this as example 2. Here I am adding the same thing again, 2 sodium amides, then liquid ammonia, then minus 33 degrees centigrade. Now to the same thing further, I am going to add C3H7Br. What is C3H7Br? It is propyl bromide. So 2 moles. Now finally when I add, this is 3, this is 4, this is 5. But what did I do? I have taken 2 moles here. Isn't it? 2 I have taken. That means it becomes double. it becomes 3 2s are 6, isn't it? 3 2s are 6, 7 8. That means I'll get octane. So what is the product form? CH3, CH2, CH2, C, triple bond, C, CH2, CH2, CH3. Let us count. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So which octane is this? This is 1, this is 2, this is 3, this is 4. This is 5, this is 6, this is 7, 8. So this is 4 octane. Let us come back and see how do we get. Here I have 2 lower alkynes, 2. Fine. After that, it's going to form sodium acetylide or ethanite. Then I've introduced this. This is propyl bromide. But I've introduced 2 moles of this, which becomes 3 2s are 6. 6 plus 2, 7, 8. This is completely the whole thing comes out and this forms. And NaBr is already there. NaBr, that is already there, but I'm showing you the conversion of lower alkynes to higher alkynes. So, but remember one thing, that is highly basic. Acetylide is highly basic, so it will prefer elimination reaction. That's the reason we are getting the products what we have seen. So this is a reaction with sodium amide, students. So if your teacher is giving you any example, like suppose if your teacher is giving you any other lower alkyne, just take this, whichever chain it is you are adding, combine the whole thing and write the product. So this is the reaction. Thank you for watching, students. Let me meet you again with the next preparation of alkyne, that is the halofoam reaction. Yes. Welcome, students, to the next session of your hydrocarbon chapter. We're almost coming to the end of the chapter. I'm just left with the chemical properties of alkynes, and then I'll be jumping into the benzene compound. There we'll be studying about the different reactions of shown by benzene, aromaticity of benzene, resonance of benzene, right? Orbital diagram of benzene, right? So when I have to come back to alkynes chemical properties, what should I remember first? So basically, alkyne is a triple bonded compound, isn't it? Right? So alkynes are denoted by their triple bonded C, triple bond C. Right. Now why did I write this? Basically because of the presence of triple bond, that is, it has 1 sigma and 2 pi bonds. This is going to show a wide range of chemical properties. What are those? It's going to show addition reactions because of the presence of pi bond. It's going to and after addition reactions, it's again going to show oxidation reactions. It will also show polymerization reactions. As I told you, in alkenes, monomers getting converted to polymers. In addition reactions also, you have different types like addition of hydrogen. Then you have electrophilic addition reactions. Then you have nucleophilic addition reactions. And again, you have different subclasses in this. When I speak about oxidation, here we are going to learn oxidation in terms of combustion reactions. We are going to learn oxidation using K-4. We are going to learn oxidation, or we are going to learn under heading Ozonolysis. Under polymerization, I am going to teach you about cyclic polymerization and linear polymerization. Both we are going to see. Right? So done. So here with this basic information, let's start learning one after the other chemical properties. So I'll be starting with the first class of compounds, or first class of reactions, that is addition reactions. First, I'll be teaching you what are the products we get with hydrogen, what are the different electrophilic addition reactions, and what are the different nucleophilic addition reactions. Right. So let's start with the topic. The first topic, that is, as I said, we're going to start with the addition reactions of alkynes. Why are we doing? We're taking this because alkynes has 1 sigma and 2 pi bonds. Now, when I have to take an alkyne, right? Now I'm going to take an alkyne. Whenever you're adding hydrogen, I say addition reactions and then addition of hydrogen. So I say addition of hydrogen. What is that? That means whenever you are adding hydrogen, it is nothing but reduction. So for reduction, what do you require? You require reducing agent. What are the different reducing agents we use? We can use like Lindlar's catalyst. Palladium, Lindlar's CaCO3. So I did one video also on Lindlar's catalyst. So palladium in the presence of CaCO3, that is Lindlar's catalyst. Here I have to use, I also use poisons, right? So poisons, like what are poisons which I use? Sulfur, or I can use quinoline, These are the poisons which we use. Further, I'm going to use reducing agents, the next class of reducing agents like nickel or platinum, sorry, palladium, isn't it? So with these reducing agents, I can easily add hydrogen to an alkyne, right? Suppose, let me take one example and see. So these are the reducing agents which help in addition. Suppose if I take an alkyne, now I've taken an unsymmetrical alkyne in this way. Done. 3 plus 1, 4. For this carbon 4. For this 1. Now I have to add hydrogen, H and H. So what did I say? I said because of the presence of pi bond, it is undergoing addition reactions. There is a cleavage of the bond here. There is a cleavage of the bond here also. So here I'm going to write this catalyst here. I'm not just writing. I'll write just catalyst. So what product do we get when this breaks off? CH3 is there. C. Now this becomes double bond, right? Now one hydrogen adds to this CH, one more hydrogen adds to this becomes CH2. This is an alkene stage. We get alkene. So 3 plus 1, 4, 1, 2, 3, 4, 2 plus 2, 4. This is one type. Suppose if I take the second example. Let me take second example. Now I'm going to use nickel as a catalyst. So hydrogen, right? So now I'll be using either nickel or platinum or palladium, right, as a catalyst. Then simple, as I said, there is a cleavage of the bond. This hydrogen adds, one adds to this and one more adds to this. Correct? So what do I get? I get CH2, double bond CH2. Further, if I add hydrogen to this in the presence of a catalyst, then what will happen? This bond also is broken and I get alkane. So this is alkyne. On hydrogenation gives me alkene. Alkene on further hydrogenation gives me alkane. So using the catalyst which I have mentioned earlier. So this is your hydrogenation reaction, students. This is how we are converting higher alkynes or the alkynes to alkenes, alkenes to alkenes using the respective catalyst. Done? Yes. So now we'll be starting with the next type of reaction, that is electrophilic addition reactions, in my next video. Thank you for watching, students. Now today's session we're going to learn the preparations of alkynes, right? So we have completed the alkenes in alkenes chapter. Now let's start with preparations. So alkynes we've already discussed what are the different methods in the previous video. Now let us start with the first type of method, that is your industrial method of preparation of alkynes. So basically you have industrial method or you have lab method, like the electrolysis process. Let's go about with the preparation. So when I have to speak about the industrial method of preparation, so let's divide this. You have two types, as I said, industrial method of preparation of alkynes, as well as we also have a lab method, that is laboratory method. In that we'll be studying about a synthesis called Berthollet synthesis. Berthollet synthesis, okay? Yes, Berthollet synthesis. This was given by Pierre Berthollet, a French chemist. Done. So when I have to speak about the industrial method of preparation, so here basically there are two ways in this. In that we have the old method as well as a modern method. So when we speak about the old method of industrial preparation, first coke or carbon is taken. To this, what is added? Calcium oxide is added. Now what they're going to do, they're going to heat this mixture at 200 degrees centigrade. When they heat the mixture, suppose what am I preparing? I'm preparing alkyne. So the basic alkyne is what? Acetylene, isn't it? Right, I am trying to prepare this from this. So now carbon or coke, if I have to prepare, so let me take this as 3 carbons or 3 coke. Then what happens? Let's see here. When you heat this at 200 degrees centigrade, just carefully observe, there are 3 carbons, isn't it? Yes. Now this 3 carbon, first important thing, this carbon combines with this, okay? 1 carbon combines with this oxygen, comes out as carbon monoxide. Now how many are left? Here 2 are left, isn't it? So 2 carbons are left and 1 calcium is left, isn't it? This is already broken. So 2 carbons and 2 calciums. So 2 carbons, let us write as C2. Left over is calcium. This is called calcium carbide. Now this calcium carbide is further treated, or it is hydrolyzed, addition of water. Now just see here, this is broken here, done. This is also broken here. Now this calcium comes out with calcium hydroxide, right? Let's write that. It comes out as calcium hydroxide. Now what is left out? It is left, what is left here? Water, H2O, isn't it, right? So H2, C2H2. So C2H2. No, this is nothing but acetylene preparation. Simple, isn't it? So this is how it is prepared, the old method of preparation. So there is one more method of preparation, yeah, in the as industrial method. What they do, they're going to take coal, the same thing like coal. Then they're going to do hydrogenation, means they're going to add hydrogen and heat it. When they go and add hydrogen, what happens is during this process, this coal gets converted into hydrocarbons, that is acetylene. And whatever non-volatile salts are there, that will come out. Non-volatile salts, they deposit off, where only acetylene is left, we collect. There is also one more method of preparation of acetylene, that is from methane. So methane, that means this is when they ask you what is the conversion method of alkenes to alkynes, you can use this process. What do? They're going to take methane. Yes, just see here, methane formula is CH4. When they heat methane at 1500 degrees centigrade, yes, right. So now suppose if I take 2 moles of methane, isn't it? Now how many hydrogens are there? 4 2s are 8 hydrogens. How many carbons? 2, isn't it? Let us write that C2, right? Among 8 hydrogens, 6 will come out as hydrogen gas. This hydrogen gas, 6 will come out. So 3 2 is 6. How many are left out? Among 8, 6 are out. We are left out with only 2, isn't it? Now C2H2. So this is the preparation of acetylene. C2H2 is nothing but CH triple bond CH, isn't it? So this is the industrial method of preparation of acetylene. Now let's come back and see the lab method of preparation of acetylene, right? So again, here we have an old method as well as modern method. So when I have to speak about the old method of preparation of acetylene, first important thing, just see here, I'm going to take coke. I'm going to heat it with carbon or coke. I'm going to heat it with hydrogen, presence of hydrogen, right? Now, these two are introduced into means they are allowed to, an electric discharge is sent to this. Then what happens? Suppose if I take 2 coke here. So this becomes C2H2. This is the old method of preparation of C2H2 or acetylene. CH, this is your old method, very simplest method. Now, we have the modern method of preparation of acetylene. What do they do? Just now I said this, the methane. This is here in the industrial method. Here also we have methane. In the modern method, what they're going to do is they're again going to take methane, right? So, methane. This is allowed to combust. Okay, right. But here the temperature which they're going to take is 150 degrees centigrade. When they heat it at 150 degrees centigrade, but important thing is, here we're going to take 6 moles of methane. When you take 6 moles of methane, just simple, we very well know whenever methane is combusting, whenever it is heated in the presence of oxygen, what are the byproducts we get? We get carbon dioxide plus water. But here, what is happening, when they're controlling the temperature to 150 degrees, you get carbon dioxide plus hydrogen. Apart from that, you also get acetylene. Because CH4, no, they're dividing the CH4. So one product you get it as acetylene. Now let us balance. 6, isn't it? 6 4 is 24. So let us write 2 hydrogen here. 2. Okay, this is not carbon monoxide, it is carbon monoxide, right? It is 2 carbon monoxide and 10 hydrogens. Let me count. 10, so 10 2 is 20, 21, 22. Okay, 22, 23, 24. Yeah, right. And next comes carbon. Here 2 to 4, 5, 6 oxygens, 2 oxygens balanced, right? So these are the products when you take methane, and the limited means the temperature is limited to 150 degrees. So this is the first method of preparation of alkynes, old method, that is industrial method. Then further I have taken you to the further methods, then Berthollet synthesis, where you are taking the old method is this, and the modern method of getting the acetylene from methane is represented here. So thank you for watching, students. Now I'll show you in my next video. I'll be showing you how is alkyne prepared from, means you're preparing the lower alkynes from the higher alkynes, or you can also prepare the other way also. You can prepare higher alkynes from lower alkanes, both the ways. So in my next method, I'll be teaching you how to prepare, means how are we going to prepare higher alkynes from lower alkynes. Thank you for watching, students. So welcome back, students, to one more session of your alkyne chapter. So in the earlier video we have seen how is the addition reaction, that is addition of hydrogen in the presence of Linder's catalyst, addition of hydrogen in the presence of nickel, platinum, palladium, isn't it? Right, now let us come back to the next concept, that is electrophilic addition reactions of alkynes. Right, so in electrophilic addition reactions of alkynes, I'll be showing different types of electrophiles, that is addition of, if I have to speak, addition of Cl2, right, and in the presence of inert solvent, that is carbon tetrachloride. I'll be showing the addition of an electrophile, that is like if I take water or HX, let us take HX. In this HX, I'll be showing you how is the addition of the bromine and the hydrogen around the double bond, right. Then after that, I'll be showing the addition of HOCl, hypochlorous acid also. Right. So let us start with the first thing, that is addition of chlorine in the presence of, as an electrophile, in the presence of inert solvent, right. Suppose let us write the heading as addition of chlorine. What should you remember here? First important thing is this particular, now I'm taking an acetylene, okay, that is where we are showing. Acetylene has 1 sigma and 2 pi bonds. Now what are we going to do? I have to add chlorine around the double bond or around the triple bond. So I'm adding chlorine, 1 Cl here, 1 Cl. For this I'm using an inert solvent. Now see, how many are there? 2 terminal hydrogens are there. This is one acidic hydrogen, this is also one more acidic hydrogen, 2 terminal. So one chlorine goes and replaces this hydrogen, and one more chlorine goes and replaces this hydrogen. Done? Yes, but what is important here? Replacing hydrogen is important or breaking the bond is important? Here, whenever you're saying addition reactions, your concept should be more, you should have more concentration in breaking the pi bond, this pi bond. And once the bond is broken, you can add chlorines on either side, right? So there is a cleavage of the bond here, 1 chlorine with Cl. This is where most of the students do mistake. That's why I'm given both the options. So what is the name of this compound? This is 1,2-dichloro. See here, 1,2-dichloro. What is the name of this compound? Ethene. That is one chlorine. Suppose if I take 2 chlorines here, I'm taking the same acetylene, okay, and here I'm introducing 2 chlorines. How is this? Like this, 2 Cl2. So total are again inert solvent, so 4 are there. When 4 are there, what will happen? This bond is broken, isn't it? First bond is broken, 2 Cls are added. Second bond is broken, 2 Cls are added. So you get compound Cl2, HC, okay, CHCl2. Okay, let me write the other way also. You can write like this also. This is Cl2, CHCl2. Both are the same. Like I just wrote. What is the name of this compound now? Hydrogen is still existing, but the bond formed here, it has become a single bond, isn't it? Right. So name this compound 1,1, 1,1, 2,2, 2,2, tetrachloroethane, isn't it? This is the compound. So this is done with the first one. So remember, addition reactions in the presence of an electrophile, in the presence of an inert solvent, where the pi bond is broken and they are adding on either ends. Further, suppose if you take more concentration of the electrophile, further the bond is broken. Here it was alkene, here it has become alkane. This is your reaction, right? So hope students it is clear. Now let's come back to the next type of addition reactions of, that is your electrophilic addition reaction, that is addition of HX, right? So where have we studied this HX? We have studied HX in addition of HX in Markovnikov rule, isn't it? You remember in alkenes I have taught you Markovnikov addition. Now let's see how is this HX added. So when I take addition of HX, hydrogen halide, done. So this X can be here, it can be Cl, it can be Br, it can be I also, done. So anything, so it can be HCl, it can be HBr, it can be HI also. But what is important here? In alkyne molecules, 2 molecules, means here there is 1 sigma and 2 pi bonds, right? So whenever they're forming, Yes, remember, whenever you're adding HBr or HCl or this one to the around the triple bond, what are you going to get? You're going to get gem halides. Remember that. You will be getting the final product as gem halides. I am writing that. The final product, you will see what are gem halides. Final product is gem halides. You should remember this. So, gem halides means what? That means vicinal means if the halogen atom are present in two separate carbon atoms. Gem halide means if the halogen atom are present in the same carbon. Let's see what it is. Let me take an example. First example which I am going to take is, see here, I am going to take an alkyne in this way. Now, I am going to add HCl to this slow reaction. So this pi bond breaks up and I'm going to get C double bond C because this is broken up right now, right? 2, 1, 2, 3, 4. See here. Now what do we have? This H is there, isn't it? Right? H and Cl also should add. So C2H5 here and your Cl is here. One hydrogen is already there, one more hydrogen. Right? Now, after this, what is still the product is not formed, we'll just further do. Now again HCl is introduced. So it's very slow. Further this goes and adds, but here you have to be careful. I said the final product is gem halides, isn't it? Now there is a cleavage of the bond here. There is still a double bond. This also breaks up. And what do I get? I get C single bond. Observe carefully. 1 hydrogen, 2 hydrogens, 3 hydrogens here. This goes and adds here, and Cl goes and adds here. So 1, 2, 3. C2H5 here, Cl here, Cl here. Now see here. This group, halogen is present in the same carbon, isn't it? So now this is called gem halide. Gem dihalide or gem dihalide. So this is what I mentioned about. Whenever you are adding HX around the triple bond, there is a formation of geminal halides or gem halides, where both the halogens are present in the same carbon atom. Right, now let us do one more reaction. Suppose if I take this is, let me take this as example 2. Suppose if I take this alkyne. Okay. Now I am introducing bromine. The reaction is slow. So this triple bond breaks up. This bromine goes and adds around this one, C double bond C. Now let us make. So one way we have C2H5, right? So one bromine adds here, one more bromine adds here, and this is hydrogen. Further, there is still a double bond. I can further break it. So again, I'm introducing bromine, and the reaction is slow. Now I said it's going to form which one? Gem dihalide. So this bond also breaks up and it becomes C single bond C. Now you have to be careful. 1, 2, 3, 4, 5, 6. This your C2H5. C2H5 is here only. This hydrogen also is here. Now there are 2 bromines. One Br is here. There is one more bromine also here. Now still I added 2 more bromines. So that bromine adds here, this bromine adds here. Isn't it? So again it has formed, see, as I said, it has formed gem halides. Bromine is present in the same carbon, gem. Suppose if I take one more example, let me take one more example, example 3. If I take acetylene, now I am introducing iodine slow. There is a triple bond, this breaks up and you can get C double bond C, H here, H here, one I adds here, one more I adds here. Okay, yes, so this reaction stops here only, it will not proceed further. Now let us take Hope the concept is clear. Let me take one more example for you all. That is acetylene. I've taken 3 combinations. I've taken acetylene. I've taken this one also. Like let me take example of acetylene with HBr and show you. Let me go with the 4th example. Suppose if I take ethane, again the same acetylene, I'm going to introduce HBr. HCl I've used, HBr also used, but acetylene I have not used. Now what happens? I said this is going to, this bond breaks up, becomes C double bond C, and this joins in this way. This is H here, this is Br here, right? So this is also H, this is also H. Correct? Yes. So let's see 1, 2, 3, 4. Now further I'm introducing HBr to this. It's going to show Markovnikov rule. The negative addendum adds to the carbon having this. So what do we get? We are going to get like this particular thing breaks up. Here both are equal. It has to go to the carbon having lesser number of hydrogens, isn't it? So lesser number of hydrogens. Here this carbon has 2 hydrogens, but this carbon has only 1 hydrogen. So what do I get? I get this product as CH3, because this hydrogen goes here, negative addendum goes here. Single bond CH, Br and Br. Done. What is the name of this compound? This is called 1,1-dibromoethane. 1,1-dibromoethane. Done. 1,1-dibromoethane. Right. So this is the compound. So hope the concept is clear, students. So this is how you're going to add. Now next reaction, let us see the addition of hypochlorous acid in my next video. Thank you for watching, students. Hope this is clear. How did I add HCl, HBr, iodine around the double bond? That is your electrophilic addition reactions. Right. So let's come back and do the next type of electrophilic addition reactions, that is addition of HOCl. What is HOCl? It is nothing but hypochlorous acid. Hypochlorous acid. Right. So here we are seeing the electrophilic addition reactions, isn't it? Right. So first of all, let me take an example and explain. Suppose if I have ethane, let me divide the page into 2 equal halves and let us take 2 examples. In the first example, I'll be taking ethane. In the second example, I'll be taking propane. Yeah. So you can take any other or further examples also, not a problem. But important thing is understanding what are the products formed. When I take ethane or acetylene, first I'm going to introduce, or hypochlorous acid is introduced to this. So here I'm going to introduce HOCl or chlorine in water. Okay, this is also done. So this is 1 sigma and 2 pi bonds, isn't it? There is a cleavage of the bond here. There is also cleavage of this pi bond. Yes. So what will happen? Cl adds to this carbon, becomes a double bond CHOH, isn't it? Done. Now further, when this is introduced for the chlorine in water, what product do I get? I get a product this way. This still double bond, this breaks off, this adds. So what do we have? HOCl or this one. Again there is a cleavage of the bond. So to this carbon CH. Now this has become single bond, isn't it? Single bond. The Cl is here. 1 Cl. Yes. 1 more Cl I am adding here. This one. On this side we have OH. And 1 more OH we have added. This is very unstable in nature. What will happen? Finally it forms a product. What product does it form? Just see. Understand carefully. There is water here, hydrogen OH here and OH here. Because this is unstable, from this compound water is eliminated. When water is eliminated, what product do I get? Cl, CH, single bond CH and CHO. This is perfect and water is eliminated. What is the name of this compound? It is dichloroacetaldehyde. 2 carbons, isn't it? So let us write the name. Dichloroacetaldehyde. Now let us do the same process here. Here I am going to take propine. Done. To this propine we are going to add HOCl. HOCl. So as soon as this is added, there is a cleavage. Now what do I get? I get CH3 is still there. Only you should concentrate more on this triple bond. Only pi bond is broken. This becomes C double bond CH. Now what are we going to add here? We said the negative addendum adds to the carbon having lesser number of hydrogens, we said. Correct? Yes. Now this is a here what happened? It is added because both are similar. We added in this way. But here HOCl, whenever you are adding, careful, this adds, what breaks up, and it adds in this way. Further, when I treat with one more HOCl, there is a cleavage of this bond also, and what do I get? I get CH3, C, OH, and OH, and C, H. One more Cl here, one more Cl here, isn't it? This is broken, and this adds here to this, and this adds to this. Now this is further unstable in nature. So what are we going to do? We are going to eliminate water from this, as I've shown here. Same thing. Water eliminates from this. From where does the water eliminate? H from here and OH from here. Remember? H from here and OH from here eliminates. And what do I get? I get the final product as CH3 is here only. This becomes C double bond O. Then this becomes CHCl2. Done. What is the name of this compound? This is 1,1. Okay, this is started from 1, 2, 3. This is 1,1 dichloro, 3 carbon chain propanone. 1,1 dichloropropane, isn't it? So here we have got an aldehyde, here we have got a ketone. So 1,1 dichloropropane is here, and dichloroacetaldehyde is here. Because of the lack of space, I am not able to write it here. Understand, students? Once again, whenever hypochlorous acid adds, first it's going to form or break the bond, break the pi bond, and adds on either way. Further, if you add, you get a product like this, which is unstable. Further, there is elimination of water molecule forming acetaldehyde. Here, there is further elimination of water forming. What is the name of this compound? It is 1,1 dichloropropane. 1, 2, 3. 1,1 dichloropropane. Done? Right. So, thank you for watching, students. Let us come back and meet with nucleophilic addition reactions of alkynes. Welcome back, students. Now let's start with the next type of reaction of that is alkynes, that is oxidation reaction. After nucleophilic addition reactions, we'll come back to this concept, oxidation. So oxidation is nothing but addition of oxygen, isn't it? Right. So oxidation reaction, we can study this under the heading combustion reaction. You can study this under the heading using oxidizing agents like KMnO4, right? KMnO4, as I've shown you earlier, it's going to release out nascent oxygen. I can also study oxidation reaction under ozonolysis. Done? Yes. So let's see the first one. Suppose if I take the combustion process. What is combustion? Combustion is nothing but heating or burning in the presence of oxygen. So combustion reactions are always exothermic reactions, isn't it? Lot amount of heat is generated in this. So when I take an alkyne and see, right, so I'm going to take an alkyne. Now to this, as I said, combustion means which occurs in the presence of oxygen, it burns in the presence of oxygen. Always combustion products are carbon dioxide and water, whether it is saturated or unsaturated, the products formed are always carbon dioxide and water. But here, as I said, the reactions are highly exothermic in nature. And let's balance this. Now suppose if I take 2, 3, yes, so 2 if I take, and this is 4. Now 2 2s are 4 hydrogens, 2 and 2 hydrogens. Now oxygen is 5. Done. Suppose if I take, now let us see, the 4 here, hydrogens, 2 2s are 4 here, carbons are 4, 2 for this and 2 for this, 4, oxygens 4 2s are 8, plus 2, 10. y to the 10. So this is your combustion reactions, heating in the presence of oxygen. Now this, suppose if I take the same combustion or if I take the same oxidation reaction, we'll be studying the second type of oxidation reaction, that is oxidation in the presence of KMnO4, or using in the presence of using KMnO4. Why am I using KMnO4? KMnO4 is an oxidizing agent. This KMnO4 is going to supply or give us the nascent oxygen. Now this particular KMnO4 reaction I've already shown in alkenes. Please watch the video. Now I'm again going to take an alkyne. As I said, this KMnO4 is going to release nascent oxygen, which I have taken here. Now this whole reaction, as I said, it occurs in the presence of KMnO4, water. The first important thing what you should remember here is, whenever you're adding oxygen or in the presence of KMnO4, first important thing which is removed is MnO2 from here. After that, potassium and hydroxide, that is potassium hydroxide, also is removed from there. Now what are we going to get? Did you see here? This one, this compound, carbon and carbon. Careful. Here I'm going to add 4 nascent oxygens. Those 4 nascent oxygens are going to break the bond and form bond around this. There is one hydrogen here, H. There is one more hydrogen here, H. So how many oxygens I'm adding? I'm adding 4, isn't it? So one oxygen adds here, one more oxygen adds here, then double bond O, third one, this is double bond O, fourth one. So what is the name of this compound? This acid is called oxalic acid, HCOOH, right? So this oxalic acid, further when I treat it in the presence of acidic medium and KMnO4, that is, I'm going to maintain the temperature at 70 degrees. When I maintain, what will happen? This carbon dioxide, whatever is there, comes out as a product. So this is your oxidation with KMnO4. Let's come back and see the next type of reaction. Right. Now let's see the oxidation reaction of 2 more examples. That is, one is I have taken 2-butane and one is propane. The procedure is the same. So for oxidation, you require the alkane which I gave you. Let us write that. After that, we also require an oxidizing agent. What is the role of oxidizing agent? This oxidizing agent is going to give me butane, means 4 carbons. It's going to supply the nascent oxygen. So I'm taking KMnO4. Here I've taken propane. Let me write the example. This is your propane, isn't it? Triple bond, right? This is 3 bonds. Now again, I need KMnO4. Okay, but here you should not write KMnO4 directly like this. Means it is going to supply what? Nascent oxygen. So this particular reaction or this particular reaction, I can write it as, this is your butane, 2-butane plus nascent oxygen. This is how you should write in the presence of KMnO4. Correct? Yes, and water. This also, you're going to take propane. You're going to add nascent oxygen to this in the presence of KMnO4. And that is water. What are eliminated? As I told you in the earlier reaction, MnO2 is eliminated. Potassium hydroxide also is eliminated. Once again, MnO2 is removed. Potassium hydroxide also is removed. Now this is where the oxygen goes and adds, isn't it? So here, if I take, I'm going to take 2 nascent oxygens. Here, in this case, I'm going to take 3 nascent oxygens. What do you get? That this bond breaks up. Now see here, your CH3 is here. 1 oxygen adds to this because only 2 we added around this. Single bond. 1 more oxygen adds to this, and this is CH3. What is the name of this compound? 1, 2, 3, 4. But. So which positions are this one? 2 ketones are there, isn't it? I name it as 2, 3, 1, 2, 3, 4. So 2 and 3. 2, 3, butadiene. Okay, dione. Yes, ketone. Or you can write it as diketone because 2 ketones are there. Suppose if I write the same here, this one, what do I get? The compound, but here what did I take? I have taken propane, isn't it? Right? I am taking 3 nascent oxygens here. Now you have to be careful. When this breaks up, first CH3 is here. 1 nascent oxygen, because this bond is broken here, this goes and adds to the first carbon. Done? Now to this one. As I said, what will go out? MnO2 will go out. Potassium hydroxide also will go out. Isn't it? Yes. So did we write this wrong? We have written this wrong, isn't it? That is the reason H I've got extra. 1, 2, 3, 4. This is wrong. H. So propine. After this oxygen is added, one more oxygen adds to this carbon. Double bond O. There is hydrogen. So third oxygen comes and adds here. Now what did I get? I've got a compound. Let us name this. This is called 2-keto 1,2. Till here. This is 1. This is second carbon. 2-keto. How many carbons are there? 3 carbons. 2-keto propanoic acid. 2-keto propanoic acid. So this is how this one adds. Ma'am, how will I know which one to add? How many nascent oxygens to add? Simple. Just break the bond. Wherever you break the bond, you need to add the oxygens on either side. Isn't it? Yes. So this is your oxidation reaction, students. Let me come back and meet with ozonolysis reactions of alkynes. Welcome back, students, to the next type of oxidation reaction, that is ozonolysis. So when I say ozonolysis, it's nothing but addition of ozone molecule. Now in alkene chapter, here I mean in that particular alkene topic, I have taught you the mechanism of ozonolysis. So please go through the video. Ozonolysis, you should remember, important thing, addition of ozone with the mechanism. Then only you'll be having a clear idea of the products formed. Right. Here I'm going to directly write that. Again, I'm going to take an alkyne. To this alkyne, now see here, now I will not write specifically any alkyne. I'll show you the general reaction, then go back. So this hydrogen I'll take out, right? I'll take out, I'll just put an alkyne specifically. So let me not write, I'll write it in the next step. Now I'm going to take ozone to this. This ozone molecule, what does it do, right? It's going to break O3 molecules, isn't it? This is going to break this bond, first bond. And you get one oxygen adds here, second oxygen adds here. There is still a bond here. This oxygen linked to this. Now I'm going to reduce this in the presence of zinc and water. There is a cleavage of the bond here. This one here. And you get a product C double bond O, C double bond O. And this oxygen and this oxygen. Okay, this comes out. There's a cleavage here, isn't it? Like this. This one and this bond, and this oxygen is here. This comes out as hydrogen peroxide. Now, what is the name of this compound? This is called a dicarbonyl compound. Dicarbonyl compound. Now, let's take one example and then see how can we write this one more with a specific example. Right. Now, suppose if I take a specific example like propine. Let me take propine and see. How should I add? This is your propine. To this propine, I'm going to add again oxygen, ozone. So how does this add? This bond breaks up. First you get CH3. Then your CH, this is there. Yes or no? Right. So let's see 1, 2, 3, 4. Okay, this bond is extra 1, 2, 3, 4. So this hydrogen is extra. This should not be here. Now, right. This carbon is here only. One oxygen adds, this carbon is here, one more oxygen adds here, one more oxygen adds here, and this one, this. For this carbon 1, 2, 3, 4 bonds, for this carbon 1, 2, 3, 4 bonds, right? That means now this has become the fifth bond, isn't it? Now where will it cleave? Let me see. It's going to cleave, it's unstable, so this is going to cleave here. This also cleaves here. What do I get? I should use one reduction or reducing agent, zinc and water. Now, just see here, addition reducing agent is going to add hydrogen. One high water comes out with this as hydrogen peroxide. This one. And the leftover with the product which I get, this is your CH3, your CO is here, correct? And CHO is here. Now this further undergoes oxidation reaction. It undergoes oxidation and forms two types of products. What is this? See here, oxidation is nothing but addition of oxygen. You get two types of acids here. One is acetic acid, CH3COOH, and one is formic acid. So this is your product. Acetic acid and formic acid is a product. Suppose if you are going to write the same in the general way. See here, this bond is extra, isn't it, which we have written. So if I write it in the general way, let me see the general way and show you. Let me take out this page. Yeah. Suppose if I take in the general way, this is a general representation. General representation. R triple bond C this. I'm going to add, as I said, ozone molecule. This bond breaks up. It's going to add as R carbon. Fine. There is one oxygen linked to this and one more oxygen, this carbon. R is here. This carbon, one oxygen here, one more oxygen here. Now let's see the valency. 1, 2, 3. For this, 1, 2, 3. Isn't it? So if I write the third one here. Now this carbon is 1, 2, 3 only. If I join this, let me count this. So 1, 2, 3, 4, 1, 2, 3, 4. Now I'm going to introduce reducing agent, zinc and water. This water comes out with this because there is a cleavage of the bond here this way. This water comes out with this as hydrogen peroxide. Now what is left? There is one group here. There is one group here which I need to write. Let me write that. R C double bond O and C R prime. Let me take this as R prime so that it is, let us write here only R prime, means it's a different alkyl group. C double bond O. This further undergoes oxidation and it breaks up into two equal halves. Here this becomes RCOH is one acid, R prime COH is one more acid. Right? So this is how it's going to show the oxidation reaction and the ozonolysis process. Thank you for watching, students. So welcome back, students, to one more session of your alkynes. That is the last topic of your or the last concept of the chemical properties of alkynes. Today we'll be learning the polymerization reactions of alkynes. So when I have to speak about polymerization, there are two types of polymerization. There is cyclic polymerization as well as linear polymerization. Now I'll be showing you the cyclic polymerization of alkynes. Cyclic polymerization of alkynes. Yeah. So now what is important here? You have the basic alkynes, that is acetylene, acetate. Now what happens is, whenever I take acetylene, now I'm going to take 3 moles of acetylene. What is polymer? Basically a combination of monomers to form a long chain polymer. Polymer means many units. Suppose if I take 3 moles of acetylene and introduce this in red hot iron tube. Okay, right? At what temperature? At 873 Kelvin. See here, this bond shifts here, this bond shifts here, this bond shifts here, and together they're going to form a cyclic structure, that is benzene. So this is benzene. Monomers are combining together to form polymers. This is the polymerization. See here, this is a straight chain. Now it has formed a cyclic structure. Hence it is cyclic polymerization reaction. Suppose if I take the next type. Now I'm going to change an alkene. Now I'm going to take propane. So propane again. This is propane is 3 carbon chain. This is CH and this is your CH. Now I'm going to take the same propane, but here now I'm going to take the CH3 in here. CH3. C triple bond CH. Now the third unit here, I'm going to take CH triple bond C CH3. See here, I started from here and ended here. I started from here and ended here. I started from here and ended here. All three are 3 different directions. Now as I said, this bond shifts here. Okay, this bond shifts here. This bond shifts here. It's going to form a cycle. Now I said we're going to take in red hot iron tube. What temperature? 873 Kelvin. All are going to together form a cyclic ring structure, and CH3 is here, CH3 is here, CH3 is here. What is the name of this compound? It is right. This is first position, second position, third, fourth, fifth, and sixth. Okay. So we have first position, we have methyl group 1. Third position, we have methyl group. Fifth position, we have methyl group 1, 3, 5. Trimethyl benzene. Yes. This is also called as mesitylene. Mesitylene. This is one type of polymerization. This polymerization, one more, let me take one more example. Let me take out the page and one more example. Suppose if I take again 3 moles of acetylene, now I'll be taking 4 moles. One I'll be writing here. 4 monomers of acetylene are going to undergo polymerization reaction. That is a cyclic polymerization. Now here you're going to introduce nickel cyanide. You're going to take or maintain the conditions of pressure, under pressure, right? It's the same thing again. This bond shifts here, this bond shifts here, this bond shifts here, and this bond shifts here. Finally, what do I get? 1, 2, 3. Okay. Okay. Now, how many I got? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Octa, isn't it? What octa is it? Now I need to write the bonds also. There's still one bond inside. One bond here, one bond here, one bond here, one more. So this is cyclooctatetraene. Tetraene. Okay, tetraene. Tetraene. Okay, cyclooctatetraene. So these are the polymerization reactions of benzene. Suppose if I have to show you, okay, students, one basic thing in your NCERT textbook, there is only one part which is shown. So please practice this. Let me show you one more thing. Suppose if I take one more example, acetylene only, but here I am going to take 4. So this. Then what happens? All are going to show cyclization, and finally I get right. So welcome students to the next concept of your aromatic compounds. So previous video, what did we see? We have seen what actually is aromaticity. When can I call some compound as aromatic, or what is the concept of aromaticity? Please watch the earlier video. Now in today's session, I'll be teaching you the nomenclature or naming of aromatic compounds. Right. So let us take the first example, the basic example, that is your benzene. Right. That is what we are studying. Now benzene structure. This is your benzene structure. It's C6H6. So let us write the name. This is benzene. We'll be learning in further classes what is the Kekulé structure, orbital structure, resonance structure, what are the resonating structure, what are the resonance hybrid. Now let us learn only the nomenclature. Now this is benzene. Suppose to this benzene ring, if I introduce a methyl group, then this compound is called methyl benzene. This is benzene, this is methyl, small letter benzene. This is also called toluene. Now I'm going to introduce 2 methyl groups to this same benzene compound. One methyl group here and one more here. Now let us name this. This is first and this is second. What is this? This is 1,2 dimethyl, because 2 methyls are there, isn't it? Dimethyl benzene. 1,2 dimethyl benzene. Right? So this is also called as orthoxylene. 1,2 dimethyl benzene is also called as orthoxylene. Let me take one more example. Now I'm going to shift this methyl group to this position, meta position. Let's see. I'm going to take the same benzene ring, one methyl group here, one I'm introducing it meta. From ortho I'm shifting it to meta. Now name it 1, 2, 3. So this is 1, 3 dimethyl benzene. Isn't it? So small alphabet, I'm writing a big alphabet, don't write that. It is small b, benzene. Now what is this called? Metaxylene. Because it is a meta position. Now suppose if I take further one more example, from here I'm going to shift it to the para position. Shift it to the para position. CH3 is here, one more CH3 is here. para position. Now what is this? 1 and 4. First, second, third and 4. So this is 1,4 dimethyl benzene. Now what is this? This is called paraxylene. Paraxylene. Hope this is clear, students. So this is one set of aromatic compounds. Now let's come back and see one more. So toluene is over, orthoxylene is over, metaxylene is over, and paraxylene is also over. Now let me take one more example. Let me take out this page and start. Now in this example, I'll be teaching you taking one more group, that is, so what was that? Fifth one. Let me take the sixth one. I'm going to introduce one more alkyl group to this, that is CH2 and CH3. Now 2 carbons are there. What is this? This is called ethyl benzene. Done, because 2 carbons. Seventh example. I'm increasing the carbon chain. Now from ethyl, I'm going to a bigger one, that is CH2, CH3. Now how many carbon chains are there? 3. So this becomes N-propyl benzene, because 3 carbon chains are there, benzene. Now I'm going to show you a different combination. See here, this is propyl group. I'm going to show you isopropyl group. Keep it in the center. Now CH here, on either side, methyl group. This is called isopropyl benzene, because this is the iso group and 3 carbon atoms. So it is isopropyl benzene. Done. Now I'm going to introduce 2. Now I'll be joining 2 benzene rings. Suppose if I take one benzene ring here and join it with one more benzene ring in this way. How many are there? 2. Now I'm calling this as biphenyl, because 2 benzene rings are clubbed together. Now gradually I'm going into the polycyclic compounds. These are called polycyclic compounds. 2 or more rings. So polynuclear aromatic compounds also you can call, polycyclic also you can call. Suppose if the benzene rings are attached in this direction, alright, here like this, adjacent. This is called the naphthalene balls which you use, right? So this is naphthalene. Let me introduce some more. Let me take some more. Which is this example? I have taken the 10th one. Let me take the 11th one. Suppose if I am going to introduce 3 rings like this, 3. 1, 2, 3. Then this is called anthracene. Suppose if you have a polynuclear aromatic compound, poly means, as I said, many. So one ring here, one more here, one more like this. This is called phenanthrene. Right? So these are the different types of benzenoid or the aromatic compounds, students. Now let me go into the next class, that is heterocyclic compounds. So I'm trying to teach you the different classes of compounds. So I've picked up some. Now we will see what are heterocyclic compounds. Heterocyclic compounds. So when I have to speak about the heterocyclic compounds, just see. Heterocyclic compounds are, see here, how do they look? This is your benzene ring. Hetero means a different atom. In benzene ring, you have a different atom like nitrogen, oxygen, sulfur, like that. Then we call it as heterocyclic compounds. So when you have a ring, or when you have nitrogen like this as a ring, this is called pyridine. Suppose if you're introducing, I'm taking a ring, and here in this case you have oxygen. This is called furan. Suppose the same thing. If you have, instead of oxygen, if you have sulfur, then I call it as thiophene. Suppose if I have nitrogen and hydrogen, this is called pyrrole. Right? So these are the aromatic compounds, students. Let's come back and see one more set of class, and that is other aromatic compounds. So I'm going to show you different examples, other aromatic compounds. A lot of examples we will do. Right. So another aromatic compounds. Suppose, let me number this. I have a benzene ring and I'm going to have like this. What is this compound? This is called, if you have a halogen attached to a CH2 group, then it is called benzyl. Understand this. So benzyl, name this compound. This is benzyl chloride, or you can call it as phenyl chloromethane. Phenyl chloromethane. If I take one more example, this is benzyl, isn't it? Now see here. In the compound, if you have like this, now hydrogen is 1, chlorine are 2, then you call it as benzyl. Benzyl chloride. Now you don't have any hydrogen, you have only CCl3 group. This is called benzo trichloride. Benzo trichloride. Hope this concept is clear, students. Benzyl is this one. Benzyl is 1 hydrogen. No hydrogen. It's called benzo trichloride because 3 chlorides. Correct? Now let's see one more class. Suppose if I don't have any alkyl group, I have a halogen attached. Suppose if it is like this, a benzene ring with chlorine, a benzene ring with bromine. What is this called? This is called chlorobenzene. This is called bromobenzene. Easy, isn't it? Yes, done. Let us come back to alcoholic group. Suppose if I have a benzene ring like this, alcoholic group. Suppose if I have a benzene ring with a ketonic group. Suppose if I have a benzene ring only with OH. See here. Whenever you have a functional group and an CH2, then you call it as benzyl. This is called benzyl alcohol, or it is also called as phenyl methanol. Phenyl methanol alcohol. Now let us name this. This is called anisole. If this group CH3 group and O oxygen is there, this is called anisole. And how can you name this? This is named as methoxybenzene. This is an ether group, isn't it? So not ketone, it is an ether. If it is ketone, it should be CO. It is an ether. So this is methoxybenzene. So which group is this? Ether. I'm sorry students, I said ketone, please correct it. It is an ether. Now here, benzene ring with OH is called phenol. Right. Let us see some more examples of this. Right. So if I have to go with the next example, let us see how to name this. Now if a benzene ring has 2 different functional groups, one is alcoholic group, one is methyl group. Now here this is methyl is in ortho position. The same thing, I am shifting the methyl group to meta position. The same methyl group, I am shifting it to para position. How to name this? This group, when you have OH and CH3 together, it is called cresol, right? This also is cresol, OH and CH3 together. This also is called cresol because OH and CH3. Which cresol is this? Orthocresol. Which cresol is this? Meta. Which cresol is this? Para. How can I name this? I can also name this as 2-methyl-phenol. Correct? Yes. Now let us see one more functional group. If I have a benzene ring with CHO. If I have, now it is ketone, see here. If I have a benzene ring with COCH3, this is ketonic group. Now we call this as benzaldehyde. We call this as acetophenone. 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 I can also name this as phenyl methanol. Phenyl methanol. This one, phenyl ethanoate. ethanoate. This also can be written as benzene carbaldehyde. Carbaldehyde. Right. Let us take some more examples and see. Suppose if I have a benzene ring like this, CO. What is the name of this compound? See here, benzene is here. This is, okay, let us take this. This is phenonic group. Phenone. This is benzene. So, according to the alphabetical order, benzophenone. ONE1 because it is a ketonic group. I can also write this as diphenyl methanone, isn't it? So, this can be written as diphenyl methanone. Suppose if I have a group like this. Now I said whenever there is an group attached, what do we call this? This is phenyl ethanol because it is an aldehyde group. So alcohols are over, ketones are over, aldehydes are over. Let us come to acid now. If I have a benzene ring and COH, so what I name this? I call this as benzoic acid. After acid group we have nitriles, isn't it? Your amines. Now this one, I call it as benzonitrile. Right, let me take out this page one more. Suppose if I have a benzene ring, I am taking all the functional groups together, C double bond O Cl. If I have a benzene ring with, let us name this. This is benzoyl group. This whole thing, C6H5CO is benzoyl. Benzoyl chloride. Let us name this as benzoyl chloride. How can I can also name this as benzene carbonyl chloride. Let us name this now. This is which group? Methyl. Which is this group? Benzoate. So we will write it as alphabetical order. No. Here functional group is should come at last. So this is methyl benzoate. Now one more. If I take like this, benzene ring it says this is called phenyl. This is phenyl. What is this group? Ethanoate. Correct? Yes, phenyl ethanoate. Right. So one more example, students. Let's try with one more and more examples you learn. You will become perfect with that concept. Suppose if I have this, I have a ring, benzene ring. There is one more, there is one more benzene ring as here. These two are attached with CO group. This is benzoic anhydride. I showed you, isn't it? We take out water molecule, then we take 2 moles of acetic acid, we take out water molecule and join. So this is called benzoic anhydride. Sorry. Now, let me take one more group. What is this? This is called nitrobenzene. Done. Suppose if I have a group like this. What is this? Isocyanide group or carbylamine we call. Suppose if I have like this, carbon attached to nitrogen. This is nitrogen attached to carbon, here carbon attached to nitrogen. If nitrogen is attached to carbon, we call it as benzene isonitrile. Iso. This is called benzonitrile. Or you can call this as phenyl carbylamine. You can call this as benzene carbonitrile. You can also call this as phenyl, capital phenyl isocyanide. Right? Fine. So let me see one more class. If I have a benzene ring like this, and if I have an NH and CH3, what is this compound? This is methyl. So N-methyl aniline, because NH2 is aniline, correct? We have already, okay, and aniline we have not seen. Let's see that aniline, the earlier one. Okay, let's see. So this is NH2. This is aniline, NH2. Right? To this aniline, what did I do? I've taken out one hydrogen and added methyl group. So it is that is N-methyl aniline. Let me introduce one more. I take the same benzene. Okay? I'm going to introduce two methyl groups. Here one methyl group, N in the center, and one more methyl. So this is linked to the nitrogen. This is called N, N dimethyl aniline. Now, suppose if I have a group, if I have a benzene ring like this, cyano group is here, bromine is here, OH is here, one combination. If I have one more combination, acidic group is here, NO2 is here, CN is here. Name this compound. How do I name this compound? This is named as, first number it 1, 2, 3, 4, 5, 6. So number 2 bromo, 4 hydroxy, benzene carbonitrile. This is the name, alphabetical order. Now this one, if I have to name, number it 1, 2, 3, 4, 5, 6. What is the name? 4 cyano, 2 nitro, benzene carboxylic acid. Carboxylic acid. That's it. So these are the different nomenclatures of aromatic compound, students. Thank you for watching. Now let us come back and start with the structure of benzene. Thank you for watching. Right, so welcome back, students. We have successfully completed alkanes, alkenes and alkynes, all the 3 hydrocarbons. We have studied different types of reactions in that. Now we'll be starting with the last topic of the hydrocarbon chapter, that is arenes or aromatic compounds. So in this particular, in the NCERT textbook, a very small concept is given. They've given you orbital structures of benzene, Kekulé structures, but here I'll be dealing with the clear explanation of each of the topic. Very important concept of aromatic compounds. So please watch the videos on daily basis. Now, when I have to speak about arenes or aromatic, what does that mean? Aromatic basically is derived from the word aroma. Derived from aroma. Okay, what is aroma? Aroma is nothing but it means fragrance. Right, fragrance means a smell. Fine, right. So this fragrance or this particular thing, these compounds, belong to this category. They've been isolated long years ago, right? So because of this fragrance, they showed the fragrance. That's the reason we gave them as, or it is named as aromatic compounds. So here for your grade 11, the aromatic compound refers to benzene. Here they've given unrelated compounds also. Basically, whenever I speak about aromatic, there's a lot of difference between aromatic compound and aliphatic compound. Aromatic means ring structures, just like benzene ring. Aliphatic means straight chain structures. First important, what should you remember for aromatic compound? Let us see those. So the first important are the characteristics of aromatic compound. It is right, characteristics of aromatic compound. So whenever I speak about aromatic compound, the first important word or the first important sentence which it should strike your mind is, aromatic compounds have ring structures. Ring structures. This is the first important thing you should remember. This ring structure, how is it? It is planar in nature and single plane, and they have alternate pi bonds. So pi bonds will be alternate in their structure. This is the first important thing which you should remember. After this, the next important thing, they're going to exhibit resonance. So I'll be showing you the concept of resonance also. There's a shift or delocalization of pi bonds. And when they exhibit resonance and they have high resonance energy, very high resonance energy they're going to possess. So this is the next important concept of, or this characteristic of aromatic compound. Let us see further. And this whatever pi electrons cloud or whatever pi bonds are there, the alternate pi bonds are there, as I said, they're always delocalized. They're going to contain, or the pi bonds contain, or they follow 4n plus 2, or they contain 4n plus 2 pi electrons. This is called Huckel's rule, where n can be 0, 1, 2, 3, 4, like that. Next important characteristics. They do not undergo addition reactions. I should tell you the reason also why they do not undergo addition reactions, though they have alternate pi bonds. Addition reactions like alkenes or alkynes also, they do not show addition. Both show addition reactions, and this doesn't show. And next important characteristic, this benzene ring is not affected by strong oxidizing agents. Strong oxidizing agents. What are the oxidizing agents which you have studied? Like cheminophore, which releases nascent oxygen, or one more oxidizing agent, K2Cr2O7. Correct? So it is not affected by that. I'll also tell you the reason why it is not affected. Next, it's not going to decolorize, does not decolorize bromine water. Decolorize bromine water. So normally we say, it is a test for unsaturation, isn't it? So it will not here, though it has alternate pi bonds, it will not decolorize bromine water. Remember this. Next important characteristic which you should remember, hydrocarbon, the arenes, they undergo substitution reactions. They undergo substitution reactions. Very important. Addition they will not undergo, but substitution they will undergo. And whenever they're burning, they burn with sooty flame. Yeah, sooty flame. Why? Because they have very high carbon content. C6H6, isn't it? 6 carbons are there. That's why they burn with a sooty flame. Let me write some more characteristics. And they're also called arenes, I said, isn't it? Yes. So this benzene or whatever is there, this is the simplest aromatic hydrocarbon. Remember, we're going to study about its Kekulé structure, orbital structure, electrophilic substitution reaction. Lot of substitution reactions will be alkylation, acylation, sulfonation, nitration, like that. So these are all called benzenoid compounds. The benzene, whichever has benzene structure, they call benzenoid compounds. There is also one more class called non-benzenoid compounds, which we'll be studying. So benzenoid compound, under that we'll be studying benzene, toluene, xylene, like that. Non-benzenoid compounds that you'll also be studying, that is a heterocyclic compounds. That is what we'll be doing that class also. So first important thing, whenever you're studying aromatic compounds and arenes, aromaticity, this is the key word which you have to remember. Aromaticity is important character. It's a very, very important character. So what does this say? It is an important character. Fine. What is this aromaticity, if I have to speak in correct sense? It is possessing, as I said, it has a benzene with a hexagonal ring structure. So I can call something as aromatic compound when it possesses a planar ring structure. This is the first important thing. Planar ring structure. And one more, after possessing planar ring structure, it should have with alternate pi bonds. It should have alternate pi bonds also. Then only it is called aromatic compound. Next, important characteristics of aromatic compound. Exhibits or exhibition of resonance. I'm repeating the same again. Exhibition of resonance, where I'm going to show you delocalization of pi bonds. Pi bonds will be delocalizing in the positions, alternate pi bonds. Whenever it's exhibiting resonance, it should have with high resonance energy. High resonance energy. Next important, it's going to possess a position of 4n plus 2 pi electrons. As I said, we are going to learn Huckel's rule, 4n plus 2 pi electrons. Last but not least, very important, delocalization of pi electron cloud. So occurrence of cyclic delocalization. So there will be, as I said, there is movement, alternate movement of the pi bond, delocalization of pi electron cloud. So if all these four characteristics are present, then it is called as aromaticity. Suppose if your teacher is asking you, what is the concept of aromaticity? What is aromaticity? What does it mean? Please write these 4 points. You'll be getting full marks. So it possesses a ring structure with alternate pi bonds. It indicates aromaticity. And next important thing, it exhibits resonance. As I told you, resonance it should exhibit. Whenever it is exhibiting, the resonance energy should be very high. Next important thing, it is going to follow 4n plus 2 pi rule. That is your Huckel's rule. And next important, cyclic delocalization. There should always be delocalization of pi electrons in the ring. Then only it can be called, or it is possessing aromaticity. Thank you for watching, students. I'll meet you again with nomenclature of aromatic compounds. To one more session of your hydrocarbons. So till now what did we learn? We have learned the different hydrocarbons, that is alkenes, alkenes and alkynes. Then I took you into a concept of aromatic hydrocarbons, that is arenes. In aromatic hydrocarbons, I have also taught in the previous video nomenclature of arene compounds, isn't it? I've shown you different examples, almost 40 plus examples I have taken. In that, I picked up examples, then I started teaching you the different, the naming or nomenclature, the IUPAC nomenclature, everything I've taught in the previous video. Please watch the video and come back to this topic. Now today, the topic which we are going to learn is structure of benzene, right? So when I speak about structure of benzene, first of all, what is the formula of benzene? Benzene formula is C6H6, isn't it? Right. To name, or what is this for? This is a molecular formula. So we are going to write molecular formula of benzene. When somebody asks you what is the molecular formula, this is the formula. Now to explain the structure of benzene, isn't it? They have, the different hypotheses, different statements were given for the structure. Let's see what are the different hypotheses of the structures and what are the valid. What is the valid explanation given here to explain the structure of benzene? First, like Kekulé was a person who was given the structure of benzene. Apart from that, we'll be studying Kekulé's structures. Apart from that, several other structures also were given, but they were not accepted. For example, this in Dewar structure. Dewar structure of benzene also was given. Okay, Kekulé structure, Dewar structure. After Dewar structure, it was Claus structure. After this, it was Armstrong structure. Okay, these are the different types where they were not accepted only. But we're going to see all those. Then Ladenburg structure. After that came into existence Levine and Cole structure. Then came into existence the modern view, where it is there in your NCERT also. So in this modern view of benzene, we are going to study the structure of benzene based on resonance concept. After that, I'll be teaching you the orbital structure, where we call it as orbital structure. In that orbital structure, means this only the same thing, I'll be teaching under orbital structure. So after orbital structure, basically, like I'll be showing you which is hybridized, what is hybridization of that, everything. In this only, I'll be teaching you a concept called Huckel's rule. Huckel's rule. Right? So these are the different structures. So let us start. Among these, Kekulé structure was the accepted one. There were few objections, but Kekulé structure is the accepted one. Next comes resonance is an accepted one. Orbital structure is an accepted one. And Huckel's rule, the most important, is accepted. So all these were not accepted because of certain objections, which we'll see. So not accepted. Done. We have written this, and let's see one after the other. So when I have to speak about the Kekulé structure of benzene, basically, so first important thing you remember is, whenever you take benzene, right, what are the important things which you should remember? See, and then we will go to the structure. So whenever we see, first important, okay, you should remember the points to remember in benzene. So remember, I'm writing this, points to remember for benzene. Okay, for benzene, what are the important points you have to remember for benzene? Remember, just see, note it. So for benzene, I said it has alternate double bond, isn't it? In the whole structure of benzene, there are 3 bonds which are arranged alternatively. So if I have to find its degree of unsaturation, right, alkenes also have, alkynes also have double bond and triple bond. If I have to calculate degree of unsaturation, so what is this? I have read 2 into 6 plus 2 by 2 minus 6. Okay, so when I'm calculating the degree of unsaturation, how much do I get? I'm getting 4. Now what is the formula for this? So directly written the values here. So when I get 4. So when compared to alkenes and alkynes, the unsaturation is very high, isn't it? It is 4. That's so we should write unsaturation is high in benzene compared to what? Benzene compared to alkenes and alkynes. Okay, so this is one thing which you should remember. First important, so unsaturation is high. Second thing, important concept which you should remember is, whenever I speak about unsaturation, what do we think? Our first concept comes to bromine water test, isn't it? Right? So important thing is, it does not decolorize bromine water. Okay, so remember, because we do test for unsaturation, isn't it, using bromine water. So it does not decolorize, benzene does not decolorize bromine water. That's important thing. Next, it also does not decolorize Bayer's test. Means these are all general Bayer's reagent. All these are general things which you should remember. These are common. These are important. What do you say? These explain the basic importance. Means benzene will not respond to this. Benzene will not respond. This is what you have to take out as a criteria while studying benzene. So it does not decolorize. When you add bromine water, it will not decolorize. It will not even decolorize Bayer's reagent. Next important thing is, it is not oxidized by, third thing, not oxidized by, what are the oxidizing agent? KMnO4, isn't it? It is not oxidized by, this is it, by alkaline KMnO4. We will see the reason also one after the other. First let us note everything. KMnO4, or one more reagent, acidified potassium dichromate, E2Cr2O7. This is one more characteristic of benzene. Next important thing which you should remember, let us write here only. Next important thing, instead of undergoing, because we said it has high unsaturation in it, isn't it? But here, instead of undergoing addition reactions, we'll try to prefer undergoing substitution reactions only. Like, remember that. So what I'm going to write here, instead of, why also we're going to see the reason very soon. Instead of undergoing addition reactions, it undergoes substitution reactions. So note all these points. So any question will be asked from any part of the point given. Undergo substitution reactions. That. Next important thing, we said it will not decolorize bromine water, it will not decolorize Bayer's reagent, not oxidized by oxidizing agents like potassium dichromate and potassium permanganate, right? So next we have written it undergo only substitution reactions, not addition reactions. That's also fine. Now, next important thing, whenever I take benzene, okay, suppose if I take benzene, this is C6H6. Now I'm going to hydrogenate. Hydrogenate means addition of hydrogen, and that too this occurs in the presence of, because whenever you're adding hydrogen, that is a reduction, you require reducing agent like metal. So nickel, the temperature which I'm going to use is 180 degrees. So here I'm going to add 3 moles of this. Then what happens? This gets converted. 3 to the 6, no? 6 hydrogens you are adding. So these 6 hydrogens will add to this. This becomes 6 plus 6, 12. So C6H12. What is this compound now? This is called cyclohexane. What is this compound? This is benzene, isn't it? Right? So whenever you're doing hydrogenation reaction to benzene, benzene gets converted to cyclohexane. Remember that. Now, suppose if you're trying to take the same benzene, I'm taking the same benzene. Now I'm allowing it to undergo chlorination. This is hydrogenation. This is chlorination. Hydrogenation is nothing but addition of hydrogen. Chlorination is nothing but addition of chlorine. Again, I'm going to take 3 moles of this, but this occurs in the presence of sunlight. This is very, very important. So, in the presence of sunlight, what happens? Benzene combines with 3 moles of chlorine. And what does it form? It forms a compound. Now, let us count how many are there. 3 to the 6. You're going to add these 6 to benzene. This is going to form a compound C6H6 and Cl6. 6 are there directly. So what is the name of the compound? This is called BHC. Let's see what is the name of this. B stands for benzene, H stands for hexa, C stands for chloride. Let us write what we have written. It is benzene hexachloride. So if you add 3 to the 6, 6 hydrogens, 3 to the 6, 6 chlorines got added to this. So these two reactions, what do they confirm? These two perfectly confirm that the presence of 3 pi bonds. If our teachers asked you what are the 2 reactions which confirm the presence of 3 pi bonds, just write hydrogenation and chlorination reactions of benzene. Please, you can note this out. Benzene confirms the presence of 3 pi bonds. How did I do 3 pi bonds? How did I get this? I see here, because of the presence of 3 pi bonds, those 3 pi bonds broke and 6 hydrogens added. Here also, the presence of 3 pi bonds, those broke and 6 chlorines got added. So these 2 reactions are very important to confirm the presence of pi bond. And next important thing, whenever you're taking benzene, you have to also remember which point is that. I've written 6th point. Let me write the 7th point. So where this, before Kekulé also came into existence, several structures were given, means several open chain structures were also assigned to explain the benzene structure. What was it? Several open chain structures, like, let us see, several open chain structures. So now we've come to a conclusion that it's a cyclic structure, but before that several open chain structures were introduced. Like we said C6H6, isn't it? So that C6H6 was divided into, it was shown like this: 1 double bond C single, this is triple C, okay, H later we can write double and C. This was also given. Now fill in the hydrogens. H2, this is H, there is no hydrogen here, this is H and this is CH2. This was, such structure was given, which is not accepted only. One more structure which they gave was this also was one more structure which was given to benzene. 1 2 3 4 5 6 1 2 3 4 5 6 6 carbons. This was also not accepted, right? There is one more structure which was given in this way. There is one more CH2. This is also linked to CH2. These 3 are linked, and now there is a double bond. They've given double bond here. So such structures were given to benzene which was not accepted. Then after all these conditions and after everything, benzene structure, a proper and acceptable structure was given by Kekulé. So let us come back and do the Kekulé structure of benzene. Thank you for watching, students. Welcome back, students. So in the previous video I've taught you the different means what are the characteristics, how do you assign the properties to benzene, whether it will decolorize bromine water, whether it gets oxidized with potassium permanganate dichromate, or is it going to undergo hydrogenation reactions or chlorination reactions. Now in this video we'll be studying about the structure of benzene, that is the valid structure, that is Kekulé structure of benzene. So some say it is Kekulé, right? So I'm using the word Kekulé structure of benzene. So basically, what did Kekulé explain us? So Kekulé, most important thing is he's proposed a ring structure. Okay, Kekulé has proposed a ring. So we call this ring as cyclic structure. So cyclic structure of benzene, this is what Kekulé has proposed. Now according to him, what is that? He said benzene has a planar hexagonal structure. The first important point or first important concept which he has explained is benzene has. So we're going to start like this. What does it have? It has a benzene has a planar. Okay, we will see what it is. A single plane, like just one sheet like this, not a three-dimensional structure. A planar hexagonal. Okay, there are structure. So in this planar hexagonal structure, what does it have? This planar hexagonal structure has 6 carbon atoms. First important thing, right? So 6 carbon atoms, where are they present? They are present at the corners. After that, each carbon atom, there are 6 carbon atoms, isn't it? Again, this 6 carbon atom is attached to hydrogen. So you have 6 carbon atoms with 6 hydrogen atoms, okay, attached to carbons only in the corners. This is also over. Now to satisfy the fourth valency, what will happen? He further said, along with this, he also said there is alternate pi bond. So what is alternate pi bond? And this is he said there are alternate pi bonds in the ring. So this became as a familiar structure with this concept: 6 carbon atoms at the corner, 6 hydrogen atoms at the corner attached to carbon, and the fourth valency is satisfied by alternate pi bonds. So how is the Kekulé structure? The basic thing which we draw every time. So 6 carbon atoms, isn't it? 1, okay, 2, 3, 4, 5, 6. So all the corners now join 1, 2, 3, 4, 5, 6. 6 corners, 6 carbon atoms, 6 hydrogen. I said alternate. This is over. Now alternate pi bonds. Here. Leave one. Second, leave this. And this is your Kekulé structure. So what is this? The ring, whatever is here, it is symmetrical, isn't it, with its structure? So this, let us say, this is symmetrical. So this is a Kekulé structure. Now it confirms uniformity because of the structure, Kekulé structure. It confirms the formation of very important concept. Just see, what does it say? It confirms structure. It is right, structure. Its structure, Kekulé structure. So Kekulé structure confirms the formation of. So because of this, we are going to learn first important thing. Only one mono-substituted product. What does that mean? That means C6H6 is a formula. Now C6H5Z. What is this? This is a mono-substituted compound. Means one hydrogen is replaced. So only one mono-substitution product, C6H5Z, irrespective of which hydrogen it is displaced, it forms. Whichever hydrogen. In the 6 carbons, whichever it is displaced, it's going to show mono-substituted product. Now, suppose if I take the second one. So what is this one? This is only one mono-substitution product. Now, what is the next one? Mono-substituted product irrespective of which hydrogen among the 6, which hydrogen it is going to replace, that is irrespective of which hydrogen is displaced. This is one concept because of the Kekulé structure. Next, suppose we take 3 distribution products. How? Means mono I said, suppose if you are going to get 3, you will be also getting 3 products. How? At 1, 2 means, just see, if I take benzene like this, this is 1, 2, 3, 4, 5, 6. That means you may get dye substitution products, right? So it can be here 1 and 2. Okay, it's 2. 1 and 3 is 2. 1 and 4. So what are this? When they form like that, then we call it as ortho. This is meta, and this is para distribution. So ortho, meta, para, dye substituted products. This is mono substituted product. This is dye substituted product. Dye. So it was found that it produces, means this also and this also. It's going to form this and this. But what did he say? That means further when you study, you'll be seeing products formed at ortho and para also, meta also. That's why this is a combination 1, 2, 1, 3 and 1, 4. Now there were certain objections to Kekulé structure. Very few objections were there. Kekulé structure, what are these? We'll see. So we will learn under some objections. Why was Kekulé structure objective? We'll see some objections to Kekulé structure. Some objections. So first thing, see here, we said 1, 2, 1, 3, 1, 4 combinations, isn't it? Now it has to form 2 different types of ortho dye substitution products with this structure, isn't it? Right? So whoever has objected Kekulé structure, they said according to the structure it has to form 2 different ortho dye substituted product. Substituted or substitution product. What? How should it look? It should look like this. This is one benzene ring. Okay. One compound, one element is here, X, and one more Y. This is ortho position, and one more. It should also form one Y here and X here. So it has to form 2 different ortho dye substituted product with this structure. Right? Is it forming? No, isn't it? So this is what they objected, and it also failed to explain. It could not explain why why benzene does not undergo oxidation with K-4. So it failed to explain. Kekulé structure failed to explain the reason why benzene does not, we told initially, isn't it? It does not undergo, or it will not undergo oxidation with K-4 or with potassium dichromate. He could not explain the reason why benzene does not undergo oxidative, we told oxidation, basically oxidative degradation means why does it not undergo oxidation with what one, with what, with oxidizing agent, isn't it? Oxidative degradation with alkaline K-4. Okay, alkaline K-4. Then so this also was not explained by Kekulé, the main reason. So here in this was one objection, this was one objection. What was the objection in the above case? According to Kekulé, he said the pi bonds are static. Pi bonds are static, he said. He did not say, according to orbital diagram, it will get delocalized. Because pi bonds are static, this concept will not work, isn't it? That's why Kekulé structure was questioned for that. Right. So now several other structures came into existence. Now we'll be seeing the several other structures for Kekulé. So whenever you're drawing the Kekulé structure, either you can make it in this way. How did I make? You can write it as cyclic ring structure 1, 2, 3, 4, 5, 6, isn't it? All joined together with carbons as he has shown. Carbon, and this is linked with hydrogen. 6 corners, hydrogen are there, and along with that you have alternate pi bonds. If I start with the first one, this is, if we take one pi bond here, leave one, second one, leave one, and third. The same thing you can denote in this way. This is your Kekulé structure of benzene. This is benzene. Which one? This is your Kekulé structure. So this is the answer. Thank you for watching, students. I'll meet you again with the next type of structures of benzene. Let's start with the first reaction, that is nucleophilic addition reactions of alkynes. So here what did I say in the index? We are going to see the hydration of alkynes. Okay, what is hydration? Basically, hydration reactions. Hydration is nothing but you'll be adding water molecule. So whenever you're adding water molecule, this particular thing happens in the presence of strong acids. What is the strong acid which I'm going to show you? The strong acid which I'm going to take here is sulfuric acid or mercuric sulfate. Right. In the presence of this only, the hydration around the triple bond happens. Right, let us see the reaction. Now during this process, first important thing which we are going to learn is, in this type of reaction we are going to learn a concept called keto-enol tautomerism or enol keto tautomerism. Okay, here we'll be getting first enol and then go there. So I'm writing enol keto tautomerism. Okay, what is this? We will see gradually. So here first let me take an alkyne. So I'm going to take an alkyne, but here I'm not mentioning which alkyne it is. I've taken the general one. Now I said we are going to do the hydration reaction. Hydration is nothing but addition of water. When you're adding water, what is important? This has to occur in the presence of an acidic medium, isn't it? Right? So HgSO4 or slash H plus. That means you are taking a presence of a strong acid. Once you're taking this, what will happen? This water molecule, just see here, careful. Whenever this is adding, fine. So HOH, you can write water as HOH, isn't it? Right. There is a cleavage of this triple bond here, and how does it add? It's going to form a compound. Let us see. Now what is existing? C double bond C. Now what else is left? R, alkyl group is present on one side. There's a cleavage of the bond here. One H adds here. This H adds to this alkyl group. There's one more carbon here with alkyl group R, and your OH is left out. Isn't it? Yes. So this OH, suppose if I have expanded, right, 1, 2, 3, 4, 5, 6, 7, 8, isn't it? Right. This is, what is the name of this? Right. This is alcoholic group, isn't it? Alcoholic group. That's why we call this as enol tautomer. Enol means, enolic means alcoholic group. So enol tautomer. Now what will happen? This enol tautomer is in equilibrium with, just see here, is in equilibrium. I'm writing this, is in equilibrium with, just I'm writing a compound, see here, R, the same thing, C, this is here, then careful, C, okay, I'm taking this C, R is still there only, fine, double bond O. Okay, what happened to the hydrogen now? This hydrogen is going to shift to this carbon. You see here. Now, simple. The hydrogen was here. There is a shift of hydrogen from this carbon to this carbon. Then it's going to form a different compound. Now, what is this compound? This is ketonic group, isn't it? That's why it is called keto tautomer. Keto tautomer. So this is enol tautomer and this is keto tautomer. This interchange or this equilibrium existence between the enolic group and the keto group, or the enol tautomer and the keto tautomer, this phenomenon is called tautomerism. Okay, keto enol tautomerism or enol keto tautomerism. So this concept of existence of equilibrium between both the isomers which are interchangeable, right? Now what happened in keto-enol tautomerism? One of the hydrogen from here has shifted to this carbon. That only is your keto-enol tautomerism. Done. Now let me show you one more example. Suppose if I take this example, now I'll be specific. Now I'm going to take acetylene. Now I have to add water because it is hydration, HOH. Now what is important? You should have an acidic medium, that is sulfuric acid slash mercuric sulfate or slash sulfuric acid. isn't it? Yes. What temperature? It's going to occur at 330 Kelvin. Done. As I said, there is a cleavage of this bond, isn't it? Yes. So there is also a cleavage of the bond. Fine. So this hydrogen goes and adds to this, and this OH comes and adds to this. Then what do I get? This CH becomes CH2, isn't it? Yes. After that, there is a double bond existing. To this CH, your OH comes and adds. What is the name of this compound? This is 1, 2, 3, 4. Right? This is called vinyl alcohol. Vinyl alcohol. Done? Fine. So now this further, as I said, it exists in equilibrium. This is all enolic group. Now it has to, this hydrogen has to shift here to this. This hydrogen will shift here. It's going to be in equilibrium. This H will shift to this carbon. So this becomes CH3 and single bond CHO. What is this? This is acetaldehyde, isn't it? So this is how it exists in equilibrium with the this is keto. This is enolic tautomer. This is keto, or this is aldehyde now, isn't it? So this existence or this particular keto-enol tautomerism is explained using hydration reaction. Now let us see one more. Let me take out this page and give you one more. Yes, let me take out. Now let us see one more example for hydration of unsymmetrical alkynes. Suppose if I take example 2. Okay, in example 2, just see, I'm going to take, which one is this? This is propane. Let us write the name, propane. Here I'm going to do hydration reaction, water. As I said, it happens in the presence of a strong acid, mercuric sulfate or sulfuric acid. So what's the temperature? 330 Kelvin. So this bond breaks here. How do I get? Just see here, this also breaks. And the product which I get in this case is propanone. This is propanone. So this is how it adds. So the cleavage is here, 2 hydrogen adds to this carbon, and wherever there's bond broken, oxygen comes and adds here. Now let us further see addition of some more. I said, what did I give you in nucleophilic addition reactions only? We will be seeing addition, okay, further examples. So now I'll be showing you addition of HCN. What is HCN? Hydrogen cyanide. Here this breaks up into H plus and Cn minus. Right? This is a nucleophile. Now the same thing, suppose if I take acetylene, I'm going to add HCN. There's a cleavage of the bond, plus and minus. Again, there's a cleavage of, or there's a bond which is broken here. When this breaks, okay, what is required? Here basically, this whole reaction occurs in the presence of barium cyanide. This barium cyanide, we use it earlier, like we use it in the production of hydrogen cyanide. The poison is hydrogen cyanide, but here we are using it, right, as a source of your cyanide. Now what happens? The bond breaks. What product do I get? I'm going to get, this is here, this hydrogen goes and adds to this carbon, CH2. Now double bond. This CH is here and this cyanide comes and adds to this. What is the name of this? This is called acrylonitrile. Done. Let us see one more example here. Here I'm going to show you addition of methanol, CH3OH. So as I said, methanol, where does it break? It breaks here and this becomes plus. So we have 2, one is CH3O minus and H plus. Right? So this is a nucleophile here. Now when I'm taking an alkyne, I'm going to add CH3OH. As I said, where does it cleave? It cleaves here. Now what do I get? Immediately when there's a cleavage of the bond here, you need to break this bond also. When this breaks up, now what will happen? The hydrogen goes and adds to this, and methoxy group goes and adds to this. I'm going to get, when this hydrogen adds, it becomes CH2. Double bond is still existing. Then this is your CH. After that, OCH3. What is the name of this compound? We'll be naming in this compound as methyl. Okay, let us start from here. Methyl. This is vinyl, isn't it? This is your vinyl group. This is methyl, vinyl. This is oxygen here, ether. So let us write methyl, vinyl, ether. This is a compound, right? Now let us see one more example here. Suppose if I take acetic acid. Okay, as I said, I'll be showing you the addition of acetic acid as well as diacetate also, isn't it? Fine. So here, suppose if I take acetic acid, reaction with acetic acid. So acetic acid formula we very well know. Just okay, let me take an example. I'm going to take an alkyne. I'm going to add acetic acid CH3COH. Now where is the cleavage exactly? It's going to cleave at this point, plus. So what do you get? Right? So here you're going to add, or this whole reaction occurs in the presence of barium acetate. Valency of barium is 2, acetate is 1. Again there is a cleavage of the bond here. Now what will happen? This hydrogen goes and adds to this carbon. This acetate group comes and adds to this carbon. Now what do you get? I'm going to get this way. Let's see. CH2 CH. Okay, I need to write double bond first. Let us write that and see what happened. CH O CO CH3. Further, suppose if you're further adding here only, if you're adding 2 moles of this here, the same case, or to this only. Suppose further I want to add CH3 COOH. Again there is a cleavage of the bond here. There is a cleavage of the bond here. This hydrogen goes and adds to this carbon. You get CH3, and this minus goes and adds to this. Now what do I get? I get CH. OCOCH3 is one case, and the second one OCOCH3. Done, isn't it? Yes. So this is the reaction with acetic acid. In the previous video we've seen what is Kekulé structure, what are the different objections made to Kekulé structure now, but finally the Kekulé cyclic structure was accepted, though we had certain objections. We'll also be seeing in this video today the other structures what were proposed for benzene. Right. So when structure of benzene was proposed, like Kekulé after giving the acceptable one, then later on the most acceptable one was the orbital diagram based on the concept of resonance, delocalization that we'll be studying, right? So benzene structure was, or it was proposed by or given by different or if I have to say scientists. Done. So the first structure which was given means other than Kekulé was Dewar structure. Okay, so we will first write the names and then draw the diagrams. After Dewar structure, it was Claus structure. Claus structure also was given. After that, Armstrong structure was given. Armstrong structure. After Armstrong structure, Ladenburg structure was given. Ladenburg structure. So these were different structures, but they were not accepted. After Ladenburg structure, we'll be also seeing one more, that is Thales theory or Thales theory. This also was given. Right, let's see. So according to Dewar structure, the benzene structure, according to Dewar, the structure of benzene looked like this. This is what he has given. So what did it have? It has a very long, para bond. See here, this is para position, isn't it? This is ortho, this is meta. So here, what does it have? It has a very long para bonded means para bonds. They're connecting opposite carbons, this carbon and this carbon. So as all the carbon single bonds in benzene are identical, so we said all the bonds, since it's H6, all are identical, but here there is a long pi bond here, so there's a long para bond. That's why this structure was not accepted. This is not identical, isn't it? This is again long and indifferent. So what made it, why didn't we accept this? Because of presence of para bond Okay, and that too para bond is how? It's a long para bond. Presence of long para bond between carbon and carbon. But in benzene, all are identical. That's why this is not accepted. Now when we come to clause structure, how does clause structure look? Clause structure, basically this is also cyclic only, but this is a ring. Here, yes, join all these bonds. This is clause. So what is the same reason? All the bonds are not identical. That's why this also bonds are not identical. That's why this is also not accepted, just like Kekulé. Then came into existence, or this assumption was given by Armstrong. What did Armstrong, how does Armstrong structure look? Armstrong structure, this is also cyclic only, but this is how he has given. This is Armstrong structure. What did he say? Each carbon, in this particular thing, has a valency which is not satisfied, isn't it? In such case, how does it form? It has to form compounds like C6H5X. Such a product was not formed by benzene, isn't it? That's why it is not accepted. Now when I come to Ladenburg structure was looking like this. This is Ladenburg structure. So again, this is not planar. We said benzene or this arene has a planar hexagonal cyclic structure, we said. So 3 words: planar, hexagonal, cyclic structure. These 3 are the characteristic feature of benzene. But is it planar? Not. It is not in one plane, isn't it? So this was also rejected. Not planar. Hence, this is also rejected. Then came into one more theory which was given by Thiele, or with Thiele we say, Thiele's theory. So he has given a structure or proposed a structure for benzene. What did he say? He said that free valencies, whatever 3 pi bonds are there, 3 free valencies of neighboring carbons interact with it. He said whatever, like 3 valencies, whatever are there, they are going to interact and they get neutralized. Now what is the structure he's given? Let's draw that first. This also, he has picked up a cyclic hexagonal structure like this only. One more benzene. Then he said the 3 valencies here, in this case here, in this case here. Now here it is between this bond and this bond, or this bond and this bond, 2 and 3. Now to shift that, valencies are here, valencies in here. That means 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Here the valencies are between 2 and 3. This is 2 and 3. Then between 4 and 5. Then between 6 and 1. Here it is between 1 and 2, between 3 and 4, and between 5 and 6. Both are different, isn't it? Now what he said is the partial valencies, whatever it is, the free valencies are there, not this one. He said the free valencies of neighboring carbons, this free valency and this free valency, they interact and they get neutralized, he said. Right? So, and he also said because they get neutralized, benzene will not undergo addition reactions. That is what he said. Benzene will not undergo addition reactions because the free valencies, okay, let us read that. Free valencies of neighboring carbon atoms, get neutralized. So because of this free valencies of the neighboring carbon atom, because they get neutralized, benzene does not undergo addition reactions. But what does it undergo? It undergoes addition reactions but undergoes substitution reactions. So addition it will not prefer but undergo substitution reaction. This is the main reason, because they get neutralized. Once they're neutralized, where will it add? It will not add, isn't it? You can't add. So that's why it will not undergo addition but undergoes substitution reaction, which is what he said. This is called Thiele's theory of partial valencies. So that is right, Thiele's theory of partial valencies, like this. But this theory also failed. Why did it fail? When they have applied the same concept to cyclooctatetraene, okay, so partial valencies, he said partial valencies get neutralized, but in case of cyclooctatetraene, so let us write that failures of Thiele's theory. So the same concept, only partial valencies getting neutralized. So based on that concept, when this was applied to what octatetraene, which octatetraene? Cyclooctatetraene. When this was given, or when this concept of partial neutralization was applied to this, what will happen? The molecule, it has undergone addition reactions. It has undergone addition reactions. That's why they said there is no chelation, means there was no neutralization happening in this, between neutralization of partial valencies and failure to undergo addition. This theory was not accepted. So that means there was no partial valence, means there was no neutralization happening. They said because this is cyclooctatetraene, though it has pi bonds, alternate pi bonds, it has undergone addition. Then they have ruled out that no partial valencies were neutralized. As these are not neutralized, what happened? This theory were not neutralized. So hence this theory was not accepted. This is what is the concept for its failure. Right? Fine. So such different theories were given other than Kekulé. Now we'll be seeing what did Levine and Cole, what did they do? So Levine and Cole, they've taken this structure, Levine and Cole. What do? They've conducted ozonolysis experiments. So what did they conduct? They conducted ozonolysis experiment on orthoxylene. We'll see what it is. And after taking this orthoxylene, they said that Kekulé structures are acceptable for benzene. Because of this orthoxylene ozonolysis experiment, this was a support to Kekulé structure. They finally confirmed that. They confirmed and they proved also. They proved or confirmed that Kekulé's structure are acceptable. This is what they said. Because of this, what is the orthoxylene now? This is your benzene ring. 1 CH3 this is CH3. Now alternate pi bonds. Okay, not neat here. Okay, this is one. This is orthoxylene. Xylene is 2 methyl groups. Now I'm going to shift the same pi bonds in this direction, but CH3 groups at the ortho position only. So this is orthoxylene. So when they have formed, or when they have done the ozonolysis reactions, I've already shown you what is ozonolysis, addition of ozone. So this addition of ozone, it has given us a different products. Because of this product formation, they said Kekulé structure is confirmed. What are the different products? So ozonolysis of orthoxylene has given 2 moles of, I'm not showing these reactions, I'm just writing the products here. This is what? It has given 2 moles of methyl glyoxyl. Okay, this is what? Methyl glyoxyl, methyl glyoxyl. It has given 2 moles of methyl glyoxyl. After that, the ozonolysis product of this has also given CH3CHO. What is this? This is glyoxyl. Apart, this is for first one. These two are given by the first compound. The second compound, whatever we have taken, the second compound has given us this product. I have done the ozonolysis. I am directly writing the products here. What is this? This is dimethyl glyoxyl. Dimethyl glyoxyl. And the second product is also given. Now this is glyoxyl. How many? 2 moles of. Let us not write 2 moles. It is only glyoxyl. So it is proved by Levine and Cole that orthoxylene gives so many products. What is the ratio? They form in the ratio of 3:2:1. It is only proposed that only when orthoxylene exists as both Kekulé structure, the actual structure is a resonance hybrid, which we'll be studying. So this experiments prove, they have given a perfect proof that Kekulé structures are the real structure of benzene and its derivatives. Hope you understood, students. So what did I say? Orthoxylene exists in both Kekulé structures. Well, we have shifted and shown, isn't it? So here in this previous this one, here I've shown here. See, I'm shifting the pi bonds because this, after shifting the pi bonds, this is giving 2 products, and after shifting this second one also is giving 2 products. So because of this, it is proved that Kekulé, both the structures are acceptable. Thank you for watching, students. Students, to one more session of your structure of benzene. So first, we have studied the Kekulé structure. We have seen the objections of Kekulé structure. Then I've taught you the different structures given by Dewar, given by Claus, given by Armstrong, Ladenburg, right? Isn't it? I've also given you what is Thiele's theory. Then I've taught you how did Levin and Cole prove that Kekulé structure is acceptable structure. So what did they do? They perform ozonolysis experiments, isn't it? On xylene, they've done ozonolysis experiments on orthoxylene. So both have given 2 products, right? In the ratio of what? 3:2:1. So today in this video, I'm going to teach you the modern view of structure of benzene, right? So when I have to take the modern view of structure of benzene, this was given under, studied under 2. What is that? One the resonance concept and one is cyclic delocalization. This is an orbital diagram, right? So when I have to speak about the modern views on structure of benzene, right? So let us write resonance, right? So when the concept of resonance was applied, right, to structure of benzene, because Kekulé has already given the molecule, benzene molecule structure, isn't it? Right? The concept or the main word or the concept of stability of the compound was explained. So this concept of resonance means it explains, what does it give us? It could explain, it gives us the stability of benzene. This is the main thing. So what did Levin and Cole also say? Kekulé structure was found to have been resonating structure between 2. What are they? They said this is your benzene C6H6. So 1, leave it, 1 more, leave it, 1 more. This is having a resonance structure. It always has a resonance structure. Here, suppose if I number this 1, 2, 3, 4, 5 and 6. The pi bond is between 2 and 3. Now number this also 1, 2, 3, 4, 5 and 6. So here it was between 1, 2 and 3. Now let it be between 1 and 2. Leave this bond 3 and 4. Leave this bond 5 and 6. So Kekulé structure was found to be resonating structures of benzene. What do? They differ in the position of pi bonds. So the actual structure we are going to draw the resonance hybrid also. So cyclohexene has only 1 pi bond. isn't it? So how much energy does it it releases? 28.6 kilocalories per mole during hydrogenation. So benzene has how many pi bonds? 3 pi bonds. So during hydrogenation, how much does it release? Means hydrogenation means you're adding hydrogen to this. You're breaking these pi bonds and you're adding hydrogen. So during hydrogenation to benzene, as I've shown you in the first video, because of pi bonds, 3 pi bonds, 3 into 28.6. So what is this 28.6? 28.6 is a energy released when hydrogen was added to cyclohexene. So 3 into 28.6 kilojoules per mole. It comes to 26. Okay, this is 85.8 kilocalories per mole. So much energy was released when hydrogens were added. How many hydrogens? 6 hydrogens were added to benzene. Yes, but it was means according to the value it has to release as much. But how much was it found to be? It was found to release 49.8 kilocalories only. There was a gap of almost how much? But found during hydrogenation, this according to cyclohexene. For this to undergo hydrogenation, how much did I say? Hydrogenation, it took 28.6 kilocalorie per mole. So, but the same thing I'm applying to benzene. So 3 pi bonds, 3 into 28.6 comes to this. But when I take the actual value of this is actual value. I should say this is an experimental value. Okay, what the value of this? Let us not write actual and get confused. Value observed was 49.8 kilocalorie per mole. So how much was the gap? There was a gap of 36 kilocalories. 36 kilocalories per mole. So between the theoretical value and actual value. So the theoretical value and the actual value. So this I've erased out. So this is a theoretical value and an actual value. The observed value difference is 36 kilocalories per mole. So this energy is called resonance energy. Resonance energy. Done. So 1 mole of benzene, how much does it possess? It possesses 36 kilocalories energy less than it should contain, isn't it? So the energy, how much ever benzene has spent by 1 mole of benzene molecule, that exhibits, that whole concept explains the resonance energy in benzene. So we will be seeing a graph on resonance energy also. We'll be understanding that. So that gap which I said is a resonance energy. We will further see in the next video, right? Now, after this resonance energy or concept of resonance, we'll be studying what is cyclic delocalization. Cyclic delocalization. Now, in benzene, when I have to draw the structure, there are 6 carbon atoms in benzene, isn't it? So 6 carbon atoms. 6 carbon atoms. And these 6 are carbon atoms. What is the hybridization? Because there is a double bond. The sp2 hybridized. sp2 hybrid orbitals. Correct. Now each carbon atom has how many? Has 3 sp2 hybridized orbitals. Correct. And what do? They're going to form 3 sigma bonds according to the structure. So let us draw the structure and see. Cyclic structure, we said. In benzene ring, we are studying the orbital diagram. This is the hydrogen, hydrogen, hydrogen. We said all hydrogens are at the corners, isn't it? Hydrogen. So these carbons, whatever are there here, all are sp2 hybridized. And what does the carbon do? It's going to form each carbon, the sp2 hybrid orbitals, they form 3 sigma bonds, isn't it? They form sigma bonds, 2 with neighboring carbons and 1 with hydrogen. This carbon, once again, this carbon undergoes sp2 hybridization with this hybrid orbitals with this one. There's 1 carbon here. This will undergo sp2 hybridization with this one and this one. And this one with one bond with hydrogen. How does this look? This looks like this. Correct? Yes. Yeah. So each carbon atom, whatever is there, has a p orbital extending above and below. After forming sp2 hybridides here, the leftover one, it forms above and below. Means that p orbital which is left out, that it forms, or it is aligned in right angle triangles in this way. So this particular orbital diagram, let's see what does it do now. It's going to form a pi bonds according to Kekulé structure. These p orbitals overlap laterally, in two different forms. According to Kekulé, basically we said this carbon is sp2 hybridized, right? Then we said the carbon has how many sp2 hybridized? 3. Means each carbon has 3 sp2 hybrid orbitals. Each carbon has 3 sp2 hybrid orbitals. Correct? That is what we have seen. After that, each carbon atom, whatever is there, it's going to form, each carbon has, or it forms 3 sigma bonds with neighboring atoms. This carbon atom forms sigma bonds with this carbon, forms sigma bond with this one, and also forms sigma bond with hydrogen. So what does it do? It forms a sigma bond. Done. Now after that, each carbon atom has a p orbital which is extending above and below. Isn't it? So first point will be this. Then you will write 3 sigma bonds in that 2 with neighboring carbons and 1 with hydrogen atom. 2 and 1 hydrogen atom. Done. So all the 6 carbon atoms and 6 hydrogen atoms are connected in the same plane. Correct? Let us write that. All carbon and hydrogen are connected in same plane. Done? Yes. Now according to Kekulé structure, let me take the same page. According to Kekulé structure, how does it look like? This one. All the structure is not so neat. I'm just drawing it as a rough diagram. This is the one which is above and below. Here also, fill that above and below pi bond, the p orbital 1. Now, according to Kekulé structure, there are 2 different ways of forming Kekulé structure. One is the pi bond exists in this one, first one, this one, and this. So this is one way of forming pi bond. Next one, pi bond can form between these 2 p orbitals. Pi bond can form between these 2 p. Pi bond can form between these 2 p. See this. There's a difference. This is forming a bond here. This there is no bond. These 2 are forming a bond here. This there is no bond. These 2 are forming a bond here. These 2 are not forming a bond here. So there's a shift of pi bond according to the with the Kekulé structure. We have shown that concept. Right. Now these structures have localized pi molecular orbitals. Correct. So instead of 2 neighboring p orbitals, now if the p orbitals of all the 6 carbon atoms, they overlap laterally, means one above and one below. How does that look? Right? This is according to Kekulé structure. Now if p orbitals, let's make one more diagram. If p orbitals all 6 carbon atoms. 6 carbon atoms overlap laterally. Suppose if they overlap laterally, how do they overlap laterally? Above and below. If they overlap like this, how does this look? The whole diagram, it looks like a donut. Maybe okay, let me try. Right, so this whole thing connecting on the top, one over. Now connect the bases one. Right, how is it looking? This is looking basically like an electron cloud above and electron cloud below. If it is like this, electron cloud is above and electron cloud is below. So above and below. It's looking in the form of a donut, isn't it? Donut, we have exact shape, form of donut. So they're going to form a ring above and below. So this is called cyclic delocalization. Cyclic delocalization, this concept. So this cyclic, as more nuclei attract pi electrons, the species becomes more and more stable. So now the pi electrons have a lot of space, isn't it, to move. They are delocalizing, the cyclic delocalization. So what happens? The molecule, whatever is there, it's going to spend more energy for the movement and possesses less energy, right? It will use it only for localization only. So on the whole, when I see the energy of the system is less because of this cyclic thing. Once again, I'm repeating. Now there's a lot of space for the pi electron to move. So when the pi electrons are moving, what will happen? The molecule, benzene molecule, whatever is there, it spends more energy. Let us write first, more space for pi electrons to move. So when there's a lot of space pi electrons to move, what will happen to the system, whole system? The molecule spends more energy. For where does this use more energy? Where does this spend? It's going to spend this energy in movement of the molecule, means movement of the pi bonds only, right? So what does this molecule do? This molecule spends more energy for movement and has, on the whole, if I see, and has less energy than it should, okay, because it is using of the energy in movement, less energy. Hence, what will happen? Hence, stable. This is where it ends, because it is using in the movement of the pi bonds, delocalization. The whole energy of the whole system is stable. Whichever has less energy, that means it is more stable, isn't it? So this is how your orbital diagram was explained. Hope the concept is clear, students. So whenever you're writing the orbital diagram, you have to remember carefully. You'll be explaining the sp2 hybridization structure, 3 sigma bonds. Then we explain about how they are connected in the same plane. Then this also I have shown you cyclic delocalization. This forms a donut. And after that, you should show the positions of the Kekulé structure, and finally explain it as stable, right? So thank you for watching, students. I'll meet you again with the next one, that is Huckel's rule. To one more session of your Huckel's rule, that is I have taught you in the previous video what is Kekulé structure, how are we applying, or what is a modern view of explaining the orbital diagram of benzene. Now, in this video, I'll be teaching you the most important rule which is applied for the aromatic or the alkenes compound, that is Huckel's rule. Right. So, what have we learned till now? We said, according to Kekulé, it has planar hexagonal cyclic structure. That is what Kekulé said. So, then after that, Alkyl came and just he has proposed that the planar ring systems, okay, whichever is planar ring or cyclic structures. So this planar ring structures, what do they have? They're going to show 4n plus 2 pi electrons. Okay, they're going to possess, what do they possess? 4n plus 2 pi electrons in them. So whichever has 4n plus 2 pi electrons, they are considered to be. So planar ring structures possesses 4n plus 2 pi electrons, and whichever possesses 4n plus 2 pi electrons, those are considered as aromatic compounds. Now that means, so here this 4n plus 2, this n values will start from 0, 1, 2, 3, 4, it goes on like this. Now let us apply this. So suppose if I take the first one, suppose if n is equal to 0, let us apply this value 4n plus 2. It's nothing but 4 into 0 plus 2 pi. This becomes 2. If n is equal to 1, same I'm applying, how much do I get? I get 6. Suppose same thing, if n is equal to 2, this becomes 10. Same thing if I take n is equal to 3 value, same I'm applying this, I'll be getting 14. It goes on like that. If n is equal to 4, then the Huckel's rule, it becomes 18. So these numbers 2, 6, 10, 14, 18 are called Huckel's numbers. So what are they? I've got here 2, 6, 10, 2, 6, 10, 14, 18. What are they? They are called Huckel's numbers. Fine. So compounds having planar ring structures and with Huckel numbers of pi electrons, they are called aromatic compounds. Remember that. So once again, let us note one important thing. What is that? He says compounds having planar ring structure. Okay, that is already shown. And that planar ring structure should contain with Huckel's numbers. These are Huckel's numbers which we have got just now. And they should have Huckel's number. Planar ring structures, there is Huckel's number. Oh, what is this? Huckel's number of pi electrons. Then they are called or considered to be aromatic compounds. This is where your Huckel's rule apply. So the 6, what about 6 pi or atomic orbital, 6 carbon atom, all these we saw, isn't it? The structure, how it is moving around, how it is coalescing, everything we have seen. Right? So this Huckel's rule, very important for benzene structure. So remember this. If your teacher is asking you, just this concept is enough for you all. This is the Huckel's rule. This is how it applies. So whichever follows the Huckel's rule, and they should have planar structure as well as Huckel number, then they are called as aromatic compound. So these are the structures of benzene, students. So we will also see one important concept with this only. That is sources of aromatic compounds. I'll add the concept here only. Sources of aromatic compounds. So from where are we getting aromatic compounds? You can note this also as an introduction to preparations of benzene. So when I have to speak about aromatic compound sources, suppose when coal tar, you know coal tar, this coal tar, when this is subjected to distillation process. So we have already studied distillation in grade 10, isn't it? When it's subject to distillation process, what happens? This is going to release different fractions. These different fractions, what are they? They are going to form at different temperatures. So different temperatures they're going to form. And from this different fractions, we are going to get different aromatic compounds. The different aromatic compounds like benzene, toluene, naphthalene, xylene, phenols, anthracene, phenanthrene, all these compounds. Suppose if I have to see how are they formed. Let me take a fraction. I told you, during coal tar is taken, it is undergone distillation, it forms different fractions at different temperatures. So if I take the fraction, here let us write at the temperature at which it is collected and substances which are present. If I take this account, okay, lines are not straight, don't mind please. Yes. Suppose the fraction here which I am going to take, that is light oil. This light oil, what temperature is it? It is collected? It is collected up to 180 degrees centigrade. Then what is the substances present in that? The substances present are benzene. The substances present are toluene, xylenes. Done. Suppose if I take middle oil. Now this is light oil and now I am collecting middle oil. Now here the temperature from 180 after that. Well, that is 180 degrees centigrade to 240 degrees centigrade. Then the product which I get or substances present in that are naphthalene and phenols. Now if I take very heavy oil, light oil has benzene, toluene, xylene, middle oil has naphthalene and phenols. If I take heavy oil, so heavy oil is beyond this one temperature, that is 240 to 270 degrees centigrade. Then I am going to get phenols. Suppose if I take green oils, or this is also called as anthracene oil. So anthracene oil from 270 to 340 degree. What do I get? The product or substances which is present is anthracene or phenanthrene. Suppose the leftover, now light oil is over, middle oil is over, heavy oil is over, and we have collected green oil. Listen, the leftover residue, whatever is there. So the leftover, that is that substances. What are the substances present? Temperature, this is the last one. Whatever we get residue, that is called pitch. Means that one, pitch is used for road surfacing. That black color one, road surfacing. This is what is your source. So we have studied the Huckel's rule. We have seen the sources of aromatic compounds. I'll be meeting you again with the preparations as well as properties of benzene. Thanks for watching, students. Students, in the previous video, I've taught you what is Huckel's rule. I've taught you what are the different sources of aromatic compounds. Now, we'll come back and learn the preparations of benzene. Right. So, benzene structure also we have learned. Different types of structures. Please watch the previous video. So, whenever I have to prepare benzene, the first important thing is from coal tar fractions. This is what I have taught you. So, I already gave in the previous video light oil, middle oil, heavy oil. So, I have also given you the temperatures at which it is, means what temperature do we get the required product. So, what do I do? First thing, preparation, that's from coal tar fractions. So, please watch the earlier video. I have given the information about this. So, here, what do? They take the light oil which we have got. This light oil is washed with acid. Washed with acid and base. Why do they wash with acid and base? Here, by washing with this, we are going to remove acidic and basic impurities. Whatever impurities are there, both acidic and basic impurities, they are washed off. Done. From here, this is finally taken and it is washed with water. Once it is washed with water, they're going to take it to a distillation tank. And in this distillation tank, what is the temperature maintained? Means according to the product required. So we very well know up to 180 degrees, which I have shown you in the previous video. Up to 180 degrees, your benzene, means benzene, toluene, xylene, all you'll get. But here we are preparing benzene. So the fraction, whatever is distilled, once it's done, here at 180, exactly at 80 degrees, we are going to get benzene. This is how it is prepared. When you would take this temperature from 80, 90, 100 like that till 180, you get other products like toluene and xylene also. Right? This is one method of preparation. Now, let us see the next method of preparation of benzene. I can prepare benzene by decarboxylation reactions. Decarboxylation of carboxylation of sodium benzoate. Decarboxylation of sodium benzoate. So what is sodium benzoate? Basically, see here, C6H6 is benzene. So I'm going to take C6H5, Cu over Na. Now I'm going to add soda lime to this. Soda lime is a mixture of sodium hydroxide and calcium oxide. And you're heating it. So let us write this. This is a sodium benzoate. Why did we take this? Because sodium benzoate. When I take soda lime to this both and you're heating it, in one of the video I also showed you what is the role of soda lime. Why do we take CaO? Please watch that video. Here what happens? Na2, just observe carefully. Na2 CO3 comes out. So the first product which comes out is sodium carbonate. Now what is left out? This hydrogen from here goes and adds to this benzene, so or say 6H5, and finally forms a product called benzene. This is what we are trying to prepare. So decarboxylation is removal. Now what this happens further when you heat? This will form sodium oxide plus carbon dioxide. That's a decarboxylation. Now the next method of preparation of benzene. Here I'm going to take benzene sulfonic acid. Benzene you're preparing from benzene sulfonic acid. So what is sulfonic acid? Let's see. See here. Benzene, the formula, it is C6H6, but here C6H5. Sulfonic acid is SO3H. What is the name? Write the name of this compound. Benzene sulfonic acid. To this benzene sulfonic acid, what am I going to do? I'm going to heat it with dilute sulfuric acid. Okay, but dilute sulfuric acid I'm adding. So when you add dilute sulfuric acid to this, what will happen? Just see here, observe carefully. This hydrogen, okay, let me take this. Yes, yeah, and this hydrogen goes and adds to this. So I'm going to get H2SO4 is out. Benzene is prepared. Right? So hydrolysis using this, and finally I'm getting sulfuric acid out. So there is one more method of preparation of benzene. So I'm going to take benzene here. I'm going to use a word called BDC. What is BDC? BDC is benzene diazonium chloride. Let us write the formula. B stands for benzene. D stands for diazonium chloride. So I'm going to take this BDC. Let's write the formula. Formula is C6H5. Okay, benzene. Basically it is C6H6, but we have taken out one hydrogen and added this group. So C6H5. Di means 2. That is diazo. Azo means nitrogen group. And chloride. C6H5N2Cl. This is BDC. This one. Now to this BDC, I am heating with hypophosphorus acid. I'm heating. So what does this hypophosphorus acid does? It immediately expels out this nitrogen gas. This nitrogen gas, whatever is there now, it expels out. After that, immediately one hydrogen comes out with this as HCl, and the leftover hydrogen goes in H6H6. Basically H3PO2, it's used to add hydrogen. That hydrogen H2, this H2 whatever is there now, one H comes out with the Cl as HCl, one more nitrogen gas expels out, and this hydrogen expels out, and this hydrogen goes and adds to this, forming benzene. So we have got benzene compound also done. This is no preparation. Suppose if I have to further prepare, I can prepare benzene from, see here, from phenyl magnesium bromide. Okay, so what is this phenyl magnesium bromide? We will see. Phenyl, okay, C6H6 is benzene. Now I am taking C6H5 MgBr, phenyl magnesium bromide. Now what am I going to do? I am going to treat this with water. Immediately, just see here, this magnesium bromide breaks and this comes out as Mg, OH and Br, and the leftover comes and adds here as benzene. This is benzene. I can also prepare benzene from acetylene. So let us write that. Benzene from acetylene. This you can use it as a conversion question also. How can I prepare? What I do is, acetylene, what is the formula? What is? This is acetylene. The same thing, I think I can write it like this. Yes. Now I'm going to take acetylene. I'm going to introduce in the red hot iron tube. I've shown this reaction already in polymerization also. Red hot iron tube. So here I'm going to take 3 of this. It's basically like this. H, H, H. This is going to shift here during polymerization. This is going to shift here. This is going to shift here. And finally, this forms benzene, C6H6. Like this. This is called polymerization reaction. Now, further, I can prepare benzene using, or more reactions if I see. Or important thing. I can further prepare benzene from N-hexene. So, it is right, one more conversion. Benzene from N-hexane. One more thing, we will write the headings and keep. I can prepare benzene from phenol also. I can also prepare benzene from chlorobenzene. So let's see what it is. So benzene from N-hexane. So what is N-hexane? N means hexane. Hexane means 6 carbons. 6. It is an alkene. CnH2n plus 2. So C6H14 is N-hexane. To this N-hexane, when I am introducing CrO3 or Al2O3, what will happen? And you're heating it. When this reagent is present, immediately 4 2s are 8 hydrogens are out. What do? They come out or they get evolved, or they get released in the form of hydrogen gas whenever you're adding this. So in C6H14, you're taking 8. So 14 minus 8. This becomes C6H6. For how many hydrogens? 4 hydrogens come out in the form of evolution, in the form of gas. This is called aromatization. This reaction is called aromatization. That means from a straight chain, it has undergone a ring. Straight chain, it has undergone a ring. That's why it's called aromatization reaction. Now, if I take phenol, what is phenol formula? This is phenol. C6H5OH is phenol. Now, if I have to introduce, means I have to take, what should I do? I have to prepare benzene. Let's try this. This is C6H5OH. If I add one hydrogen to this and remove, means this hydrogen if I add and take out oxygen. So take out oxygen. Addition of hydrogen or removal of oxygen is reduction, isn't it? So I'm going to use a reducing agent like zinc. What am I going to do? I'm going to heat it. Then automatically benzene is out, C6H6 is out because this hydrogen, and ZNO comes out. That's it. Now benzene and chlorobenzene. I'm going to take chlorobenzene, Cl, and I'm going to use reducing agents like nickel and aluminium. Okay, so when I'm using reducing agent, or this is a nickel aluminium alloy, isn't it? This is an alloy, mixture of two or more metals. So this alloy is taken in sodium hydroxide solution. When you're taking this in sodium hydroxide solution, what will happen? This is a reducing agent. We are going to add hydrogen to this. So what will happen? HCl comes out, and this hydrogen adds to this. So benzene is formed. That's it. So we have seen the different preparations of benzene. So what preparations we have seen? We have seen it from benzene, sulfonic acid, from using soda lime decarboxylation. I've shown you the reduction. I've shown you the conversion of benzene to hexane, hexane to benzene, phenol to benzene, chlorobenzene to benzene. So these are the different preparations of benzene streams. Let me come back and meet with the properties of benzene along with the mechanisms. I'll be teaching you with the mechanisms the properties of benzene. Thank you for watching. So welcome students to the properties of benzene. In the previous video, we've seen how to prepare benzene. So I've taken different reactions to explain that. Please watch the previous video and just come back to this. So properties of benzene, both we'll study the physical as well as chemical properties. So when I speak about properties of benzene, I hope you would have seen it in the lab, isn't it? So benzene, what is the color? Benzene is a colorless liquid. Correct. So what is the this an odor of that? It is characteristic odor, a different odor. So with the characteristic odor, colorless liquid with characteristic odor means smell. And what is the boiling point of benzene? Benzene boiling point is 80 to 82 degrees. That's why in distillation, when we did distillation, before 80 degrees only, we have got the benzene. It means it starts boiling and vaporizing. When I see the structure of this, it is a non-polar molecule. And if it is non-polar, or automatically immediately we will write it is insoluble in water. If it is polar, it will be soluble in water. If it is non-polar, it is insoluble in water. So there is no force of attraction between them. No force of attraction between them. Done. So whenever you're burning benzene, it's going to burn with sooty flame, isn't it? With sooty flame. It will maximum, as we said, it will maximum undergo substitution reactions, but very few addition reactions. Undergoes few addition reactions. Right. So when I have to see, I've listed out the chemical properties. See here. So the different chemical properties which I'll be showing you with mechanism. So it will undergo very few addition reactions like hydrogenation reaction, or it will undergo chlorination reactions. And after that, I'll be teaching you oxidation reactions. So whenever you're studying oxidation reactions, you should study, you should explain in the presence of strong oxidizing agents. What are they? Potassium permanganate, alkaline potassium permanganate, or acidified or acidic potassium dichromate. And you can also use in the presence of a catalyst, that is vanadium pentoxide as a catalyst.
I'll also be showing you the Ozonolysis reaction, very important, and I'll be showing you the formation of glyoxal. There's one important reaction called Birch reduction. This reduction I'll be showing in the presence of ethanol and sodium metal. I'll be showing the mechanism of this. Then I'll be taking you the most important concept of benzene, that is electrophilic substitution reactions, that is halogenation, nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylation. I'll be showing the mechanism for everything. Then I'll be teaching you what is Gatram and Koch reaction as well as Gatram and reaction. So hope students, I'll meet you again with the first reaction, that is benzene addition reactions, in my next video. Thank you for watching. Students, to one more session of your properties of benzene. In the previous video I've taught you what is the boiling point of benzene, what is the physical state, that is physical nature, that is it's a liquid. Then we've also seen it is a non-polar molecule, hence it is insoluble in water. Now in today's video we'll be learning the benzene addition reactions, and gradually I'll be taking into substitution. As we have seen, benzene only two addition reactions it undergoes. Beyond that, it undergoes electrophilic substitution reactions. What is the reason? Because of the delocalization of pi electrons. That is what we have seen. Now in today's video, we'll be seeing the benzene addition reactions. As I said, only two of them. The first one is, let us divide the page into two equal halves. So benzene, basically, because of the presence of pi bonds, alternate pi bonds, suppose if I try to add hydrogen to this hydrogenation reaction, now the same benzene I'm going to take and allow it to undergo chlorination reaction, that is addition of chlorine. So whenever you are adding hydrogen, remember you require a reducing agent like a metal, that is nickel. I'm going to heat it to 180 degrees. The same chlorination, whenever you're performing chlorination, this has to occur in the presence of sunlight. Then only the chlorine will get added. In the exam, suppose there is no light given, please write no reaction. So light is important here. So how many pi bonds are there? 1, 2, 3. So 3 hydrogens I'll be adding. How many pi bonds? 3. So I'll be adding 3 chlorines. So what happens when 3 hydrogens are added? This bond is broken. This bond, and these hydrogens, 3 to the 6 hydrogens, this is broken. See here, 1, 2, 3, 4, 5, 6. All the 6 are broken, and means 3 pi bonds are broken, and these hydrogens add to this. What do I get? I get a compound like this, because they are broken already. These hydrogens got added to this. So what is this? This is C6H6. Now to this 6, I am adding 6 more hydrogens. So this becomes C6H12. So this is the compound. What is the name of this compound? This compound is benzene, and the name of this compound is cyclohexane. Cyclohexane. So here also, suppose if I take say in benzene, there are 3 pi bonds, so I'm adding 3 chlorines. So what will happen? This in the presence of light, it breaks open. Means the pi bonds are broken. How does it add? So everywhere there is carbon, 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 and hydrogen everywhere. Now to this, the hydrogen which I was adding, see here, opens up, and how many chlorine? 6. So 3 to the 6, 1 chlorine adds here. Hydrogen, that bond breaks up, 1 more chlorine. Hydrogen, 1 more chlorine. Hydrogen, 1 more chlorine. Again, the same thing, hydrogen, 1 more chlorine. Hydrogen, 1 more chlorine. Now what is the formula for this? This is C6H6. Now let us count how many carbons? C6. 1, 2, 3, 4, 5, 6. How many hydrogens? 6 hydrogens. 1, 2, 3, 4, 5, 6. How many chlorines? 1, 2, 3, 4, 5, 6. 6 chlorines. So this is called BHC. What is the full form for BHC? BHC stands for benzene hexa, there should be a small letter, hexachloride, or it is also called as gemaxine. Gemaxine, we call it as gemaxine, no? Where are we using? We are using gemaxine in the form of insecticide. To kill insects, we use gemaxine, isn't it? And small ants also, right? So this is also called as 666 is also gemaxine. This is also called as lindane. So all these are names for gemaxine. So this occurs in the presence of sunlight. So hydrogenation gives me benzene to cyclohexane, and chlorination gives me benzene to gamaxane. So 9 isomeric forms are available for this. So beyond this, benzene does not undergo any other addition reactions. Now let's come back and see the next type of reaction of benzene, that is oxidation reactions. Right. So whenever you're speaking about oxidation, you require strong oxidizing agents. Remember that. So strong oxidizing agents, as we have seen in the earlier video also, what are they? Oxidizing agents include alkaline KMnO4. Let us write that. So that means in the presence of an alkali. So oxidizing agents, what are we using? I'm using alkaline KMnO4, potassium permanganate. I'm using one more, that is acidic K2Cr2O7. That means it is nothing but K2Cr2O7 in the presence of an acid. This is what it means. You can also use perform oxidation using hydrogen peroxide. But whenever you're using this, you're using a catalyst, that is vanadium pentoxide. You know, it speeds up the reactions. V2O5, that is vanadium pentoxide. Right. In the presence of these, benzene undergoes oxidation reactions. So oxidation is nothing but addition of oxygen, isn't it? So I'm using oxidizing reagents. So this is the catalyst which I'm using. So when you're adding oxygen, I'll write the product down because there's no space. When I'm adding oxygen to this, the bond breaks and it forms this is the product formed. This breaks up, oxygen adds here, there are carbons already there, right, and oxygen, and finally forms malic anhydride. This is called malic anhydride. You will also further perform oxidation reaction of benzene using hydrogen peroxide. I'm going to take benzene, I'm going to add hydrogen peroxide. So I said this is going to add oxygen to this. So the pi bond, whatever is there, breaks up, opens up, like means it adds OH. So the conversion of benzene to phenol, you can use hydrogen peroxide. Now when I have to come back to the next type of reaction, that is ozonolysis. Ozonolysis also comes into oxidation reaction only. So what is ozonolysis? We have already seen the mechanism. Ozonolysis is addition of ozone. This ozone, and further what we do, once we add ozone, we are going to allow it to undergo reduction, correct? So in the presence of zinc. So let's see how it goes. First of all, I'm going to take benzene, right? Hope it is clear, students. To this benzene, I am going to add ozone, correct? Ozone is O3. So how many hydrogen? So 3 hydrogens. So I'm going to get 3 moles of ozone. How does this look like? It looks like this is your thing. Correct? Now see, the bonds are broken. This is a 9 oxygens I need to add. So this is a benzene ring. Just see here, I'm going to add 1 oxygen, 3. See here, ozone is 3 here, O and here. Done. Next one, oxygen, oxygen, oxygen. How many are over? 3 plus 3, 6 are over. 3 more are there. Here at this point, oxygen, oxygen, oxygen. Correct? Done. So 1, 2, 3, 4, 5, 6, 7, 8, 9. These are 9 oxygens I've added. What is the name of this compound? This is called benzene triuzonoide. It's called benzene triuzonoide. Now it further cleaves. Where does it cleave? Just see. You can hold your pen like this and exactly it cleaves here. After that, where does this cleave? It's going to cleave. It starts cleaving in this direction, and there's one oxygen here beyond this. Now again, this is over, isn't it? Now immediately start here. This is going to cleave exactly here. One cleavage, is below this oxygen, one more cleavage is below this oxygen, one more cleavage is below this oxygen. It breaks up, and finally what are we going to do? I said we are going to introduce zinc prince of water, right? So it will break up and form a compound as a CHO. How many? 1, 2, 3. 3 moles of this. Now what is this compound? This is called glyoxyl. Glyoxyl. Remember this. Okay. So just now once again we will see. In ozonolysis reaction, what is the step? Ozonolysis reaction. What is the step? First we have taken benzene. After benzene, it has formed, what have we been doing? I'm going to add ozone. It's going to form a compound called benzene triozonide. To this benzene triozonide, I'm going to add water and some zinc. I'm going to get glyoxyl. How many moles? 3 moles of glyoxyl. So this is your ozonolysis reaction, students. Now let us come back and see the next type of reduction, very important and famous reduction, that is bridge reduction. Thank you for watching. So welcome students to one more session of your benzene properties. In the previous video I've taught you addition reactions of benzene and oxidation reactions of benzene. Now after oxidation, today I'll be teaching you what is bridge reduction along with the mechanism. So let us write that. Okay, let me adjust my mic first. Yes. So in the bridge reduction process, so as I said, I'll be teaching the mechanism also. Let's write the heading. So this is your mechanism along with bridge reduction, right? So and mechanism, right? So in bridge reduction process, the first important thing which you should remember is reduction, we said. So for reduction, you require a reducing agent, correct? Fine. So in bridge reduction, I'm going to take benzene. Further, I'm going to introduce this with ethanol. I'll show you the mechanism, you'll understand. Ethanol in the presence of sodium. Whenever you're performing the reduction reaction, means you require a reducing agent, that is like nickel, platinum, palladium, sodium. Yes. So when you are adding ethanol and sodium, the product which you are going to get is this. You'll see the mechanism, then you'll understand. What is the name of this compound? Let's write. It is 1,4 cyclohexa, because still there two alkenes, 2 double bonds are there, hexadiene. 1,4 cyclohexadiene. Done. Now let's see the mechanism of this. So this is your benzene. Fine. So when I see the mechanism, the first step of bridge reduction is, see here, I am taking benzene with alternate pi bonds, correct? Fine. So this is in resonance with, right? First important thing, in step 1, this bond is broken here, this is broken, and it forms one free radical here. Okay, it's a radical. Now what will happen, this one will receive an electron from sodium. This is the important thing. It's going to receive an electron from sodium. So once it receives one electron, that this is 11, isn't it? 281. That one electron this receives. When this receives, how does it look? Bond is here, here, and minus. This is it. This is called what? Ion radical. Now this ion radical is going to receive H plus from ethanol. That is the role of this. H plus from ethanol. C2H5OH. Once it receives here, the electrons present, isn't it? That H plus will go and add at this site. Then what do I get? I get one hydrogen here, one more hydrogen here. There's still, right? Now this one I'm writing it here again. This further shows resonating structure, the shift of pi bond. So what are you doing? You're shifting. So this free radical also shifts here, here. Now, what does this happen? Here, it's going to again take electron from sodium, Na, this one. So, how does this look? This looks like this, H, 2, and this is minus. Now, same step repeats here. It's going to take, see here, electron from sodium, electron from sodium. This is going to again take H plus from ethanol. From ethanol, it's going to take H plus. Once this takes H plus, how does this look? This looks like this. So this is called this product, cyclohexadiene 1,4. So cyclohexadiene. So this is a bridge reduction. So this is a bridge reduction mechanism. Benzene. This is the first step. After that, once formed radicals, it's going to accept electron from sodium at this point, and later it accepts proton from ethanol here, proton, and finally that undergoes resonance. And again, once it undergoes resonance, electron it receives from the same step. It receives from sodium, and after that, it's going to receive a proton from ethanol, and finally from cyclohexadiene. Thank you for watching, students. To one more session of your chemical properties of benzene. Now we have come to the main concept, that is electrophilic substitution reactions of benzene. Right. So first of all, before going into the electrophilic substitution reactions, let's see the mechanism of electrophilic substitution. So first of all, electrophile. What do we denote with? We denote electrophile with E plus in this way. Correct? When I take benzene molecule, whenever I am adding an electrophile, electron deficient species, how does it show? The bond is broken here, and the electrophile goes and adds to the para position first one, and the H plus is out. So it undergoes lot of electrophilic substitution reactions. Let's see. Now, in this electrophilic substitution reactions, what is the mechanism? The same thing I'll be showing step by step. Keep noting it. Let's turn the page. I require the whole page. So we'll see the mechanism now. So when I have to see the mechanism of electrophilic substitution reaction, first important thing, right? You need to show it step by step. Then we'll be speaking about what happens when an electron releasing group is present, what happens when an electron withdrawing group is present. So in the mechanism, the first important thing, right? I'm taking benzene. So as soon as I take, I'll draw the alternate pi bonds. Correct? First important thing, there is a formation of arenium ion or carbocation or sigma complex or valence intermediate. This is what is the first important thing, right? Sorry. In the step 1, formation, let us write this as step 1. Step 1. Formation of what are formed means the same thing. It is either called as arenium ion or it is called as carbocation, or it is also called as sigma complex, or it is also called as valence intermediate. Valence intermediate. Done. Right. So benzene, I am drawing a bit lower here. Fine. So first important thing, whenever you're taking benzene, there is a shift of this bond. When it shifts off, how does it look like? Benzene, this pi bond is here only, this bond also is here. Now here the pi bond has shifted in this direction. This has lost electron, so this becomes plus. This has gained electron, this has become minus. Now this is called arenium ion or carbocation or complex sigma complex or valence intermediate. I have written it here. Now this further, when an electrophile attacks, this electron is shared to this electrophile. And how does this look? Get hydrogen and electrophile and plus here. Now in the second step, what happens? Next step, this bond, this pi bond shuts. Now this starts showing resonance. This pi bond shifts in this direction because there is electron deficiency here. When it shifts, and this will become deficient now, H and E. Now this further shows this again undergoes delocalization because there is a positive charge here. When this is removed to this becomes a positive site. This bond is here only. This bond now shifts to this direction because we shifted it here. This becomes plus and hydrogen and electrophile. Now further, this undergoes delocalization. This is plus, isn't it? Yeah. So the whole shift. This is one shift over, second shift over, third shift also over. Finally, we are going to get further resonance means there's no more aromatic delocalization because there are no pi electrons present. Correct? Yes. So finally, this forms a resonance hybrid. How do we write that? You're going to write it dotted lines like this and H and X. So as I said, no more aromatic delocalization, isn't it? Pi electrons, because it has already shifted. This one is here, one is here, one is here. So this, whatever positive charge is here, this is going to spread to two other carbon atoms. Yes. And how is it aromaticity restored? It has to be restored, isn't it? Then only you'll form a resonance hybrid. So what will happen? Positive charge formed spreads to two other carbon atoms. So how does it spread? It's going to take a bond like this. Right? H and E. So this bond shifts here, and finally I get all the bonds and electrophile is left out and H plus is this. So now the aromaticity is restored. So here, what is important thing? Benzene is acting as Lewis base. What is Lewis base? Lewis base is lone pair donor. Electrophile here is acting as an Lewis acid. What is a Lewis acid now? Lone pair acceptor. Right. Now, this is your mechanism of electrophilic substitution reactions. Suppose if I have, let me take you to one more thing. Suppose if I have an electron releasing group. So here in this electron releasing group, what will happen? What are the different electron releasing groups? That is your alkyl groups, isn't it? I've already shown you. Alkyl groups are present, which will increase, or they're going to increase electron density. Let's see. Suppose if I have electron releasing groups. I also made a video for electron withdrawing groups and electron releasing. Means what are the electron withdrawing and what are the electron releasing groups. Suppose whenever alkyl, example, as I said, alkyl groups. So whenever I have alkyl groups, they release electrons by what process? They release by a process called hyperconjugation. In GOC, you have seen this, isn't it? The release by hyperconjugation. So this, because of this, they are less reactive than compounds having above groups. Means different thing. Okay, I'll explain what is the concept. So this, by hyperconjugation process only, it's going to show, or it'll the whole impact is due to hyperconjugation. Let's see what it is. Suppose if I take an electron releasing group with benzene ring. I've taken benzene I have ethyl group, alkyl group. I am introducing E plus to this. Okay, let me put this into a box. Yes, E plus to this. In the step 1, this pi bond shifts here. Right? So what will happen? Electrophile also attacks. How does this benzene look? Your methyl alkyl group is here. Right? This has lost an electron, so this becomes plus, and H and E. Further, what happens? It undergoes resonance now. In the next step, this bond shifts here. H and E are here. Electron releasing group is here. Now what will happen? This bond has shifted to this direction. So here, and this becomes electron deficient, and there's one more bond here. Further, this undergoes resonance, means shifting of bond. Here, what do I get? I am going to get one bond here, one bond here, CH3 here, hydrogen here, electrophile here, but there will be plus charge here because this has lost electron. Then to satisfy this, further what happens? See here, electron releasing group I said, isn't it? Now CH3, I'm writing it as H. Okay, only one line, I'm sorry. H and CH2. So hydrogen is here, electrophile is here, positive is here, and this. Right? Okay. There is shift. Okay, let us see. There is shift of this bond. This bond has shifted here. Okay, I should not write here. This bond is here, isn't it? Okay, I'm sorry. Now, there's a bond broken. This becomes positive here. Correct? So, further what happens? This is in resonance with this bond is still here. H and E. This pi bond is still there. Now this bond is broken, isn't it? So this becomes double bond C, H, H, and this is lost, H plus. Further, what happens in this one? Further, when I take resonance of this, H and E here, pi bond is here, it's also here. Hyperconjugation I told you, isn't it? See here, I'm showing the hyperconjugation. So H plus, this is your hyperconjugation, isn't it? Further, I'm showing the hyperconjugation. See, hydrogen is here, hydrogen is here, one hydrogen here, one more hydrogen here, and H plus, isn't it? So here bond pair moves with where there is plus M effect, isn't it? Plus M group lone pair, because of the plus M effect, groups lone pair starts moving. So this is the concept of hyperconjugation, isn't it? So whenever you have an electron releasing groups like this, it's going to show the concept of hyperconjugation which I have shown. Now suppose if you have electron withdrawing groups, what are the different electron withdrawing group? Cyano, nitro, right? Like CO, we will list out one after the other. So remember, whenever you have an electron releasing groups, it's going to show the whole mechanism in this way. This is the way. Hope this is clear, students. Now we will write, or I'll show you what happens when I have an electron releasing group like this. So I have already made one video with electron releasing group. Let me take out the pages. Electron releasing group also I have shown you what are the different electron releasing groups, right? So when you have an electron, not releasing, withdrawing group, sorry, withdrawing groups, what happens? How does it show? So electron withdrawing groups, for example are NO2, cyano, SO3H, CHO, C double bond R, or if I have to take double bond O R NHR double bond O NH2 etc. So all these are electron withdrawing groups. Suppose if we have an electron withdrawing group, so these they're more electronegative atoms, isn't it? What do they exert? They exert minus M effect as well as exert minus I effect. So they're going to exert minus M effect as well as minus I effect also. Both they show here. If you have electron withdrawing group, when you have electron releasing group, as I've shown you, this electron releasing group in the earlier one, which works with hyperconjugation concept, isn't it? Right. Now let's see. Whenever you have an electron withdrawing group in the ring, this way, NO2 plus. So you're adding an electrophile to this. First important thing, this is electron withdrawing. You need to be careful. Right? Once the electrophile adds, just see here what happens. First important thing, you need to concentrate here. Plus O and electronegative atom, and the arrow is directed towards that. Right? So this bond from here is broken and one hydrogen and electrophile adds. So plus. Further, this shows resonance. NO2, H and H. Here there is positive charge, isn't it? So this bond shifts here only. So this will be here and this pi bond is here. When this bond shifts here, this will get a plus charge. Right. So what do we see? We have seen the resonating structures. Right. Now let's see. So where did we stop in the previous video? I think I have stopped it here. Let me take that. I'm writing the same compound again. Okay. Now I have an electron withdrawing group NO2. You have a hydrogen and electrophile. This is your bond and this is your bond. Now this pi bond has shifted here. When this pi bond is shifted here, there is a plus here. Now what will happen? Benzene ring, NO2 is here, hydrogen is here, electrophile is here, and this pi bond has shifted here. This pi bond is here. This becomes a positive charge. Correct. Now NO2, I said it is an electron withdrawing group. Yes or no? Yes. So because of this electron withdrawing drags the electron density. Yes. So what will happen? This bond not here, this will become plus because it is dragging the electron density towards itself. Yes or no? It will drag. So when it drags the electron density towards itself, suppose if I take, that's what I said, minus I effect and minus M groups. So minus I effect is showing here. Okay. So this is how it's going to show the electrophilic reactions. The mechanism of this is with nitro group, electron withdrawing group. So when I have groups like CCl3, NH3 plus, they also withdraw electrons from benzene ring. By what? They exert minus I effect like this. And when it is exerting minus I effect, what will happen to the ring? It will deactivate the ring. It will deactivate the benzene ring. So compounds with such groups are also less reactive than benzene, very less. Fine. So what will happen? These electron withdrawing group, which I have given the list like this, they are deactivating groups. All these are deactivating groups. What do? As you have seen, they withdraw pi electrons from the benzene ring. See here, I've shown you, isn't it? They withdraw pi electrons from benzene ring. And what will happen when they withdraw? The positive charge starts increasing in the benzene ring. And once the positive charge starts increasing, it is deactivation only, isn't it? So such compounds are very less reactive than benzene. Hope the concept is clear, students. So let's come back and start with the next first important reaction of benzene, that is halogenation reaction, along with the mechanism. Thank you for watching. Back, students, to one more electrophilic substitution reactions. In the previous video, I've taught the complete mechanism of electrophilic substitution. I also showed you what happens when an electron releasing group is present, what happens when an electron withdrawing group is present. Done. So electron releasing groups, they work with the concept of hyperconjugation, and electron withdrawing group, they show us the minus M effect as well as minus I effect. Right. Now, so whenever I take halogenation reaction, let's write the mechanism. What actually is halogenation? Halogenation is nothing but addition of halogen group, isn't it? Halogen can be your chlorine. X stands for chlorine. Here we are picking up chlorine and showing you. So whenever you have a halogenation reaction, it's a replacement of or introduction of halogen atom in the presence of hydrogen. That is what you should write the definition. So the definition would be introduction of halogen atom in place of hydrogen in benzene ring. Benzene ring. So this is your halogenation reaction. So whenever you're doing or performing halogenation reaction, so most important thing is you require the presence of, definition is over, so you require the presence of Lewis acid. Remember this. So presence of Lewis acids. So Lewis acid, what is Lewis acid like? I'm going to take aluminum chloride or FeCl3 or SbCl5 or SnCl4. Anything you can take as a Lewis acid. So what is the role of Lewis acid? It reacts with halogens. So Lewis acid, it reacts with halogens and generates halonium ion. So let us write the role of Lewis acid. So you're going to write, first important thing, it's going to generate, or first Lewis acid reacts with halogen molecule, reacts with X, and it generates which ion? Halonium ion. So this halonium ion, it acts as an electrophile, and after that it displaces hydrogen atom and displaces hydrogen atom from where? From benzene ring. From benzene ring. Okay, this is how is this. Now let's start. Suppose whenever I take halogenation reaction, okay, so first of all I'm going to take benzene, correct? So this benzene, instead of like pi bonds, instead of writing like that, I have written in this way, not a problem. So here there is one hydrogen, C6H6, isn't it? Now I'm going to add halogenation, chlorine. Done. There is chlorination. This, as I said, it should occur in the presence of a Lewis acid, aluminum chloride. First step, HCl is out. So write HCl. This chlorine goes and adds this hydrogen and you get chlorobenzene. This is chlorobenzene. Suppose if I take bromine, now X is equal to bromine. I'm going to add bromine to this hydrogen, Br. When you're adding bromine, you're going to introduce iron, Fe or FeBr3. HBr is out and you get bromobenzene. This is bromobenzene. I've shown already the electrophilic substitution mechanism. Now we will see the halogenation mechanism step by step. Right. So in step 1, I said halogen. So let me take instead of chlorine or bromine, X. Halogens are represented by X, isn't it? Right. This X, whatever is there, let us fill the electrons. 1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6, 7, 8 is here. Now, aluminium chloride, whatever is there, it acts as Lewis acid. This acts as, halogen acts as Lewis base. So Lewis acid is what? Electron pair acceptor. So this aluminium chloride is going to accept an electron pair. Then what do I get? This halogen is here with representation of electron. Done. This has lost one pair of electron. So this becomes plus. And AlCl3 minus, because this is accepted, this has become minus. Because this is lost, this has become plus. Done. Now, the next step, this bond is going to shift here. How does this look? This looks like X. Yeah. So this, not this particular thing. I'm talking the shade pair of electron. This is lost, this becomes plus, and X, and AlCl3 minus. Now, this acts as a Lewis acid, and this is an electrophile. Acts as a Lewis acid is an electrophile. This acts as an electrophile. Electrophile. Now, we are going to take this electrophile and further see the mechanism. Now this electrophile, first thing, I am going to take benzene with alternate pi bonds. I said in halogenation reaction, in the step 1, what did I say? Lewis acid reacts with halogen atom and generates halonium ion. Didn't I say that? Right, halonium ion. That halonium ion displaces hydrogen. So I am going to take this benzene. It's going to show a resonance. It is in resonance with. This is going to shift here. When it shifts, how does it look? It looks like this pi bond is here. Okay, this pi bond also is here. Now this is one hydrogen. Just see here that pi electrons are shifted here, isn't it? This becomes minus. Electrons here, and one hydrogen and plus. Now that electrophile, whatever is there, X, in the previous this one I showed you, that X acts as an electrophile. So this minus shade with this X. Yeah, this happens here only. And what do I get? I get this is shade with this. I get X. 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen. Now this becomes positive. Yeah. Now this is further resonance with. So there is positive charge here. So this shows for this positive charge shifts. H in X. So here we've got a positive charge, isn't it? To satisfy that, this is going to shift here. When this is shift, one here, one positive, one bond. Further, to satisfy this pi bond shifts in this direction. What do I get? That pi 1 and here H and X. Then what happens after shifting? This attains a positive charge. Yes or no? Yes. Again, after this means this bond is broken further, right? This bond is broken, and what do I get? The same structure, if I write. This is in a resonance with this structure also, isn't it? See here. I'm writing basically this we have done. Okay, this also we have done. Fine. So this again, the pi bond shifting will be there like that only. As I said, let us not write this plus. There is a shift of bond.
then one bond is here, one bond is here, one bond is here, and I get X and H plus is out. This is called your halobenzene. Right? Fine. So this concept of halogenation, hope this concept of halogenation is clear to me. I'll meet you again next with next type of electrophilic substitution reactions. Thank you for watching. Welcome back, students, to one more session of your electrophilic substitution reactions of benzene. Right. In the previous video, we have seen the halogenation reaction of benzene. Now, we'll be proceeding to the next concept, that is nitration. Right. So, what actually is nitration? Nitration is something simple. It is, you're going to introduce introduction of NO2 group. Right. So, this NO2 group is electrophile here. So what is it going to do? We're introducing this NO2, that is your nitro group. NO2 is nitro group, whose in place of hydrogen atom. Right, hydrogen atom and benzene. So introduction of nitro group in the place of hydrogen atom and benzene is called nitration. This is the definition of this. So when I have to start with the reaction, first of all, whenever you're doing nitration process, we are going to first take benzene. Along with this, we are going to introduce an important thing, that is nitrating mixture. So this is the main important thing. So for nitration, what do you require? You require nitrating mixture. This nitrating mixture consists of what? It's going to contain two acids, that is concentrated nitric acid and concentrated sulfuric acid. So this is in the presence of nitrogen mixture only nitration occurs. So I said we are going to take benzene. Along with that, I am going to add two mixtures, that is nitric acid. Nitric acid HNO3, I think I can write it as HONO2. Just see here, HNO3. Now this is treated in the presence of sulfuric acid. What is the temperature? 40 degrees centigrade. First, initially, when I take this benzene, hydrogen is here, isn't it? Everywhere, C6H6. So this hydrogen and this OH comes out as water. And this NO2 goes and attacks benzene, and it forms NO2. What is the name of this compound? This is your benzene, and this is nitrobenzene. So nitrobenzene. Done. Yes. So this is at 40 degrees. Suppose if you increase the temperature above 40 degrees, let us take this as step 1, let us take this as step 2. The same benzene, I'm going to take same benzene. I'm going to introduce 2 moles of this nitric acid and just one more sulfuric acid, one more nitrating mixture. Now from 40 degrees, I'm increasing the temperature to 80 degrees. Then what happens? As usual, there is hydrogen here for one water molecule. So for one nitric acid, we have got one water molecule out. For 2 nitric acids, again the same thing. What happens? I can write this nitric acid as HONO2. But how many are there? 2 are there, isn't it? See here. One hydrogen from here and one more OH. Right? So that's the first one. One more hydrogen from here, one more OH. So basically, this is one more hydrogen. So this hydrogen and this OH, this hydrogen, this OH comes out. So how many are we getting out? 2 water molecules are getting it out. Then NO2 is there, isn't it? So one NO2, remember, it attacks at the ortho position, and one more NO2 attacks at the meta position. So nitrobenzene, nitro group is always meta-directing nature. So we get meta dinitrobenzene. Okay, right. So remember, at 40 degrees you're going to get nitrobenzene. At 80 degrees you're going to get meta-dinitrobenzene. Remember. So even if sulfuric acid is not there, nitration takes place, but you require a lot of high temperature for doing this. So sulfuric acid here, what is its role? It acts as a catalyst. So let us write that. So the role of H2SO4 in nitration. If your teacher is asking you for 1 mark question, Just simple. Sulfuric acid here acts as a catalyst. It speeds up the reaction. And what else does it do? It's going to generate, it generates NO2 plus. This is electrophile, isn't it? What does it do? NO2 plus by interacting with HNO3. So I'll be showing you the mechanism in a few seconds. Then you can understand that. Interacting with HNO3. Okay. Right. This is the role of HNO3. Now let's come back and see the mechanism of nitration. So when I have to study the mechanism of nitration, let's write the heading first. So mechanism of nitration. Nitration. So what did we say? We require nitrating mixture, isn't it? Right. First of all, let us take step 1 part. So first important thing, nitric acid. So that is here nitric acid HNO3 and this is nitric acid, isn't it? Let's come 1, 2, 3, 4, 5, 6, 7, 8. For this oxygen 1, 2, 3, 4, 5, 6, 7, 8. This is nitric acid. This combines with sulfuric acid. This is an reversible reaction. So what happens in the first step? If we observe sulfuric acid, the sulfuric acid, it breaks up into H plus and HSO4 minus. Okay, and once again sulfuric acid, this breaks up into H plus and HSO4 minus. So this H plus attacks this oxygen. What do you get then? Hydrogen, oxygen, one hydrogen here, nitrogen, there is one more oxygen, double bond O. So the bond is shared, so this oxygen gets plus because this lone pair is shared by this hydrogen, isn't it? So shall we write that R and yeah. So this has got plus now, plus HSO4 minus. HSO4 minus. Done. Now here, what is it doing? It is accepting a proton, isn't it? This is accepting, nitric acid is accepting a proton. So this is called, it acts as Lewis base. And when this is Lewis base, this automatically is a Lewis acid. Done. Now in second step, what happens is, this HSO4 minus, it combines with water. No, it is not water, it is hydronium ion. Okay, now hydronium ions 1, 2, 3, 4, 5, 6, 7, 8 plus. Right? This occurs in the presence of sulfuric acid. Now what is this? This basically, this one is bisulfate. This is bisulfate. This is hydronium ion. Acidic medium we said, isn't it? Bisulfate, hydronium ion. So they together combine. When they combine, what will happen? Let's see. First of all, did we leave one step? I think we have left one step. Let's come back and see. Here in this step, okay, I'm sorry. I think I forgot one step here. Let's see. This has got positive charge, isn't it? Fine. Here, right. So there is a cleavage of this bond. There's a cleavage of this bond. I get water molecule. Perfect. Now it's right. And once this is broken, what is left out? You're left out with nitrogen, double bond, oxygen, yes, plus. Done? Yes. Now what is this ion? This is called nitronium ion. This nitronium ion, when you're further treating with sulfuric acid, same thing, sulfuric acid, what happens? It breaks up into, same thing, HSO4 minus. What's all no? Sulfuric acid, how does it break? It breaks up into H plus and HSO4 minus. So nitronium ion is out. This water molecule combines with this H plus, forming H3O plus, and HSO4 minus is out. Hope this is clear, students. Right? Done. Now this NO2 plus, this acts as an electrophile. Hope this step is clear. In the step 1, sulfuric acid breaks up into H plus and HSO4 minus. This being a Lewis base, it gives, or this acts as a Lewis acid. It accepts an electron from a Lewis base, and you get this, right? So further, what happens? This, which a complex which is formed because oxygen has attained a positive charge. This is a cleavage of the bond here. I get that, and NO2 plus electrophile is generated. Now this H2O combined in the presence of sulfuric acid forms hydronium ion, and bisulfate is released out. So this is a nitronium ion. So nitronium ion, it acts as an electrophile, as I said. Yes. So a carbocation which ceases to be aromatic is produced in intermediate. Now by the release of H plus ions from the carbon, NO2, let's see how is it going to attack the benzene ring now. Right, so when I have to take this NO2 plus, just see, now this is your benzene first, then the nitronium ion which we got, NO2 plus is out. Now first step, shift of pi bonds. Then what do you get when you shift the pi bonds here? This is going to attain a positive charge because this bond has shifted. You have pi bonds here and hydrogen and NO2, right? Okay, let us not write this because I'll be showing in a continuous step. Now there is a positive charge. This is going to shift in this direction. This is in resonance with more. Your hydrogen and nitrogen are here only. From here the bond has shifted here, and now this becomes plus. Further, this bond shifts in this direction. This becomes electron deficient now. This is plus H, NO2. Done. So what is now? This is where you can pick from any point here also, and one more you can shift. You can shift this. Fine. So further, when this is treated, let us take this. When this is treated with HSO4 minus, we have got HSO4 minus now. Just see here in the previous video, and sorry, in the previous page. I'm sorry, not the video. In the previous page, we have got HSO4 minus here. This HSO4 minus, when it's treated or with water, okay. Now H plus is removed out. Right. So now what happens? Same way. This particular thing, if you shift in this direction, this drops out. Okay, and this drops out, drops here, or when you take this, it drops in this way also, not a problem. Drops in this way, you get a bond here. So what will happen? You get NO2 which is there, and benzene, and what is left? HSO4 plus H plus gives me H2SO4. So this is your nitrobenzene. Right, done. So this is the mechanism of nitrobenzene, students. So you can take any intermediate carbocation and show the mechanism. Thank you for watching, students. I'll meet you again with sulfonation mechanism and reaction. Welcome back, students, to one more electrophilic substitution reaction of benzene, that is sulfonation, along with its mechanism. Right? What is sulfonation? Basically, when I have to write the definition, it is nothing but introduction of SO3H. This is, what is this group called? This is called sulfonic acid. Sulfonic acid group. Okay, introduction of SO3H in the place of hydrogen atom. So where is this hydrogen atom? In benzene. This is called sulfonation. And the product what we get is benzene sulfonic acid. Now let's take. Now I am going to take benzene, hydrogen. To this I am going to add sulfuric acid. So sulfuric acid which will generate the sulfonic group. We'll see. So I am going to add sulfuric acid. Sulfuric acid can be written as H2SO4 is a formula. OH here, OH here, sulfur in the center, 2 oxygens above, that is 1 oxygen above, 1 more oxygen below, not join the bonds. So H2SO4. Done. So now what happens? This hydrogen and this OH comes out as water. Water. Now what is left out? We left out with sulfur, oxygen, oxygen and OH. So this sulfur, being an electronegative atom, it's going to be attack at this point. So you get benzene, link it with sulfur, 2 oxygens are there, isn't it? 1 oxygen here, 1 more oxygen here, and OH. So this is called benzene sulfonic acid. Benzene sulfonic acid. So sulfonation is carried out by heating what? With benzene with concentrated sulfuric acid. This is concentrated sulfuric acid. Suppose now, okay, let us write sulfonation with concentrated sulfuric acid. Right. Suppose if you are heating with dilute sulfuric acid, what will happen? We'll see. Okay. Treatment with dilute sulfuric acid. Okay. When you are treating with dilute sulfuric acid, the same thing. You are going to take benzene. Right. So now we've got this H2SO3H, isn't it? Benzene sulfonic acid. I'm going to take that. So that SO3H in this first stage, bond shifts here, and you're treating with dilute sulfuric acid. This is that proton from the dilute sulfuric acid. Possible reactions. What will happen? This bond has shifted here, isn't it? Yes. So there is a deficiency created here. Yes, and here hydrogen and SO3H. This further, when you're dealing with H plus, this bond shifts here. So what do you get? You get 1 pi bond here, 1 more here, 1 more here. What is left now? SO3H or HSO3. Anything? HSO3 minus. HSO3 minus is generated. So whenever you're treating with dilute sulfuric acid, you get back benzene. So remember, nitration, when it is, not nitration, I'm sorry, sulfonation. Sulfonation, whenever you're treating with concentrated sulfuric acid, and sulfonation when you're treating with dilute sulfuric acid. So whenever you're treating with concentrated sulfuric acid, you get benzene sulfonic acid, BSA. Whenever you're treating with dilute sulfuric acid, you get benzene back. Remember this. Now, let's see the mechanism, what is involved in sulfonation process. Right. So, let me write the heading. Mechanism of sulfonation. Right. First of all, SO3, now so we are going to take concentrated sulfuric acid first. So whatever SO3 is there, this SO3 is present in dissolved state, present in concentrated sulfuric acid. Which condition? In dissolved state. Remember this. It can also be, it can also be produced. How can it be formed? By interaction of 2 molecules of sulfuric acid. How is that? We will see. First, I'm going to take 1 sulfuric acid like this. OH in one side, 1 more OH, sulfur here, oxygen, oxygen. Now, this is going to combine with 1 more. This is H2SO4, 1 molecule. This is going to combine with 1 more OH, SO3H, 1 more sulfuric acid, 2 molecules of sulfuric acid. So now what happens? Reversible reactions. Yes, these two are going to combine. These two will combine. How will it combine? Just see. The first hydrogen is here, right? The second oxygen is here. Then and sulfur is here, oxygen is here. Okay, not this one. Double bond oxygen is here. OH is here. Fine. So now see here. This oxygen, whatever is there, 1, 2, 3, 4, 5, 6, 7, 8, isn't it? Fine. Observe carefully. There is a cleavage here. HSO4 minus comes out. Basically, HSO4 minus comes out. HSO4. The cleavage here. This proton accepts this. This donates and this accepts. So what do you get here? You're going to get hydrogen. This has lost a pair, so plus. Done. Further, what happens? It's the same thing. Further, there is cleavage of water molecule. Just here. So you get water out. And what is left out now? We are left out with sulfur. This part I am writing. Oxygen. Double bond oxygen. O and H. Correct? Yes. Further, this breaks up. Observe carefully. Water is there, isn't it? So there is a cleavage of the bond here also. H combines with this forming H3O plus. And what is left out? SO3 is out. Right? So this acts as an electrophile now. This is the electrophile. Now we are going to take this electrophile and we are going to show how it is added around benzene. Right, let us further proceed. Now what is electrophile in sulfonation? SO3 is electrophile. Now I am going to take benzene. So SO3 we have already generated. Now in the step 1, yes. So when this pi bond has shifted, how does benzene look? This site attains a positive charge. This is like this only. This is also like this. So because this is accepted, here it attains a negative charge. Now electrophile is what? SO3. So sulfur structure SO3 is this one, isn't it? So 3 oxygen. Now count 1, 2, 3, 4, 5, 6, 7, 8. Now for this oxygen 1, 2, 3, 4, 5, 6, 7, 8. For this oxygen 1, 2, 3, 4, 5, 6, 7, 8. Now this SO3 which acts as electrophile, then it attacks at this site. This site. So how does this look? 1, this pi bond is here, pi bond is here. It opens up hydrogen because the electrons are excess here, isn't it? And it attacks that part as with sulfur. Oxygen here, oxygen here, oxygen here. Now for this double bond 1, 2, 3, 4. For this double bond 1, 2, 3, 4. Now this is accepted. Now around sulfur how many? Okay, there still be single bond, isn't it? It's oxygen. So 1, 2, 3, 4, 5, 6 minus. Further, this undergoes resonance. Fine. There is a shift of the bond because there is plus sign here to satisfy that. This bond is going to shift to this direction. Okay, hope it is clear. This has got a positive charge. This has got a negative charge. To satisfy this bond is going to shift here. Yes, so how does that look? This looks like this. This bond. This is hydrogen. This is sulfur. Double bond oxygen. Double bond and single bond oxygen. This got a positive charge. Now to satisfy that, this pi bond gets exchanged. And what do you get? You're going to get a structure like this. Hydrogen, your sulfur, oxygen, oxygen, O minus, and one bond here, one bond here. You get plus. Now, this hydrogen bond to satisfy this valency, this bond shifts here. Right, we are going to treat this with HSO4 minus. So this HSO4 minus, this bond shifts here, picks up this H plus. After shifting the bond, the H plus is picked up by HSO4 minus. What do you get? You're going to get, now all the pi bonds are here. and I am left with sulfur, oxygen, one more oxygen, and oxygen minus. So this HSO has picked up this hydrogen, isn't it? You get sulfuric acid. Further, when you treat this, what you get? You get pi bonds, S double bond O, double bond O, and further you're treating with this particular thing, you're treating with sulfuric acid, isn't it? The H plus is picked up by this. Then it further attacks, one proton attacks this, and we get OH plus water molecule. Fine. Now here you should be careful. Whenever you're shifting pi bonds, carefully see that you're shifting it perfectly. So how did I get this H? Let's see. Now in this particular stage, you're treating with sulfuric acid. Sulfuric acid has picked up this hydrogen. At the same time, you're treating it with water. Here, see, hydrogen into plus. So this oxygen accepts this proton. That is where we have got this OH. Right. This is your sulfonation reaction mechanism, students. So hope it is clear. First I have generated SO3, then I have taken that SO3 and shown you a stepwise. So this is the mechanism. So careful. One, this is the first step. First, second, third, fourth, fifth, sixth and seventh steps. So thank you for watching, students. I'll meet you again with Friedel-Crafts alkylation and acylation reaction mechanisms. Stay connected. Right. Now let's see the uses of sulfonation. So we have already seen how we have generated SO3. How is it adding around the benzene ring? So basically sulfonation reaction. So sulfonation, it is used to block a position in benzene ring. So it's going to be, or we are using it to block one position in benzene ring. Let us see one example and understand that. Fine. So, and no other group occupies, so that it will block and no other group comes and occupies that. So suppose if I take toluene, right? Fine. To this I'm going to add sulfuric acid. See how is it blocking. So this sulfuric acid, as in the mechanism we have seen, it releases SO3H, isn't it? Now this SO3H, it goes and blocks the para position, SO3H. So para position is blocked. That is the main use. Now what happens? Suppose if you are introducing bromine in the presence of Fe, this is blocked, this is also blocked with sulfuric acid, SO3H. Now this bromine goes and attacks at this site. First is this site only, isn't it? So your methyl group is here, bromine is here, SO3H is here. Further, if you try to hydrolyze this, let us H plus and heat. So this H plus and this SO3H comes out as sulfuric acid, that is there. And the leftover compound is this CH3 and Br. That's it. So basically sulfonation is used to block any position, whichever position, because this is para-directing, we have blocked that, and the leftover site is this. So bromine has come and attacked this. So this reaction is basically sulfonation reaction is useful in preparing which one I can use to prepare. I can prepare orthobromotoluene, means specifically orthobromine instead of ortho and para bromotoluenes. So instead of preparing that mixtures, I can prepare only orthobromotoluene by blocking the para position instead of getting two different products. Right. So then students, I'll meet you again with the next concept, that is Friedel-Crafts alkylation reactions. Thank you for watching, students. Welcome back, students. Now in today's session, what are we going to learn? We are going to learn the Friedel-Crafts alkylation reaction of benzene. So what is Friedel-Crafts alkylation? Step by step we will see. So here when I have to write the definition, we have been writing the definition for all. Like nitration means introduction of NO2 group. Sulfonation means introduction of SO3H. Halogenation means introduction of chlorine group. Now, in Friedel-Crafts alkylation, it is basically introduction of alkyl group. Introduction of alkyl group in which one? In benzene ring. Done. In the place of hydrogen. In the place of hydrogen atom. Alright? In the place of hydrogen atom. It's called Friedel-Crafts alkylation. So first of all, for Friedel-Crafts alkylation, what are the requirements? What do you require? You're going to, or this whole reaction occurs in the presence of a Lewis acid, that is your aluminium chloride. So you're going to take this Lewis acid, in the presence of that only we are going to show the alkylation reaction. Suppose let us take, I'm going to take benzene. When I take benzene, now I'm going to add Rx. What is Rx? Rx stands for alkyl halide. Alkyl halide. Suppose this is methane. So this is R. To this methane, I'm taking out one hydrogen. I'm introducing one more X. Then it is Rx. Alkyl halide. Okay. Done. I said we are going to introduce in the presence of aluminium chloride. This H and this X combines. And this comes out as HX. What is left out? We are left out with the alkyl group which is attached to benzene ring. So this is R. This is alkyl benzene now. Alkyl benzene. Now let us take example. I'm going to take a benzene ring, right? In place of X, I'm going to introduce Cl. In place of R, I'm going to introduce CH3. Now I'm taking aluminium chloride again. The hydrogen which is there in benzene, it comes out as HCl. And CH3, whatever is there, it goes in attacks and it forms a compound called toluene. Toluene or toluene. Suppose here instead of chlorine, I'm going to take bromine, alkyl bromide. So this is your benzene. I'm going to introduce bromine, CH3. This is alkyl bromide. So HBr comes out. What do we require? We require aluminium chloride as a Lewis acid. But here, you should not use this. Careful. For bromine, you are going to use FeBr3, iron bromide. So HBr is out. What do I get? I get CH3, that is toluene. Right? Clear, students? Let us take one more. Suppose if I take benzene ring, if your teacher has given you like this. This is what? Ethyl chloride. Whenever you see chlorine, you should be careful. You are going to introduce AlCl3. Whenever you see bromine, you will introduce FeBr3. Now what will happen? The hydrogen here and this chlorine comes out as HCl. This whole thing attacks here. Everything CH3. So this is your CH2. This is CH3. Now come 3 plus 1 4. 2 3 4. So this is ethyl benzene. This is ethyl chloride. This is benzene. So all these are called Friedel-Crafts alkylation reactions. Done. Now let's come back and see the mechanism of Friedel-Crafts alkylation reactions. Mechanism. So first important thing, I said this whole reaction occurs in the presence of aluminium chloride. Yes or no? Yes. So for this, first you're going to take alkyl halide. Count 1, 2, 3, 4, 5, 6. Minus. Okay. Aluminium chloride here acts as a Lewis acid. Right? Fine. So it's going to accept this pair of electrons. And how does this look like? R X is here. Because this has lost this pair of electron, what will happen? It's going to attain a positive charge now. And AlCl3 has accepted that pair of electrons. Now this has a positive charge. To satisfy that, this bond shifts. What do you get?
I get R plus. This is alkyl carbocation. Alkyl carbocation. Let me change my pen. This is not writing properly. Okay, let me take this. Now what is left out? Left out with this one. X AlCl3. Now count 1, 2, 3, 4, 5, 6, 7, 8. Now AlCl3 is minus. So alkyl carbocation is ready. This acts as an electrophile. Now I am going to take the same benzene ring as we have seen. Step 1. Shift. When it shifts out, how does this look like? Because this site has lost an electron, means here the shade paid is lost here, isn't it? So you get a positive charge here and a negative charge at this point. Now the carbocation, whatever is there, attacks. This is shade to an alkyl group. What do you get? Bond is here. When this is shade to the alkyl group, hydrogen R. Now there's a positive charge still existing. To satisfy that, this pi bond shifts here. What do you get? You are going to get hydrogen is here, R is here, 1 pi bond, because this has lost the this is donated to this site, isn't it? So this attains a positive charge, electron deficient. In the next step, the pi bond from here shifts. So when this is shifted, here you will get a positive charge. Correct? So your bond, yeah, here, and this is plus. This is hydrogen. This is alkyl group. Now further. Now see here. This is over. This bond also has shifted. From here, this has come in this direction. This is positive. Right? Now suppose you can pick up anything. You can take this, you can take this, you can take this, any part you can take. And finally what happens? Suppose if I take any of the intermediate state when this was in this direction, further there is a cleavage of the bond here to satisfy this. This bond shifts and there is a cleavage and only alkyl group is present. Alkyl group, and your H plus is out. This is your alkyl benzene. Now basically this H plus, whatever is there, what happens to this? It's going to combine with, you have AlCl3, isn't it? In the first reaction you've got this AlCl3 here. That H plus combines with this AlCl3, right? So AlCl3, this is minus this H. Okay, there we have cleaved it already. Let's see. Yeah, X 1, 2, 3, 4, 5, 6, 7, 8. This is shade with this hydrogen. Now how does this look? Bond formed. AlCl3 also is here. Now this is shared an electron pair. That means this gets a positive charge. Now further what happens? This is a negative charge. This bond is shared to, yes, the bond is broken, this is shared, and you get HX outside and AlCl3. So 1, 2, 3, 4, 5, 6, 7, 8. So the advantage of Friedel-Crafts reaction. What is the disadvantage of Friedel-Crafts reaction? What happens is, in some cases, the carbocation is formed, right? So what does it do? It starts rearranging to become a more stable carbocation. That only rearranges. Before we introduce that in the benzene ring, it rearranges. So the rearranged carbocation, what will happen? It enters the ring instead of the original one. It will enter. And basically we want the carbocation, alkyl isn't it, group to be introduced. But the carbocation, because of rearrangement, we get an unexpected product. So let us write that. Disadvantage of Friedel-Crafts reaction. Right? Okay. I'll just change my pen and come back to you. Welcome back, students, to the last topic of the hydrocarbon chapter, that is Friedel-Crafts acylation reaction. So till now we have covered all the types of mechanisms, right? We have studied about halogenation, we have studied about sulfonation, nitration, Friedel-Crafts alkylation, and now the acylation part. This is the last topic of the chapter. After this, according to the sin, I'll be starting the next chapter, right? So the next chapter follows immediately from tomorrow only. Done. So whenever I speak about Friedel-Crafts alkylation, what is the definition? So whenever you have a name reaction, remember you need to write the definition and then go back to the mechanism, right? So what is the definition? It is nothing but introduction of, in this particular reaction, we are going to introduce introduction of acyl group, acyl, A-C-Y-L, acyl group. Where are we introducing? In the benzene ring. So we are going to introduce acyl group in the benzene ring, right? In whose place? In the place of hydrogen, in the place of hydrogen atom, right? So we are going to introduce acyl group in the place of hydrogen atom and do the whole reaction, right? So here, let us see the reaction, then come back to the mechanism gradually. So what is this first? So now I'm going to write the reaction. We are going to take benzene ring, right? So we have studied the properties, structure, everything about benzene ring, isn't it? Right. So benzene ring shows aromatic property. Now here it is C6H6, so there's one hydrogen here. Now I'm going to add acyl group. What is acyl group? Acyl group is nothing but, just see here R on one side, done. C double bond O on one side. Now here Cl. This still here, whatever is here, this is called acyl group, and Cl, because chloride is present, we call it as acyl chloride. This is acyl, this is chloride. So let us write the name as acyl chloride. Now I'm going to add this acyl chloride to benzene ring. So first of all, what happens? HCl comes out. But what is important? This whole reaction occurs in the presence of a Lewis acid, that is aluminium chloride. We'll see the mechanism very soon. So just see. Now what is eliminated? HCl is eliminated. HCl is eliminated and COR group attaches to the benzene ring. And what do I get? I'm going to take this benzene ring. That this is the position. Now HCl has come out. Now what is left out? You're going to link with carbon. Remember that. And on one side, double bond O. This is R. What is the name of this compound now? This is acyl. This is benzene. So it is acyl benzene. Done? Yes. Now let me take some certain examples and see here. Instead of R, let us take specific examples. Now next one is examples. Now here again I'm going to take benzene ring. Okay, right. Now here Cl is there only. Now C double bond O is there. Now instead of R group, I'm going to introduce CH3 group. Now what is important? This whole reaction occurs in the presence of aluminium chloride. It is a Lewis acid. Now what is important? HCl is eliminated out and the acyl group goes and adds to benzene. Which point? Here only. So what do we get? We're going to get benzene ring, we're going to carbon, double bond O and CH3. Right? What is this name of this compound? You see here now. This is acetic acid, isn't it? Just like that. Acetophenone. So what do we write? Acetophenone is a compound. Done. Now let's take one more example and see. Right? So here acetophenone, we have taken from acetyl chloride, we've got acetophenone, isn't it? So let us write the name of this compound also. So this is acetyl chloride. Done. Now let me take one more example. Now instead of acetyl chloride, let us take benzyl chloride, right? So what happens now? Here I'm going to take benzene. Now Cl is here only, then C double bond O is here. Now instead of methyl group, we are going to take C6H5. So what are we going to call this? This is acetyl chloride. Now this becomes benzoyl chloride, isn't it? This is benzoyl chloride. Now the scene is above, aluminium chloride, Lewis acid. What are we going to remove? We are going to remove HCl from here. When I remove HCl, here also HCl. What product do I get? I get benzene ring. Yes. Now in this benzene ring, carbon is attached to this, C double bond O on one side and C6H5. Now let us name this compound. What is this compound called? This is called benzophenone. This is acetophenone, and this is benzophenone. Done? Yes. So now let's start with the mechanism. There's no rearrangement here. There is no rearrangement which takes place during Friedel-Crafts acylation reaction, right? So no rearrangement takes place. What is the reason? Because acyl carbocation, whatever is there, is stabilized by resonance. So remember, when you take acyl chloride, you get acyl benzene. When you take acetyl chloride, you get acetophenone. When you take benzoyl chloride, you get benzophenone. Now let us see the reaction mechanism as such, right? So when I speak about reaction mechanism, let's write mechanism. So in step 1, the most important thing here, you're going to take acyl chloride as well as aluminum chloride, both, right? So first let us take acyl chloride, and you're going to add aluminum chloride to this. What is important here? Acyl chloride acts as a Lewis base and aluminum chloride acts as a Lewis acid. So what is Lewis acid? Lewis acid is electron pair acceptor, isn't it? Electron pair acceptor. Lewis acid is electron pair acceptor. Now see, now let us count. This Lewis acid has to pick up the electron pair from here, right? So this is electron pair donor, this is electron pair acceptor. Now let's count the number of electrons. 1 2 3 4 5 6 7 8. Done. So this Lewis acid is going to accept one electron pair from chloride. When it accepts, how does this look? This looks like R is here only, then C double bond O is here. Now Cl has donated an electron pair, so this is there as such, this is also there as such. Now it has donated an electron pair, so it becomes plus, and AlCl3 has accepted the electron pair, so this becomes minus. Done. Now from this stage, what is the next stage? Just see here, this oxygen 1 2 3 4 5 6 7 8. Done. So this has become what now? Sorry, yeah, chloride has become plus. So in the next step, what happens is there is a cleavage of the bond. There is a cleavage of the bond here. So how does this look? R C double bond O 1 2 3 4 plus AlCl4 minus, right? That. Now what happens? This is plus. So here, because to satisfy this, a part of the electron shifts here, shifts. Now further, what do I get? This is in resonance. Now what is this carbocation? This is called acyl carbocation. This is acyl carbocation. This acyl carbocation, how does it stabilizes? It stabilizes by resonance. That's why I've written double-sided arrow. Stabilizes by resonance. When it stabilizes by resonance, how does this look? R C double bond, right? So one done. So shifting here, this becomes plus. This 5. So now this is the acyl carbocation which is stabilized. Next important thing, what should you remember? After this particular step, now let us take benzene. Now this is your benzene ring, correct? This is your benzene which the acyl carbocation has to attack. First step, yeah, shift. When it shifts, what happens? Yeah. Your benzene ring. Now just observe carefully, a electron has been shared to this. It means it's shifting, a pair of electrons shifting here. So 2 dots. So this becomes minus. So what will happen to this side? This side becomes plus because it has lost a pair of electrons. Now to this, your acyl carbocation is going to come in. R C double bond O. 1 2 3 4 5 6 7 8. Right? So this carbocation, whatever we have here, fine. So this is plus. Now see here, this carbocation, yeah, this is attacked, correct? So when this is attacked here, what happens? Just observe carefully. Please don't get confused with the signs. Fine, done. So you are going to get the structure. This bond is here only. Done. Hydrogen is here. C double bond O. 1 2 3 4. To the same, R also is linked, and there is plus here. Done. This is further in resonance with. Just see here. What am I going to do? Hydrogen is here. Carbon double bond oxygen R. Now there is one bond here. Fine. So just see here. This bond, whatever is there, this bond, whatever is there, it's going to shift here in this direction. Then this bond and this bond should not be together, so this bond also shifts here. You get like this. So this is a plus sign here. I'm sorry, it is not neat. Done. Further, what happens? You get now at this particular stage, this bond has shifted here. So this one, and this side also gets positive. So hydrogen, carbon, double bond O and R. Done. Yes. So in the next step, this side has got positive. In the next step, what happens is, like, you know, this the shifting of bonds from here till here to shifted. This also has shifted. So there's one side created positive here, one more side is positive is created, one more side positive is created. So ortho position, para position, the positive sign, positive side is created. Now here, when I come back with this, just see here, this is hydrogen, carbon, double bond OR. Yes. So I'm taking one of the side and I'm showing this. So minus H plus, the last step. What are we left with? Because this bond is shifted here, carbon, double bond O, R plus H plus. So finally what happens? H plus combines with AlCl4 minus, which we have got. Finally, I get HCl and AlCl3 is out. The Lewis acid is out. So here, important thing, just see, first you have to show the formation of the acyl carbocation. This is very important step in Friedel-Crafts acylation. After that, that acyl carbocation is stabilized. Okay, that we have shown. And you're going to take that acyl carbocation and show the shift of the pi bond at the ortho, para and ortho position. Ortho, para. See here, this is ortho, this is para, and again this is ortho position. After that, finally AlCl3 is out. So what is the use of Friedel-Crafts acylation reaction? So uses are basically, I can this Friedel-Crafts acylation reaction is used in the synthesis of polynuclear aromatic compounds. So what are polynuclear aromatic compounds? So polynuclear aromatic hydrocarbons. So this, like naphthalene, anthracene, all these, isn't it? So here we are going to synthesize or prepare naphthalene compound from your means using Friedel-Crafts acylation reaction. So I'll be showing this naphthalene compound or preparation in my 9 o'clock slot video. So thank you for watching, students. This is your hydrocarbons chapter. Wonderfully done. All the reactions are covered in this. So please, I hope you all would go through all the videos, go in the sequence only, right? So I'll be meeting you again with the next chapter, very important chapter of grade 11. It will be useful. I'll be doing a lot of exercise problems with that. Stay connected. Please watch it on the daily basis. Thank you for watching. Hope you would have seen the earlier video, students. I've taught you what is meant by eclipsed conformation, staggered conformation, that is in like Newman projection, as well as I taught you Sawhorse, everything clearly explained, right? So now in this video we'll be learning about the concept of torsional strain, and we'll also be drawing the Newman projection conformations as well as Sawhorse for the ethane molecule at different angles. Done. So when I have to speak about the concept of torsional strain, just see. So torsional strain is nothing but a resistance because of the repulsion existing between adjacent carbon atoms. Done. So first let us write the definition. What is torsional strain? It is right, definition. The resistance to twisting which affects the stability of conformations is called torsional strain, right? And one more concept which is related to the torsional strain is torsional energy. Let us write that. Torsional energy. So what is this? I said because of the repulsion, resistance to repulsion, that means that restricted molecule, that's it. I said this is energy difference of 1 to 20 kilojoules. That little, because of repulsion between electronic repulsions, because of that the torsion strain is created, and the energy which is required in restriction is called torsional energy. Okay, let us write energy required in restriction. It's called torsional energy. One word. Right. We've also seen in the previous video what is that dihedral angle. One more word which I have to give you a definition is dihedral angle. So what do we see dihedral angle? I said the angle means when I take a molecule, like listen, let us draw that example and see. Same thing I'm drawing. One, I've taken staggered conformation in this. One hydrogen here, one more hydrogen here, one more hydrogen, one hydrogen, next, and one more. Now I said the angle between these two is called dihedral angle. How will we define this? Right? So same thing, the angle between adjacent hydrogen atoms present is called dihedral angle. Right. So this dihedral angle, or the magnitude of this, so on what basis does it depend? Important thing, why did I draw here? Because the magnitude of the torsion strain depends on the rotation about carbon-carbon bond. So dihedral angle, because it's denoted by theta. What am I trying to explain? I'm explaining the magnitude or the measure of torsional strain depends on theta, dihedral angle, around or about carbon-carbon bond. So among the staggered and eclipsed, what we have seen, staggered form has least torsional strain. I said the repulsion is very minimum, isn't it, in staggered? So among both the forms, when I have to see, staggered form has least torsional strain, right? And when an eclipsed form, as I said, because the atoms are very close, isn't it, as I've shown in the previous video, so eclipsed form has maximum torsional strain. So what is the energy difference between both? The energy difference is between both is 12.5 kilojoules per mole. Now let us answer one question. Suppose if your teacher is asking you, why is it not possible to separate or isolate conformational isomers of ethane? Why can't I separate? We've written, isn't it? They're non-separable. So if the teacher is asking you this question, let's see, why is it not possible to separate or isolate different conformational isomers of ethane? If they ask, if your teacher asks, why can't you separate them? So simple answer which you have to write directly, just you need to mention the keywords. Important thing is, we said the energy difference is very less, isn't it, 12.5. So because energy difference is very small, very less in ethane molecule, even at ordinary temperature, like normal ordinary temperature, right? So they gain thermal energy or kinetic energy. That kinetic energy, why? How do they gain? Because of intermolecular collisions. That's why, because of this, the energy difference is easily they're interconvertible, isn't it? So because of this, they gain kinetic energy, they get interconvertible. When they get interconvertible, can I separate them? I can't separate them. So that is the reason we can't separate both the isomers. Let us write, since energy difference is small between both, small between two conformers. How much is energy difference? I said 12.5 kilojoules per mole only. Done? So what will happen? Even at ordinary temperatures, what do they gain? They gain which energy? As I said, they gain thermal energy. They gain thermal or kinetic energy easily, isn't it?
How do they gain this thermokinetic energy? Due to intermolecular collisions. So once they gain easily, I think they can. It's once they get converted, it's very difficult for us to separate with very less energy, isn't it? Right? So because of the intermolecular collisions, they get interconvertible, and we can't separate them easily. So I think with this, the concept of torsion strain, dihedral angle, torsion energy, and is clear, students. Now let us come back and draw the conformers of ethane, conformers of propane, or the conformations of propane in terms of Newman projection, Sauer's projection, and see how are we drawing it, means how are we showing it, what happens when we rotate it through 60 degree, what happens when we rotate it to 120 degree, 180 degree, like that. Thank you for watching, students. I'll meet you in my next video with the conformations. Stay connected, stay tuned. Welcome, students, to one more session of your general organic chemistry. So we have done in the previous video the conformers of ethane. I have clearly explained the different concepts like your Sauer's projection from Wilson representation, Newman projection representation. Then I've taught you what is SKU conformations. I've also given you the information based on dihedral angle. I've given you information based on torsional strain, torsional energy, what is that energy whenever using that. And I also given you the order of staggered conformation, that order of stability of staggered conformation, Newman projection conformation, as well as SKU conformation. We also said among all the three, staggered is the most stable. Least stable is eclipsed form because atoms are very close by. Done. Today we'll be learning about conformations of propane and conformations of butane. Done? Yes. So here I'll be drawing the Newman projection conformations, Newman projection conformations for propane. So when we see Newman projections, I think you would have clearly understood how we represent, right? I'll be drawing the eclipsed form for that, and I'll be also drawing the staggered form for this. Done. So in the Newman projection eclipsed form, right? So both you have to show this, right? So we said there are two, front carbon atom and the rear carbon atom. Correct, right? So this is propane molecule. So first CH3 is here, hydrogen. Now at the rear carbon, this hydrogen very close by. In eclipse they will be close by. You have to remember that. Hydrogen. In staggered, they're equally spaced. CH3, hydrogen. This is the hydrogen, one more hydrogen. That's it. Simple, isn't it? So rotation, where does it happen? It happens between C1 and C2 carbons. So let us write that. Rotation around C1 and C2. Done? Fine. So now we'll be learning the conformers of butane, right, students? I told you I'll be showing the conformers of butane. I'll be showing the conformers of cycloalkanes also, right? So now let us come back and write the heading conformers of butane. So 4 carbon atom, isn't it? Butane is a 4 carbon alkane. So let us write. So here again I'll be showing Newman projection only. Let us write that. Newman projections. Done. So in case of butane, so as I said, 4 carbon atom, how should we start? First, Newman means you have to show this. Then, yeah. Right. So the first different one, CH3, H and H. Now when I draw the rear carbon atom, CH3, hydrogen. Now this is which one? This is the first one. Let us name this fully eclipsed form.
Now we are going to do or show 60-degree rotation. But which one? Between C2 and C3. Rotations between C2 and C3. So let us write that. Rotation between C2 and C3. In the earlier one it was between, as we have done, C1 and C2. Now C2 and C3. When it is rotating, how does this look? CH3. See here, 60 degree. Okay, first this hydrogen I have to write. One more hydrogen, one more hydrogen. So this is the second part. This is called gauche or gauchy. Some say gauche, gauchy, gauche. Yes. Now the same, this one, I am going to rotate it to 60 degree again. How does this look? This is rotated to 60 degree. So you're rotating it like this. So you're right. So first here hydrogen comes here because you're rotating this part, isn't it, like this? So this hydrogen comes here. And the CH3 group comes here. One more hydrogen here. So yeah, this part is over, isn't it? Now we have rotated like this. H, the CH3 has come here. H. We still have the second carbon. So one more CH3 comes here. So one more H here, one more H. Hope this is clear, students. See here, we have rotated this part. It's come here in this way. This also has moved down. This also has moved down here. So the leftover is here. So this is third. We call this as partially eclipsed. Partially eclipsed. Further, I am rotating to 60 degree. Now, this looks hydrogen, hydrogen, CH3. Further, I am rotating. CH3 is here, hydrogen is here, hydrogen. Hope you are understanding, students. I am not able to show it here. Just analyze, imagine it. So this is the fourth one. We call it as anti-staggered. Anti. This is again staggered. Anti-form, but it is staggered because equally spaced. Now I'm going to take this and rotate it to further 60 degree. Okay, I'll further rotate it to 60 degree. How does this look like? This looks like hydrogen, 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 CH3, hydrogen, and CH3. This is the fifth one. This is called partially eclipsed. Further, we'll rotate this to 60 degree. Finally, we get okay, I think this is wrong. Okay, I'm striking this off. I'm sorry for this. Let us draw it properly. I'm sorry for this. Okay, I'm rotating further 60 degrees, isn't it? It has to come like this. Yeah, this is right. Please cross this. This is right. CH3, H, CH3, CH3, H, H. This is the sixth one. This is again called gauchy or gauche form. Some say gauchy, one say gauche form, that way. Right? Right, students? Right. Now let us write the stability order for this. Stability order. Right? For the stability order, see, 1 is less stable than 3. 3 is less stable. Okay, not less stable, it is almost equal. 3 is in equal stability with 5. 5 is less stable than 6. No, not 6. I think, yeah, 5 is less stable than 2. Then 2 is almost equal to 6 less than 4. Let us write what we have written. Let us see once again. We said the first one is less stable than 3. Okay, what is that? fully eclipsed is less stable than 3 that is partially eclipsed, which is almost equal to the fifth one, that is partially eclipsed, right, which is less than gauche, which is approximately equal to 6 because both are 6 forms, and which is less than 4, that is anti, that is nothing but staggered form, that is nothing but staggered. So hope students it is clear. Staggered is equally spaced, fully eclipsed, there's a lot of torsional strain, that is why it is less stable. So these are the conformations of butane. I'll meet you again in the next video with the conformations of cycloalkane, right? So we will also draw the order of stability for different cyclo compounds in terms of chair form and boat form. Thank you for watching, students. Stay connected, stay tuned. Welcome back, students, to the important topic of your conformations of ethane. Done. So what did we learn in previous video? We said the conformations of ethane, like among the infinite number of conformations, Newman projection as well as Sawhorse projections are the most important one. Now today let us learn the conformations of ethane at different dihedral angles, right? Suppose the first one, when I take Newman projections, right, and let me learn about Sawhorse projection in the same page. Sawhorse projections. Done. So Newman projection, as I said, we have eclipsed form, staggered, and the other one is skew. Skew is in between, the angle in between eclipsed and staggered. Let us draw both and see. So when I have to draw the Newman eclipsed form, done. Just see here. How should you draw? You have to draw, yes, center, one hydrogen, one more hydrogen. I said eclipsed, the very close by, isn't it? Because of this, the torsional strain exists here. So hydrogen. So here in this case, theta dihedral angle is 0 degree. The same Newman, if I have to draw the staggered, I said they are equally spaced, isn't it? One hydrogen here, one more hydrogen, hydrogen. Here they're equally spaced, so the dihedral angle is 60 degrees in this case. Now, in the skew, I said it is an angle between eclipsed and staggered. How to draw that? So, carbon center, hydrogen. So one more hydrogen is here. Okay, this, it should not be the same. Here it is like this. I'm sorry for this. Cut this. This is wrong. Here, and one more hydrogen is here. So this is the dihedral angle theta. So I said theta is anything else other than in between these two, anything. The same thing if I have to draw the Sawhorse projection. How should you draw? Carbon. First one hydrogen here, one more hydrogen here, one more hydrogen here. Exactly hydrogen. So theta is equal to 0 degrees. Now here I have to draw theta is equal to 60 degree, the dihedral angle. How should I draw that? Carbon, one hydrogen here, one more hydrogen here, one hydrogen here. 60 degree rotation. The second hydrogen means the second carbon, the hydrogen is here, one hydrogen here, one more hydrogen. Now if I have to draw skew projection, I said anything else. Means the angle is anything else. How should I draw? Carbon. That's it, same straight. One hydrogen here, one more hydrogen. This hydrogen is there only. This hydrogen also there. Little bit means I'm showing the difference hydrogen. So this is how you're going to draw for ethane, both the Newman projection as well as Sawhorst projection, right? So the eclipse conformation here, when it is 0 degree, means the dihedral angle is 0. The staggered conformation here is 60 degree. So in between those two is the screw conformation, right? Now let us see the potential energy difference, the barrier between both. How much did I say? I said it is 12.5 kilojoules per mole, isn't it? Right? Now let us draw one, right? So I'll be showing with Newman and exactly drawing it here. So I'm drawing here Newman projections. The conformation which I've taken here is Newman projection. Now again in this we said we have eclipsed form. In eclipsed, then we have staggered, then we will draw one more eclipsed, then we will draw staggered. Okay, the space is not there as well, right? Here in this eclipsed, theta is equal to 0 degree. Then in staggered, theta is equal to dihedral angle is 60 degrees. Now again eclipsed, theta is equal to 0 degree, and again staggered, theta is equal to 60 degree, and we'll show this energy later. Now when theta is equal to 0 degree, how does it look? I'm drawing the Newman projection. H, one hydrogen, and one more hydrogen here, one more hydrogen here, and one hydrogen here. So here the difference is theta. Okay, I've written here, not the difference, the dihedral angle is 0. Okay, so the potential energy barrier, when I see this, first one is 0 degree, then next one I'll be drawing it as 60 degree, then for this, okay, not for this, basically I'm just drawing the scale, I'm sorry for that, 0, 60, 120, 180. Okay, 180, let us write. So the first one, energy difference barrier. Okay, this is the difference in energy which I am showing. How much is the energy difference here? It is nothing but 12.5 kilojoules per mole. Correct? Right. Fine. So I have drawn that. Once I complete the conversion, then I'll show that. So this next one, 60 degree. This is the thing. Hydrogen, hydrogen, hydrogen. Then equally spaced hydrogen, one more hydrogen, one more hydrogen. Now again rotating, eclipsed 0 degree. Hydrogen, 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 right. So here, this is here, this is here, there's one more hydrogen here. So how much it is rotated? Angle of 120 degree. From here, see here, to this hydrogen to this hydrogen. How much is angle? 120 degree. So I've written this here. Now let us draw the last staggered. Hydrogen, hydrogen, hydrogen. This is one more hydrogen here, one more hydrogen, one more hydrogen. So you further rotated from here till here. How much is the rotation? It is completely 180 degree, which I have drawn here. From here till here, this is only 60 degree. Correct? Hope this is clear, students. This is complete rotation of 180 degrees, isn't it? Now let us show this in energy barrier. So energy, potential energy graph. So 0 degree, right? Highest torsional strain, isn't it? Here. And then it comes down to this barrier. It is decreased, right? It is touching the barrier. Again 120 degree. And then finally 180 degree. Then see here 120 degree, how much is very close by, the torsion strain is maximum. Again 180 degree, when you are rotating, they are equally spaced. So the torsion strain is minimum. So the potential energy barrier between both of them is 12.5 kilojoules per mole. Done? Right, students. So this is your Newman projection as well as Sawhorse projection for ethane molecule. Hope the concept is clear. I'll be meeting you again with the next video, that is conformations of propane. Now, if I have to write the stability order among all these three, hope this concept is clear, students. Right. So if I have to draw the order of stability, so remember, order of stability among all the three, which is more stable? Staggered, because repulsion is very less, isn't it? Staggered is more stable than skew. Among that, eclipse is the least stable, because there are a lot of the atoms are very close by, repulsions are more, automatically the torsional strain will be more, hence it is less stable. Right, students, thanks for watching. I'll meet you again in the next video, which is with conformers of propane and butane. Thanks for watching. So welcome back, students, to one more session of your conformations of alkanes. So in the previous video I've taught you about the conformations of ethane, and then I've taught you about conformations of propane and butane also. So today we'll be learning about the conformations of cycloalkanes. So basically, what are cycloalkanes? Cycloalkanes, if I have to define in a simple term, these are nothing but rings of carbon atoms, isn't it? Rings of carbon atoms. Done? Yes. So here in cycloalkanes, almost up to C20 till C20 ring, so the carbon atoms with C20, till that they're isolated. But among them, like almost 5 or 6 carbon atoms. Common rings are 5 or 6 atoms, carbon atoms. So C20, although they are isolated, we'll be studying basically about carbon atoms having 5, means rings having 5 carbon atoms or 6 carbon atoms. So 5 or 6 carbon atoms, rings are common. Done? Yes. Fine. So first of all, this particular study about the cycloalkane conformations was given by Adolf von Baeyer. Okay. Yes. So here he has studied, Adolf von Baeyer has studied the relative stabilities of cyclic molecules. So let us write that. He has studied relative stability is of cyclic molecules. Cyclic molecules. So the stable forms of cycloalkanes are chair form, boat form, as well as a twisted boat form. Okay, let us write that here. Twisted boat form. Right, these are the 3 stable forms. So when I have to draw the chair form of cycloalkane or cyclohexane rather, so I'll be taking the example of cyclohexane here. So cyclohexane chair form looks like this. Let's draw. Right, done. So when I have to draw the boat form of cyclohexane looks like this. When I draw the twisted form, right, let us count. 1, 2, 3, 4, 5, 6 hexane, 6 carbon atoms. Let us count here. 1, okay, let's start from here. 1, 2, 3, 4, 5, 6 carbon atoms. Here in this case, 1, 2, 3, 4, 5, 6 carbon atoms. So these are the 3 common conformers of cycloalkanes. So here, when I have to speak about their internal angles, right? So the internal angles are, between the atoms is 120 degree. Internal angles here are 120 degree, but an angle between the successive bonds, as I've seen here, the angle between successive bonds is 109 degree. but the angle between successive bonds, how much is it? Is 109 degree. It's just like a tetrahedral angle, isn't it? Tetrahedral angle. Done. So when I have to draw the chair form, as I told you, chair form, boat form are important. Let us draw the chair form of this and represent. So when I have to draw the chair form of cyclohexane, it looks like this. See here. Okay, now start filling the hydrogens. One hydrogen here, one more hydrogen here. Right, first of all, basically this is the first one. This is the first one. This is one. Then this is the second one. This is the third one. This is the fourth one. This is the fifth one. This is the sixth one. Done? Yes. So this is the chair form. Now this is called axial hydrogen and this is called equatorial hydrogen. Axial hydrogen and equatorial hydrogen. Now suppose if I have to draw the boat form of cyclohexane, how does it look? We have already drawn in the lesson, but I'll be showing representing the hydrogens. Done. Now fill the hydrogens. One hydrogen, second one, third one, fourth, fifth, and this is the sixth one. So this hydrogen and this hydrogen is called flagpole hydrogen. Flagpole hydrogen. Right. So cyclohexane basically is expected to have more deviations from ideal angle, and means because of that deviation, like let us draw, and means we'll be representing that particular structure, that is a chair form, this in your boat form, because of this deviation, the existence of the chair form and the boat form, where the bond angle is exactly tetrahedral angle. So in terms of Sawhorse projection, I'll be showing that to you now. Yes. Right. This is how I represent. Right. So this is the Sawhorse projection of chair form and boat form. Hydrogen, 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 one more hydrogen, 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 hydrogen. This is one more hydrogen. Here you have one more hydrogen, 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 and hydrogen. When I have to draw the boat form of this, flagpole hydrogen, this is one more hydrogen at this point. Hydrogen, this is also hydrogen, flagpole, this, hydrogen, hydrogen, this is hydrogen, this is hydrogen. So this is the A form of this is the B form. So both are Sawhorse projection of chair form and boat form. Okay. Yes. Done. Of cyclohexane. So among the order of stability, if I have to say, so the order of stability, if you're asked in the question, among all the forms of cyclohexane, the order of stability among them, the chair form is the most stable form. Then twist form, there's one more then boat, then half chair. So this is the order of stability of cyclohexane projections. So when I have to see the some factors on which it is depending, so let us write what are the factors on which the stability of different conformation depends upon. So basically there are two important factors which you have to remember. So let us write factors affecting stability of conformations or conformers or conformations. So basically there are two factors. Let us put a line here and learn. The first factor is called torsional strain. The next factor is steric strain. Okay, right. What is this torsional strain and steric strain? Let us see. Let us write the difference. So basically, when there is a torsional strain, there is increase in potential energy of a molecule. Okay, the increase in potential of the energy of a molecule. Here also, due to steric strain, there is increase in potential energy of a molecule. Now, ma'am, what is the difference? You should ask me. Difference is both the strains are occurring due to repulsions only. Okay, let us write that due to repulsion between electrons in bonds, okay, that do not, we'll do an example, you will understand that do not share that do not share an atom. Okay, now here increase in potential energy of the molecule, same thing, I'm not writing again, due to repulsion between electrons in atoms that are not directly bonded. What are those directly bonded? What are those? Let us see. So torsional strain means, if I take an example, this is one, chlorine, hydrogen, chlorine, hydrogen. So the strain or the repulsion between two bond, these two, the electron cloud of this one and the electron cloud of this one, there's a lot of repulsion. So because of this, there is certain amount of torsional strain which exists, and because of this there is increase in the potential energy. So this is called, this particular repulsion, due to repulsion, the strain caused or the strain formed is called torsional strain. Now when I have to take the steric strain, I said they're not directly bonded. How is it? Let us take one carbon here, one more carbon, there is one more hydrogen here, there's hydrogen here, this is linked to one more carbon, one more hydrogen, one more hydrogen. So this carbon also is linked to one more carbon, which is linked to hydrogen, right? So this also is linked to hydrogen, right? So there is a CH3 bond here, there is a CH3 bond. So this and this is linked. Now see here, the strain which is created between two atoms, or these two molecules rather, which are, they are not directly bonded. See here, they are bonded here. So because of the strain which is the strain which is formed due to the repulsion between these two electron clouds is called steric strain. So here it is among the same molecule, here it is between two which are not bonded. So these are the two factors, one is the torsional strain factor, one is the steric strain factor, because of which the stability of the conformation differs, or because of these the stability of conformation, that is the chair form, boat form, twisted boat, all will vary. And this particular thing, these are held together at a distance equal to or greater than the sum of their van der Waals radii, right? So these are held basically, you know, I said this particular electron cloud and this particular electron cloud will be repelling. So what distance? They are held at a distance equal to or greater than the sum of van der Waals radii. So if this distance between them is smaller than the sum of the van der Waals radii, if that, when I add these two, the distance, if I calculate, if the radii is smaller than that of the van der Waals radii, they start repelling. And that is why there is certain amount of strain. So once again, if the distance between them is smaller than the sum of their van der Waals radii, once you find the van der Waals radii, if the distance between them is lesser than the sum of this, then this starts repelling. When this starts repelling, what will happen? Automatically that affects the conformations of the particular alkane. So these are the conformations of cycloalkane, students. Hope this is clear. I've explained about the chair conformations. I've explained about, just see here, I've explained about the chair form, boat form, twisted boat. Then I've given you the angle between them. I've also drawn you how to represent chair form and boat form, and I've also shown you the sawhorse form of chair and boat. Then I've given the order of stability of this. I've also given you the factors which are affecting that. I showed you what is torsional strain, what is steric strain in both the cases. So thank you for watching, students. I'll be meeting you with the next important topic. I think I have completed the conformations. So all the isomerism concept is done. So we have studied about different isomerisms. I have gradually taken you into I've first given you the flow chart of isomers. I've given you the flow chart of isomers. Then I've taught you what are the structural isomers, stereoisomers, different types, right? In my next video, as the topic is complete, I'll start with the next important topic, that is nomenclature of organic compounds. Very interesting. Here I'll be clubbing both 11th and 12th nomenclature. I'll be teaching you what is IUPAC nomenclature. I'll be teaching you what is common naming or common system of nomenclature. So we'll be learning that is a trivial system. So everything in detail with loads of examples. Thank you for watching, students. Stay connected, stay tuned, stay happy.